to introduce you this morning 3 wonderful lectures, which are the plenary lectures under the program of Class B on Exact Sciences. So this will be a trip towards the end of space and time while approaching the event horizon moving towards a black hole in the universe. The black holes were first predicted by the general relativity theory of Einstein and then only recently finally imaged. So we will go there, we will go into the space and then come back to the Earth, to time and history, and see how we get prepared to face one of the biggest challenges in the 3rd millennium, which is that of ensuring the production of the sufficient levels of energy that we need in order to support our growth and further progress as human beings, and also ensure that this happens without destroying the Earth, and ensuring that we care about the Earth and we ensure sufficiently low levels of pollution and don't disrupt the environment around us. So we will come back into time and history first and see how we faced already in the past of our history a number of energy revolutions and how those impacted the humans and the environment around us and how we reacted as human beings. And then we will move to today and into the future to see what are the most promising ways to produce clean, renewable energy in the next decades and quite likely in the next centuries. And this will get us in a way back into the cosmos to see the same energy which is produced inside the stars, which is fusion energy. So that's the trip of this morning. The first speaker this morning will be Professor Heino Falcke. Professor Heino Falcke is an astrophysics and a radio astronomer. His contributions have been fundamental for understanding black holes and cosmic particles. He has been a pioneer in imaging the Event Horizon Telescope, which finally led to the first image ever of a black hole in 2019 and the first image ever of the supermassive black hole which is at the center of our galaxy. So that's where the journey starts from this morning, and I invite Professor Heino Falcke here. Thank you.
Thank you. Thank you for having me here, being at this wonderful meeting. I think some people had a big party yesterday evening, so they will still come in. I want to acknowledge and be thankful for the Balzan Foundation, who actually has been helping to co-sponsor part of this event, and where I had the honor to receive that prize last year, which is really was a memorable moment. And I want to take you on this journey, and as you said, we'll start with Albert Einstein, who reshaped our understanding of space and time. We thought, it was a big revolution to realize that gravity is a force. That's what Newton, after the discovery of Kepler and the planetary orbits, figured out, and we were able to describe the orbit of the planets. And then Albert Einstein really changed our concept of space and time, saying that space nor time they are not absolute, but they're relative. They are what you observe. In essence, you could say, space and time don't have an existence of their own. They're always what I measure. And how do I measure them? I measure them with light. And light is a true constant in the universe. The speed of light is a true constant. And gravity, he was explaining then, not as a force, but as a property of space-time, the combination of space and time. And there's this famous quote in this theory: matter tells space-time how to curve, and the curvature of space-time tells matter and light where to go. And that's exactly this interface. You can think of space and time as a big theater, and matter and light as the actors playing in that theater. And they both change each other all the time. And the way gravity is explained is that if you, picture gravity or space as a two-dimensional surface, then matter will curve that surface, and that makes light actually follow the curvature and make a turn around a massive object. And that was then used by Eddington in the 1919, using a solar eclipse to see that actually the sun was actually changing the appearance of stars behind it because it was deflecting the way light was propagating. And that, that's exactly what confirmed the theory of Einstein. But then also, light has to take a longer turn, so to speak, because space is stretched, but it still goes with the same speed. And speed is, as you remember, of your car, it's kilometers per hour, right? Length per time. So the ratio between length and time is constant, but length and time can change. So if length is expanded, time needs to change as well. And that's what we see, that actually the time we measure actually changes as matter curves space and time. And you see this in the form of GPS satellites, which have very precise atomic clocks, and they actually go at different speeds, whether here on the ground or up there in space, because they're 38 microseconds per day. They go faster than here on the ground. And so that's purely relativity. Now you could take this to the extreme, and that's what Karl Schwarzschild did, actually, in the middle of World War I, where he was calculating and taking, in just a few months after Einstein published the theory, what would happen if you put all the matter in one point. And as all physicists know, this is just, is not reality, right? So we don't put all the matter in one point. It's just a mathematical convenience, which means we can calculate it easily. And so if you do this, wonderful equations become simple, and we can solve how space-time looks around it and how light would behave. And then something strange happens. Two strange things happen. Light, which in the presence of vacuum would never start and would never stop. Actually, time itself doesn't have a time of itself. When time itself, light doesn't have a time. It's only when you create it and destroy it that you can measure time. But then light, if you go around this strange space-time, suddenly stops. Light comes to an end point. And there is a singularity. That's because all the matter is in one point. The curvature of space-time becomes infinite. So you just go into an infinite deep hole out of which you can never escape. And sort of that's the end of time as well, because you cannot even measure time inside the singularity. And there's another strange point, and that's what we call the event horizon. That's actually outside the singularity, well before you reach the singularity. That's when the curvature is so strong that actually light cannot escape before. Light will still exist, it will continue down, but it will not be able to escape. And that's like, imagining a waterfall where you're swimming against the current before you go over the cliff. But once you go over the cliff, you're still alive. You're only going to die once you hit the singularity at the bottom, okay? But you have no chance of swimming upwards this waterfall. And that's exactly what light is doing. So once it's gone over the event horizon, it's not be able to escape anymore. And that was a fundamental, also philosophical problem, because it means that no information will ever escape that object. Because light is the fastest speed we have, and actually it's an information speed. It's not just the speed of light, it's the speed really of information. And so no information can actually swim against the stream of this waterfall. And that means there's a physical reality in these black holes, which does exist. Physics doesn't stop. It only stops essentially at the singularity, because that's unknown physics. But we cannot measure it. And in physics and science, everything is about what we can measure. And so there's a part of space and time that we cannot measure, and that's inaccessible to physics, even though it is part of physics. So Einstein, saw that. He liked the mathematics, but he said, of course, that doesn't exist, right? This cannot exist in nature. And even tried to prove that it doesn't exist, but he failed. In fact, Oppenheimer then showed that actually these objects can form. And today we call them black holes, and they form in the collapse of stars, for example. And they can be even existing in larger objects. In fact, this all became interesting again when the quasars were discovered at the end of the 60s, early 70s. We found really, really bright lights in the universe out there, quasi-stellar radio sources, but they were billions of light years away, as small, it looked as small as a star, but they really turned out to be like planetary system-sized objects, but with the energy of 30 times of all the stars in our Milky Way, for example, compressed into one region. Enormously powerful objects, and if you look at one of these galaxies, for example, here with radio eyes, then you see a powerful plasma beam shooting out, which can have a length of 1 million light years, and again has a power of more than all the stars in our galaxy. And we think that they are powered by these black holes. Not a little black hole, but a supermassive black holes, where you had not just one star, but millions, sometimes billions of stars collapsing into one object, into one singularity, which is the most bizarre and exotic scenario you can think of. But it's also the most efficient way of generating energy. We just heard about nuclear stellar fusion reactors. This is even 10 times more efficient. So, if you would have a black hole and you would have 10 buckets of water, you pour it in there, you can provide all of the Netherlands with all forms of energy for an entire year, right? Just 10 buckets of water that you pour into a black hole. That's how efficient this process is, and that's how you can produce a lot of energy into a very small area. And the way it works is matter will spiral around and will actually reach almost the speed of light. Then you have friction, which is typically magnetic friction, which heats everything up to billions of degrees. And it starts to radiate. You have strong magnetic fields, which shoots out these plasma streams, and all hell breaks loose. And then, of course, all that energy disappears in the event. Some of that is, of course, radiated away, so we see it. But some of that goes into the black hole, and you see it as darkness. And so the darkest darkness, the coldest temperature in the universe, really is that black hole in the very center. And surrounded, it's by really the hottest temperatures and the brightest brightness you can imagine. So again, an area of extremes really in the cosmos. And let me just, one final thought, it also echoes really the beginning of the universe, if you think about it. Where everything came from one point, here everything ends in one point. In the beginning of the universe, everything starts from one point with extreme densities and extreme matter configuration where there's not even matter existing, just energy. And so what's happening in black holes to some degrees echoes what you have in the Big Bang, plus the fact that you cannot look beyond the Big Bang, like you cannot look into event horizons. Now, if you want to understand these objects better, you want to go for the big ones. And at some point I want to see, right? Seeing is believing, at least in science. And there you want to go to the objects which are the largest on the sky. And what has been found in the past is that if you have supermassive black holes that typically exist in the centers of galaxies, because that's where the high star concentration is, where stars can collapse, and a black hole will always grow and become bigger and bigger. And it turns out the bigger the galaxy, the bigger the black hole. Seems simple, but you need to show it. And they're typical galaxies like our own, the Milky Way, spiral galaxies, and they have millions of solar masses. And if you ask, where is the closest normal galaxy, well, it's our own. So the biggest, normal supermassive black hole will be in the center of our galaxy, the Milky Way. And then there are monster galaxies, elliptical galaxies, which are created by the merger of multiple of these spiral galaxies if you have a big cluster. So where is the biggest cluster in our universe that's the closest? Well, it's the Virgo cluster at about 55 million light years away, and at the center of this cluster is the galaxy M87. So this is the biggest of the monster galaxies nearby, and the Milky Way is the biggest one. And if you look at the evidence that was there for their black holes, one is 4 million times the mass of the Sun, the other one was 6 billion times the mass of the Sun, 1,500 times bigger than in our Milky Way in M87, but also about 1,500 times bigger, but also 2,000 times further. So essentially, it's much bigger, but also further away. And the size of a black hole scales linearly with the mass. So 2,000 times, it would have been, in our phase, it would have been 2,000 times bigger than the Milky Way, but then you move it 2,000 times further away, then it's exactly the same size. That's one of these weird coincidences that these completely unrelated galaxies with the two biggest, examples of black holes have exactly, within a factor of 2, the same angular size on the sky. And they have both radio emission that you can use to image them. And that's the other part of the story that allows you to do this. This is the galaxy M87. In fact, if you look at it here, you see this little streak of light sticking out there, which was discovered, I think, 1918. So just a few years after Einstein discovered general relativity. So astronomers saw something sticking out, which essentially we now know says, look, here is a black hole. See my finger? But nobody at the time had any clue that this completely theoretical, abstract thing, like a black hole, which was just a mathematical curiosity, had actually, finger of God pointing at it in this galaxy. Okay, it took 50 years to, get a sense that this might be the case, and another 50 years, essentially, to actually image it. And what you see there is this plasma jet. You see this here, this radio emission shooting out of the center of the galaxy. And this is actually the large-scale structure imaged with the LOFA array in the Netherlands, where really 200,000 light years around the Milky Way, in the galaxy M87, everything is filled with this plasma, all coming from a tiny scale, the size of a solar system. And then the center of our galaxy. This is our galaxy, the Milky Way. You see the dust clouds, this dark band of light, obscuring a lot of the stars in the galaxy. It's a disk galaxy. We are sitting in the disk, so we see it from the side. That's why we only see a fraction of the galaxy. But we can zoom in. Essentially, that's what the group of Reinhard Genzel has been doing for a long time, using infrared cameras, because infrared light will go through that dust, as radio emission does. So it's like an X-ray, so to speak. And then you see, to the very center, you see these stars. And these stars, imaged over 16 years, start to move. You see them actually literally move in front of your eyes with 8,000 kilometers per second sometimes. And if you look at this star here, it actually goes on an elliptical orbit around a particular point with 8,000 kilometers per second. And if you go, with that speed around the corner, you need very good tires to not, being flung out, or some force that keeps you stable. And that force, of course, in the universe is gravity. And how much gravity you need? You need 4 million times the mass of our sun concentrated in this one point where the star orbits around. And that really sealed the case for the fact that there are compact dark masses in the center of galaxies. There had been suspicions that they were there, but this really sealed the point. There are compact dark masses. This is not just an extended thing of something. There's no dark matter. It's really something compact. And that's where Reinhard Genzel got the Nobel Prize for a few years ago for this measurement, and André, I guess, the American competitor, essentially. And but it's not, we don't yet know whether it's a black hole or not. So that's the key question. And now here is the radio picture taken with the Pathfinder array of the square kilometer array in South Africa of the central region of our galaxy. You see the plane of the galaxy. Now everything lights up. Radio emission actually penetrates the dusk. You see stars that have exploded. You see molecular clouds which still form stars. You see magnetic filaments. It's just a fantastic ecosystem of things going on in the center of our own Milky Way. If you then zoom further in, you see this streamer of gas. And then in the very center, you have a tiny, tiny radio source, just like a pin of a needle in the very center, but very, very bright little thing where a lot of radio emission is produced. And that was discovered in 1974. It had, some unusual radio properties, and people had been wondering whether that is the central black hole of our galaxy. And when I, did my PhD, the first measurements of Genzel came out. The first, high-frequency radio measurement of that source came out, and we thought, but actually I was working on something else, but it sounded like this is interesting. This is an interesting thing. We need to work on this. And we tried to explain that radio emission. I made a model for it, comparing it to galaxies and quasars and in other galaxies, and we said, well, it's like the quasars. It's just on a starvation diet. It's just, a black hole that's not fed enough, right? So it's a very, very tiny black hole which is sitting there and starving. But then everything else is the same. And we're calculating the radio emission. And one thing that stood out was that this radio emission should come, if you go to high enough frequencies, should come from near the event horizon. So that you're actually illuminating at a certain frequency the event horizon with light. And so the first thinking is, okay, can we see it? Because in radio astronomy, we can actually create the telescopes with the highest resolution by using interferometric techniques, which I'll explain in a moment. At that moment, I was a bit stupid. I was just calculating how big it was, and it looked like it was a bit too small, right? So it was like, you would need to build a telescope bigger than the Earth, actually, to see it. And with all arrogance and self-confidence you have, you think, oh, well, that's not going to happen in my lifetime. But then, I actually overlooked a certain effect. And it turned out that had been in the literature for decades. We just had forgotten about it, and I was just glancing through a book in a library, and just happened to stumble over an article, which is something you wouldn't do anymore these days with electronic means. Right? I was turning the wrong page, literally. Right? So I saw things and said, that's strange. Oh, yes. Right? So it's this one moment where you say, oh, gosh, I overlooked something. And that, of course, is the obvious effect that light is bent around black holes. And what you see here is actually a picture from Max von Laue from 1921, but actually which goes back to a lecture from David Hilbert, famous mathematician. I think it was summer 1916, again, just a few months after Einstein published his theory of relativity, calculating how light would behave around such a strange object, which wasn't called black holes at the time. And so what happens is the light comes in here, which is, you look at it, the light will be bent, and at this critical separation here, it will actually end up on a circular photon orbit. It will actually go around in a circle. If you stand at this point, you look forward, you actually look around the black hole, and you see yourself, your back of yourself in front of you standing. Right? That's how space is curved. But that also means that everything in between here and here will be captured. So the impact of the darkness, the missing light, actually is much bigger than just the size of the event horizon. Essentially, the black hole amplifies, magnifies, lenses itself. It makes it 2.5 times bigger, sometimes even 5 times bigger, depending on spin. And that was like, oh, yes. And that means actually it was big enough to be seen with a telescope the size of the Earth. So the next step was to A, convince your community that this is possible, and B, that and do the experiment, right? So there are 2 different steps. So it took a little while, and then at some point I realized, okay, just talking is not enough. You have to really show images, do good marketing. So just explaining these concepts not enough. Show an image, and so this is something that we published then was sort of how would a black hole look like at these frequencies in the presence of other effects that are relevant in the galactic center. And you would see this darkness here, and you would see a ring of light surrounding it. And we called that darkness the shadow of a black hole. Not the black hole itself, because the black hole really is the curvature of space-time. What you see is the shadow, the lack of light. The light that's disappearing. That's why it's called shadow. And we gave it a nice color. At the time, color print was becoming available. You'd had to pay for it, but okay, I thought it's worth it. And we gave it this red color. It's radio emission, right? Radio, in principle, is very red, red glowing. But it was more like the artistic thinking, right? So it's danger. It's glowing. It's hot. That's why I chose this color. And actually, it stuck. So this is sort of an artistic choice. This is not a scientific one that you see in these images. And we said, if we can show that this is observable with very long baseline interferometry at sub-millimeter wavelengths, assuming that the accretion flow is optically thin. And how do I picture this? Picture a dark object, in this case a teapot, in the center of a campfire. Right? The campfire you can look through. It's optically thin, it's transparent, but it's bright, it's light. But you see this dark object in the very center, which absorbs all the light. Okay? This teapot will reflect still, but the dark object will just suck in from all directions light. And in fact, because it also curves space-time, you actually sometimes look from behind, from there. I mean, you see everything at once in a black hole. So it's not a simple teapot, but the analogy is the same. Now, of course, today we have these simulations much more advanced. These are, this is to some degree, jokingly VRG, RTT, 3D, GR, MHD simulations. It's virtual reality, general relativistic ray tracing, three-dimensional GR, MHD, magnetohydrodynamic simulations. So essentially what you have a curved space-time, you have matter flowing around. It's like weather with magnetic fields, plasma flows. Then you create particles. Then you create the radiation. The radiation will go on curved spacetimes, curved trajectories. It will be emitted and absorbed, and then you look at what you see. This is essentially what we do. This is a sort of a more PR version of a really deep numerical supercomputer simulation. You see the plasma flow going around. This is multiple frequencies, multiple colors essentially at once. It's a thick accretion flow, and then you see it being bright, and then at the very center you see this this dark patch. And if you go to, you select on frequencies, like again, an X-ray at your doctor would just, use an X-ray rather than your visual eye. With your eye, you would see your skin. With X-rays, you see your bones. And so we tune to the right frequency, and what you see is then this ring of light, which is actually light going around, and you see the darkness. And that ring of light has a characteristic size, which is proportional to the mass. And so the diameter of that shadow is 10 times what's called the gravitational radius, and the gravitational radius is, for the experts, gm over c squared. G is the gravitational constant, c is the speed of light, m is the mass of the black hole. And that is an angular width on the sky for M87. That galaxy is 40 microarc seconds, and for the center of the galaxy is about 50 microarc seconds. What's a microarc second? 40, 50 microarc seconds, about a mustard seed in New York as seen from here. Okay, so that's the size of the object you need to see. That's possible. And you do this with very long baseline interferometry. It's something that I didn't invent. I was at an institute which was working on these technologies. You just had to sort of extrapolate into the future and go to higher frequencies. It used different telescopes. You needed more digital technology to make it work, but in principle, it's very simple. Now think of a telescope, literally the size of the Earth. What will it do? And if you just take 2 points of the surface of this telescope, light will come in, will be reflected, and will be bundled in the focus of this telescope. Okay? And so essentially it's a plane wave coming in. If you have a point source, it will be bundled in the focus, and these two light rays will interfere with each other. They're like waves. And so you get an interference pattern from just those 2 points. And that's what you would see if you just have a telescope with 2 reflecting patches. Yeah? And then you get an interference pattern between these 2 things. Every telescope, your digital camera does that. Okay? But it has many other connections, many other patches that actually are combined. Okay? But that's a simple point of any imaging instrument. And what we do is, we sample the radio waves here and here. We actually can measure the wave, because it's a classical wave. It's not photon limited, so we actually measure the amplitude and the phase. We can digitize it. We can store it on a hard drive. We can time tag it with an atomic clock, know exactly when it arrived. And then this bundling in the focus we can do later in the computer. Yeah? And what that measures, again, for the experts among you, each of these combinations measured a Fourier component of that image. So every telescope is a Fourier transforming instrument, right? And we only measure one Fourier component in this image. Now, then you add more combinations here, and you see these interference patterns overlap. And the more of these interference patterns you have, the more patches you have in your telescope that you combine, you in the end are able to recover the structure of this object. It happens to be a teapot again. And you can see it. You don't see every detail because there's information missing. It's like a lens where everything is scratched and just on a few patches are available. And so in order to get a nice and clean image, you need to employ some imaging cleaning algorithms, right? You can just look at the raw data and it tells you a lot. In fact, when I saw the first data coming out, I knew exactly what we were looking at. But then you need to go through a long process to actually make it then nice and pretty. And so in 1917, we had our big first experiment, a global collaboration of 300 people, different institutions, 13 stakeholder institutions, among them our own university, and using these telescopes, equipping them with digital equipment, atomic clocks, and people. And we had really a mixed, diverse team around the world. And for my group, we had, which was, by the way, supported by the ERC. Thank you for that. I mean, this was really the game changer. Getting a big ERC synergy grant would not have been possible without to play on that level. And then, we were at these telescopes. I was in Spain. People have heard the talk before. No, I'm always joking because there was the best food really, among all the telescopes. It's an illusion food, and they were cooking for you. This is a crew here in Chile. Before the observation, 2 weeks, day and night, we were observing because the weather, turned out the weather was good everywhere. You need good weather for these high frequency, 230 gigahertz observations. And for some miraculous reasons, there was good weather around the world and all the technology worked, which usually is not the case, right, when you do an experiment the first time. And I was expecting like 10 years of misery ahead of us, right? And then everything works on the first time. That just, doesn't happen often in science. So it was a bit exhausting. This was before, this was after the observations. But it was, again, was worth it. We then went into, this was a collaboration meeting in Nijmegen in November 2018, when we had actually analyzed the data. In fact, we had split up in multiple teams. We had done everything, every step from calibration, there's a step called correlation, calibration, imaging, and analyzing. We've done everything at least twice. 2 different groups. That's the advantage of having global collaboration. Also working with astronomers, usually like to work on their own teams. They don't used to work in these big teams. So, no, my method is better than yours. It's good, because then you can check each other. And so we were checking literally every step in this process. We were checking internally before we went live. And some things like the imaging we did 4 or 5 times, which had never been done before in this community. And then the big day came. A press conference in Brussels. Actually, we said, well, do we have one big press conference in Washington, or do we have... I said, well, no, I think we had a lot of European funding, right? And it was our idea, so we should have one in Brussels. Okay, so in the end, we had a press conference in Washington and Brussels, but then we had one in Santiago, one in Taiwan, one in Japan. I think it was great. It was just not one point, it was actually many points around the world where we had press conferences and presented this. This was the first, I think, big science result announced in Brussels, in the press room there, and I had the privilege to present it there for the collaboration. And this was the movie that we showed, with a little bit of music from my son, who's making film music. And we're zooming in from the high plains in Chile and at the Atacama Desert, looking towards the constellation of Virgo, where the galaxy M87 is, 55 million light years away. You see this beautiful LOFAR image there as the music dramatically increases the expectation of the viewer, and then you see this plasma stream shooting out from the center of the galaxy. We're switching actually telescopes until we reach the highest resolution ever achieved, and saw that. By the way, if you listen to the music, I was expecting my son to end in like big crescendo, like bang, right? But it actually goes down again, at the very end. And that's exactly what a black hole is. It goes up, it becomes more dramatic, but then it fades away, and that's the darkness. And so the real key result is the darkness that you see, because that really is, where light disappears. That's the point of no return. That's the first time we look into the event horizon, and we see this essentially eternal darkness. And it was, it was front page news everywhere. It was like 4.5 billion people saw this image in the next 2 weeks. It was just, one of the probably most seen picture of science in recent decades. I always say, 4.3 billion always forgot it then 2 weeks later, but it's okay. The internet went wild, but it also, was included now in the photo collection of the Rijksmuseum and the MoMA in New York, because it became sort of a cultural icon. A year later, we had another experiment. In fact, we had more experiments. We published a second image this year, actually, confirming the first one. And it has exactly the same ring shape. The intensity changes, that's what you expect, but the size of that ring, which is directly proportional to the mass, that's what needs to be constant. And it was constant within better than 10%. We also measured polarization. Polarization is actually, of the light, is actually created by magnetic fields. Magnetic fields actually polarize the light, and that allows us to infer the direction of magnetic fields. And in fact, this magnetic field directions is very consistent with what we expect in our models, where magnetic fields are dragged along in these accretion flows, and then at the inner edge, a plasma jet is being shot out. And that's exactly what we see. So this radio emission really comes from the inner edge of this accretion flow and where the jets are being launched. So we see essentially stuff flowing out to a large degree. And then there's also the center of our galaxy. As I told you, it's 1,500 times smaller. It also means gas is moving at the same speed, but it takes, it only takes a few minutes to go around rather than a few weeks to go around, because it's just smaller, with the same speed. And so that makes it a bit more difficult to image it, because on the left one is a movie and the right one is a movie. It's just with the speed differences. So the one flickers, goes quick, the other one is slow. And that was sort of a challenge that we had to deal with. And that's why it took longer, even though we took the data at the same time. We wanted to be careful. We also, just to give you a little bit look under the hood, every imaging and processing algorithm that we used was tested extensively. So what you have here is a simulated source structure. So there's a ring, what you expect, but then a disk, or you had a point, or a double source, or a simulation. And then everyone who came with their favorite method said, oh, I know how to do this, had to script it. And you were given these different source structures. They had to process them all. And you could only use the methods and parameters that were able to accurately reproduce very different types of structures. Okay, so that was a test. And again, these kind of tests have not been done by essentially anybody in the community before to that level. And these are different types of methods. And you see they all largely reproduce, they actually do reproduce these structures. And I just say this because sometimes people, all kinds of myths going around in the community. We do use simulations to test our analysis, but we do not use simulations to actually do the imaging. Some people say, oh, you use your models to actually do imaging. No, we do not do this. Or some people say, oh, use machine learning to do this. No, we don't use machine learning. Okay, so I just say this because sometimes people, it's an 80-page paper, and sort of most people haven't read it, and so they come up with all kinds of things they sometimes say. And then we actually literally produce thousands of images because they're all valid. So the top 2% best images that you make, you produce. And these are thousands of images that we make in script. And then you say, which one is the best? They all fit the data. Okay, they all fit the data. There's slightly difference. If you look at them, they all have rings. Well, essentially, you combine them, and then that's what you get. That's a combined image sort of all possible images that fit the black hole in the center of the Milky Way. And again, it has a ring, and it has the ring structure and the right size. I think I have to speed up. Well, you can also sort them in different structures. I'll just say this because these are the details of the imaging procedure. And so, I mean, this is sort of the most common kind of structures. All of this fits the data. This one here, which doesn't have quite such a nice ring, is only a few % of the data that looks like it. Now, of course, we have more data now, and we'll have more in this in the future. So this is a summary here of those images. This is the M87, and this is a solar system in comparison. This is Neptune's orbit here, so the outermost planet. This is a galaxy. This is Mercury's orbit. So that's the innermost planet, right? So that's inside Mercury or outside Neptune. That's the difference between those two rings. And that was a prediction. And I think it was quite, and I even got the color right? So in the prediction. So anyway, no, that's of course a joke. And what I find most impressive is this one here. As I told you, the shadow size is proportional to the mass. And what you see here is the mass. You see the shadow size. And this is essentially what GR predicts. Okay, it's a linear relation, very simple. And this is what M87 was. Within 10%, it was on target, okay, of what GR predicts, because we have an independent mass measurement. This here is from gravitational waves. I mean, as you know, there were gravitational wave measurements of stellar mass black holes merging, and it's an indirect measurement, but it obeys the same essentially gravitational waves follow the same optics as light does. And so it actually also measures essentially the photosphere. That's the important thing. So the size you measure is actually the same, it's essentially a shadow size. And you can measure the same components of the space-time metric. That's what was shown in this paper by Dimitrios Psaltis and for our collaboration. And essentially, for 8 orders of magnitude, this fits that relation. And then, galactic center came in next, and where does it fall? Here, right? And so over 8 orders of magnitude, this theory, gives that shadow right. And I think that to me really, seals the case pretty much. Of course, we also, I'll skip this one, I have too much to show. These were the last campaigns we had. The previous slide was about numerical simulations, which I'll skip. We had more observation, 21, 22, 23. In fact, I've seen some of the results already. Here is new telescopes in France. The Greenland telescope joined. Some of them had better weather, some worse. And we are now working on a project to actually put a telescope in Namibia together with, I have 5 more minutes, but including questions, right? So then I'll try to speed up quickly. So we have this telescope in Namibia. Well, we're working on together with our colleagues at the University of Namibia because we want to really make a movie of black holes. And right now we have too few telescopes in the east of the world, which is, in this case, is actually Africa and Europe. So, and so these red lines are the connections that we'll add. And if you have, right now, the first few hours you make an image, you would not even get a ring. But if you add 1 more telescope, you have enough connections because, every telescope connects to everybody else. Essentially the number of connections goes quadratically. You get a ring, and you could even make a movie. So, like sort of every hour you could make an image, and you see something go around. That's the basic idea that we want to have. And I just want to show this because this was just a side project, because we have an outreach project in the Netherlands where we go with a mobile planetarium to schools. We thought that might be good because we need young students, because there's so many bright students also in Africa and in Namibia, and they want to do something. We need to do some outreach there. And there was sort of very small astronomy department. And now what's happening is, this planetarium project was now, taken over by students and master students and PhD students in the University of Namibia, and they go to schools. They have now, I think, more than 15,000 school children, in fact, by now that they have reached within 2 years. It's just amazing. And from really the youngest to the oldest, they sort of give a planetarium tour. They talk about the universe.
One by one.
So this is, and it's done by students here. So it's completely run by them, and they adopt it. And so, which is, and kids are the same everywhere.
Okay. So you can use.
Yeah. So it's this awe and wow that you see. It's just, it's. And I was, in one of these classes, you're dragged in and you're bombarded with questions. And in fact, questions sometimes you cannot answer. Oh yeah, sorry. Yes. Okay. There was a. So it's amazing. Last thing, I'll just skip over it quickly. We want, yes, I do. Now I'm old enough and bold enough to say, yes, we can go to space, make a telescope that's bigger, having an array of 2 or 3 spacecraft in space, and in fact, that could make images like this, really detailed. Actually, it's missing some details here. Even make movies and so forth. So, let me stop here. I think we've seen the black hole shed twice in 2 different sources, actually at different times. So I think black holes are real for all practical purpose, beyond any reasonable doubt. I think we can now think about black holes, and the event horizon relativity holds over 8 orders of magnitude. We can understand the astrophysics, which I skipped over. And really, we are now in the age of experimental space-time physics. I think that's really is a fundamental change compared to like 10 years ago. Thank you.
Thank you. As Professor Falcke said at the beginning, he won the Balzan Prize 2023, which is definitely one of the most prestigious and most relevant prizes across Europe. There will be a second Balzan lecture in the afternoon under the program for the life sciences. So you're invited to get there.
It's by Eske. He's really, really interesting stuff. So yeah. Listen to it.
So this was a fantastic journey. I mean, through the way we can compare ourselves to what exists around us. Think at just the fact that all of this stuff was simply predicted by theory 100 years ago. And then now it became true through real images which show it. I think this is really amazing. So the floor is now open for questions, please. Yes.
Thank you for this wonderful talk. I was wondering, do you know when a star falls inside a black hole, if you write down the mass balance, how much of the mass of the star is lost, and what kind of particles are those?
Oh, you cannot give a general answer to this because it really depends on the ratio between the black hole mass and the star and the orbit. And so there are simulations for the center of the Milky Way, for example. There was one cloud going in, and you would see that some fraction of that cloud would actually end up in the black hole and the rest would be flung out. But if you have a more direct orbit, then essentially the entire star could disappear. But we see these tidal disruption events, which we think there's suddenly a galaxy brightens up, and there you expect that the star is just tidally disrupted and is sheared away, and then it only gradually falls into the black hole. So typically, I think most stuff will take a while until it falls in. And direct hit, well, you will hardly actually see because we'll be gone.
Thank you.
Yes.
How does the, if at all, the Hawking revision that allows for a certain amount of energy leaking out of a black hole affect the imaging task that you've so elegantly described?
As it so happened, we just published a slightly heretical paper on Hawking radiation, actually confirming that it will exist, but we're also claiming that potentially everything will make Hawking radiation, not just black holes. So you would make Hawking radiation as well and disappear in 10 to the 90 years, which is maybe a sad story to hear. But the black hole itself, M87, will take 10 to the 97 years to radiate away. And so the level of energy that radiates is so small that you cannot even conceive of a detector to measure this. So how you would need to find it is really small. I mean, probably, really micro, but you cannot create them micrometric black holes. So we need to find a way to, this is a crucial question. Finding Hawking radiation, experimentally verifying it, some effects in this direction, because that's where new physics is. And, and black holes, obviously, where you have the strongest effects. So, some analogs first, some particle physics experiment that, combine gravity and quantum effects. I think that's what we need to do in the future to understand that better. And of course, seeing whether that shadow really is, right now within 10%, is it within 1% or 0.1%? Because, there are different theories now, and you could always have alternatives.
Thank you so much. It was very exciting to see the images and everything. But one thing which really struck me was a tiny detail that you mentioned, that you repeated things twice to confirm, at least twice, and then you check different methods. And this is not done very often in the field.
Yes.
And we are all scientists here. And I wonder, I have the same experiences in my field. And I wonder if you could elaborate of why do you think that is? Why do we not value this repetition enough?
Because if you're second, right, so everybody who's second, it gets less attention, obvious, right? And so there actually have been confirmation experiments. There have been 4 other papers who have actually come out with the same image. Nobody cares about them. There is one paper who actually claims, this is completely wrong, which we know is pretty wrong, that paper itself. But that gets much more attention than all the other ones which confirm it. Right? That's a confirmation bias. So it's better to actually build it into the system, because then everybody gets instant recognition. But of course, then you have to trust the collaboration as a whole that that this really is a fair competition between the different groups. But okay, yeah. So that's a fundamental problem. Maybe you should only allow fundamental results to be published only once there are 2 groups actually independently have confirmed it. So you can think of ways to put this into the system.
So this is all very exciting, but I'm afraid we need to move on. Thanks a lot, Fantastic talk. Okay, so oops. Go ahead. Yeah. So can I take this? Yes. Okay. So we move on now. We go back to the Earth. We lost time when going into the cosmos. Now we get back to the Earth and to time and history with the next speaker, Verena Winiwarter. Verena was trained as a chemical engineer and she worked into environmental chemistry labs. After that, she pursued an academic degree in history, and since then, after that, she became the first Austria's full professor in environmental history. And since then, she taught multidisciplinary classes to several audience during the last 25 years. So she's really, her background really spans across science and the humanities. And she's the perfect speaker for the talk, which is entitled Energy Transitions of the Past. Is there something to learn from history? So please, Verena, the floor is yours.
They're done. Thank you very much, and thank you to Academia Europaea for making this possible. I'm really pleased to be invited into the section on the exact sciences, and I can tell you why that is the case. And this is because Johannes Lercher, who's a member of the exact sciences class, I think, as, like me, is the vice chair of the Commission on the Defossilization of the European Energy System of the Austrian Academy of Sciences. And in this commission, we try actually to do interdisciplinary takes on the question of how can we come up with an energy transition, and Paolo also mentioned this in his morning speech. How can we come up with an energy transition so we don't trash the planet while we're getting exciting science results? So now that we have all seen a black hole, the main story about the black hole obviously is that a black hole's mass is so concentrated and big that it sucks in more mass. Now there's a lesson to be learned which has been formulated in ecological economics. It's called stocks create flows. What do I mean by that? Industrial society actually has a lot of stocks, like this building. And if you talk to the facility manager of this building, he will immediately agree with me that you need a pretty large flow of energy and matter just to keep this building at the status quo. And we're talking about stocks creating flows here, which create one of the big lock-ins that we already have created. And as an environmental historian, I'm going to try to talk to you about energy transitions and their history. So, an energy transition is an all-encompassing change in the main energy carrier a society is based on. And if this sounds abstract, I'm going to show you this in a little more detail as we go along. Such a transition, unfortunately, is not just about technology. Because as we have just heard from this fabulous first speaker of this morning, it gets messy as soon as people are involved, right? With their lifestyles, like my data are best. German atomic clocks work better than any other atomic clocks. We've had that, I think. Systems of governance. How can I put up a telescope in Namibia without it being stolen? Power relations in and between nation states or other social entities that come with a change of dominance of sources of energy. So if we go solar, we go to a different geopolitical space than when we have fossil energy. And here, if you stop listening to me now, it's fine. This is the red line here. All prior energy transitions that we have been experiencing as humanity have been energy additions. All prior energy transitions were local or regional, at least for decades before they became globalized. But now what we're thriving at is a global transition away from an energy source. And this has never been attempted before. And we'll see how we do. Now, the one guy whom I owe most in terms of how to explain energy and civilization is Václav Smil, and he published a paper a few years ago where he said, okay, let's have a dozen insights based on performance about energy transitions. And I'm not going to give you a dozen. The first thing that he, looking at empirical data, was that progress of a specific energy transition on a national level has sometimes been pretty fast and sometimes been pretty slow. But all global energy transitions have always been gradual, and they have been pretty prolonged affairs. And our society, and everybody who works in renewables will tell you about the increase of their staff, how much they have built. Super. But we're still an overwhelmingly fossil-fueled civilization. Current fossil fuel dependency is between 83 and 86%, depending on how you calculate it. And what Václav Smil goes on to say is the unfolding energy transition is not just about shifting from one set of primary energies to another. It is stop trashing the earth with greenhouse gases, and that can only be achieved, he says, by decarbonization of the global energy supply. Now here, I have an issue. We are still going to use carbon. So we suggest to call it defossilization. It's weaning society off fossil carbon sources, which is a big difference to renewable carbon sources. And what Václav Smil has detected is that there is very little to no evidence that the global primary energy transition has been accelerating during the recent decades. And carbon intensity, so how much fossil carbon is in commercial energy supplies, remains high. What has been achieved is a shift in energy, in electricity generation. And that is not our main thing. So this has had a small effect on the decarbonization of the overall primary energy supply. Václav Smil is not known as the most optimistic scientist, I have to say. And I'm going to try to give you the final 3 slides, I think, are going to be my optimistic take. So the grand scheme of history has what can be called socio-metabolic regimes. We start as hunter-gatherers and fishers with passive use of solar energy. Then we go to agrarian societies, which we call the Neolithic transition, not a revolution because it took like 10,000 years. It's like Hawking radiation. It goes so slowly that you can't measure it, actually. Agrarian societies have an active solar energy use. They change land cover by planting their stuff, and they actually cause a great deal of deforestation already. So then comes the fossil fuel transition, which is usually called the Industrial Revolution, and it ends up in industrial societies based on fossil fuel use, which actually is so big that it impacts on global biogeochemical cycles. And then we're looking for something which is called the sustainability transition, and we have not very much idea about how a sustainable society really looks like. Now remember that I said stocks create flows. Let's have a look. Since the Industrial Revolutions, humans have extracted 2 times the amount of materials than in the 300,000 years before the Industrial Revolution. And I have just given you the numbers here. Yeah, the hunter-gatherers for 290,000 years have only extracted biomass. The rest is very, very little lithic material. Agriculturalists took 8,250 years to actually produce a little bit of mineral and fossil materials. And in the past 35 years, we have produced all these material stocks from mineral and fossil materials. Some we have heated, but a lot is stocks. This is very likely not sustainable. And if you look at the socio-metabolic profiles of different modes of subsistence, and we are comparing here hunter-gatherers, agrarian and industrial societies, what you can see is that material use per capita has gone up by a factor of, say, 20 from hunter-gatherers to industrial. Population density has gone up by a factor of probably 4,000. Agricultural population, where they had nil, of course, in hunter-gatherers, has dropped to below 10% nowadays, while in agricultural societies it was above 80%. So most of your ancestors, just by for purely statistical reasons, were peasants. Material use density, direct material, has gone up by a factor of, and here the numbers are not particularly great in terms of precision, but let's say they go up like 3 to 4 orders of magnitude. The biomass share of energy drops from above 99% to between 10 and 30%. The share of non-energy use of materials, okay? Hunter-gatherers had a sling to bring their babies and a few stone tools. Whereas now, we have all this stuff. That has gone up. We now use more than 50% of our materials not for energy. And the stocks of artifacts have gone up by like 4 or 5 orders of magnitude. So now we have so much stocks that we somehow have to keep them in working order. And that means we're used to a high energy diet, and that's not gonna feel particularly nice to go on a low energy diet. Do we have to do that? No, I don't think so. Is the transition going to be easy? No, I don't think so. So let me for once show you that I'm actually not a member of the exact science class. And I'll give you the most exact social theorist that I know, Niklas Luhmann. Very much hated by my colleagues from history, and I'm a historian, I still think he has a point. He says hunter-gatherers come in tribal societies, and their differentiation is segmented. They have bands of people all basically organized the same way in segments that sometimes meet and go in for war or for party, but they're all very similar. And the evolution of tribal society is purely demographic. Next in history come empires or feudal societies. And here, the evolution of society is no longer driven by demographics, but by power. And what you differentiate is centers of power and peripheries. And then come the advanced agricultural societies, very important for the story here. Here, inventors come up. In feudal societies, if you were a project maker, you probably had a low status and a low recognition. Now, if you have a great idea, you're a good person. And we stratify, we differentiate in terms of you're part of the nobility, you're part of the clergy, you're a part of the peasantry, you're a day worker without land. So this is a stratified differentiation. And what Luhmann didn't realize that it's all based on the energy you're using. So he calls it modern society, which I call fossil-based society. And here you have a completely different evolution scheme. You evolve by subsystem creation. And nowadays, these subsystems are very, very bad at talking to each other. So politics can try to talk to the scholarly subsystem, but it works in a very haphazard way. And the health system and the economy system and the politics and the sport and the media system all have their own logic. And there's a lot of noise and very little communication out there. And Luhmann calls this functional differentiation, and it actually works brilliantly, because if you sort people by function, they become pretty productive. But it has side effects on how well we work as a society as a whole. Now, the downside of feudal society is that one of the ways to create extra energy is to enslave people, because you don't need to feed them while they're growing up, and you only take those who can work. So you get an energy gain. Advanced agricultural societies do this, but they do it in places where you don't see it, which makes it less politically problematic. They do colonial exploitation. And of course, by now you will know what my next point is. Fossil-based society is based on global resource exploitation. You might want to call it overexploitation, but the point is it's global and it's based on resources. And yes, slavery and post-colonial exploitation still exist, but as part of this global resource exploitation scheme. Why did people do that? Now, this is like Václav Smil wants to put his images. He likes black and white. Okay, now what do we see here? We have a very long history here. It's about 4,000 years. And if we look at this first one, which is 2000 BCE Egypt, what you can see here with the small dots is people as prime movers. People carrying stuff, people hauling stuff, and a very, very small portion of animals, draft animals on top. And if we go to, let's skip Rome and China, but go to Europe in the 1200s, and we've just heard about the Netherlands, the pioneers of windmills. What you can see is that animals, water wheels and turbines, and a little bit of windmills in the 1200s make up approximately 20% of the prime movers, but it's still 80% of people schlepping stuff around, okay? And only by the 1900s in Europe do we have a pretty big change, and that is the steam engine. What you can see here in this dark shade is railways. And then what you can still see here is the addition of steam turbines, but that black thing here, it's not a black hole, is internal combustion engines, which is cars and trucks. And you can see that this transition from people to internal combustion engines made us do away with a lot of the slavery and drudgery of people, and instead using fossil energy. But let me go back one step now, because what all these energy transition people don't like to do is they don't like to figure in how we feed people, because it's not technical energy. It's so goddamn soft stuff. But if you want to feed 8 billion people with approximately, what is it? I don't know, 8,000 kilojoules per day, that actually adds up. So let's go back and see how agrarian societies fed their people, okay? And I'm going to give you the data my friend Fridolin Krausmann has made from an Austrian village, and we're going to compare 1830 to 1995. And I can assure you from 1995 to today, not much has changed there. Okay, the net grain yield per hectare goes up. Now, this is the story that my agrarian colleagues love to tell. Grain yield goes up from approximately 500 kilograms per hectare to above 3,500. Super efficiency gain. Great. Even the conversion efficiency of livestock goes up. Would you believe it? While livestock had a conversion efficiency from less than 4% in the 1830s, it goes up to approximately 10%. Now, 75% of all the nitrogen that you feed a cow is still coming out on the backside. But that's pretty good. We've doubled the efficiency. Also, we can now support way more people per area. We could support approximately 0.7 per hectare, and we're now at 4. Boy, have we become efficient. And if you look at the supportable population per labor input, it's even better. For one agricultural laborer, you can now feed 30 people, whereas you could feed like 2.5 people in 1830. But at what cost? On the left side of this image, I give you the input-output relations of this same village, but the image on the right side with the red line around it shows you the output per unit of energy input. And we didn't get much per hectare, but what we got was 5:1 ratio of energy. We actually were harvesting solar energy with a little bit, with a tiny input of people and animals. We actually made an active harvest of solar energy. And this has gone down to 1. So to give you this in a picture, what we can see here is the fossil fuel powered transformation of agriculture from solar energy harvest, of energy provisioning, to mere conversion. We now have an ROI, an energy return upon input, that has gone from 1 to 5 to 1 to 1. Any reason for that? Fossil fuel-based fertilizer. By 1980, approximately, the anthropogenic total nitrogen fixation, which is fertilizer plus legume crops, had actually exceeded the natural ecosystemic nitrogen fixation. What's the name of the game here? The Haber-Bosch process. And if you look at data by Jan Willem Erisman and others, what you can show is that approximately like 3.5 billion people could exist based on yields achieved without artificial fertilizer, but the rest basically is only getting enough food because we have artificial fertilizer. Approximately 50% of world population rely on the Haber-Bosch process derived food via fertilizer. Now, this is an extremely energy costly process. Yeah? I think it's what 300 degrees, 400 bars, nitrogen really doesn't want to become ammonia. That's not what nitrogen is really desiring. So you better have put a lot of pressure and heat, and pressure and heat is costly. The Haber-Bosch process alone uses up approximately 1% of the world's greenhouse gas budget. Yeah? 1% of global greenhouse gas emissions comes from one process, and that is fertilizer production. Austria, pardon me, I'm Austrian. Austrian greenhouse gas production is 0.14% on the global scale, and 1% is approximately the entire emissions of Australia or Pakistan. So this is here you can see the food system as a source of inertia to the global energy transition. And those of you who were at Steve Evans' talk to high school students yesterday have seen that he is working on a fantastic idea of getting excess wind energy that can be used because there's too much wind directly via an electrochemical process into the creation of ammonia from nitrogen in the air. Now that would be a game changer. And he's going to go to Nebraska to figure out why people don't adopt that. As I said, as soon as you get people in technology, it's getting messy. Now this is the food story. So my point here is no energy transition without a food transition, without a land use transition. Let's get back to the big picture. What I'm showing you here is data over 3,000 years, and you can see how the black age of coal and the age of hydrocarbons on the very, very end of this. And I want to remind you that previous energy regimes were not just super nice. I'm not a romantic. The age of charcoal, increasing charcoal production for increased pig iron production, actually deforested England so much that they had to come up with another solution. But before we get there, I want to show you the global picture again. Kenneth Pomeranz has argued that there is a great divergence between China, Europe, and the world economy. Now, this is my only slide that has dollars, constant dollars on it. And it goes from, it is about the GDP differences. And what you can see here between 1500 and 1950, the GDP stayed pretty much the same in India and in China, whereas in Japan, in Spain, in Italy, in Germany, in France, it all rose in this particular time, 1850, when coal was added into the energy mix. So our GDP is based on fossil fuels. But I didn't speak about the black line yet, right? Because what works even better is the combination of colonies and coal. So it is also about environmental injustice, about taking someone's resources and feeding them into your own industrial system. Okay, I promised Britain. Here we go. England was completely deforested. Buying a tree was expensive. So biomass dropped from the 1700s, it's basically out of the energy mix, and coal moved up. And the first 200 years of the increase of coal is what Smil calls a slow energy transition. But then, as you can see, from 1950 to 2000, actually with finding North Sea gas, and coal miner strikes and Thatcher governments and all kinds of things happening, coal drops down pretty fast. Okay, so what you can see here is we're starting in the 1800s with a biomass-based society. And we're ending up in 2000 to 2015 with a society based on what I have here in different shades of brown. this is fossil fuel. And if you look at how long this transition actually took, what you have is energy inertia. And if you look at the first 50 years until coal hasn't yet reached 20%. Now this tells you something about how long energy transitions take. Like 2-3 generations, easily. Yeah? And even the transition away from coal to crude oil on the global basis took quite a while, which you can see in my second window. And what you also can see is that renewables are dancing up here. Still, I said, we're still a fossil fuel-based society. What we also have is a new problem, and that is we are working ourselves down the energy density ladder. Now, you remember the first talk? What was it? 10 buckets of water in one black hole? That's a very good energy density, I would say. Yeah? But what we are now doing, we're no longer using the energy dense, or we don't want to, or we cannot use the energy dense energy carriers. We have to go either to liquid biofuels, which are approximately as bad as you can do, or we're going to low density, power density with solar water heaters and stuff like that. Is that a problem? Not necessarily, but you need to figure it in, and actually things will become a lot easier if we stop wasting so much energy. Because at the moment our energy system is incredibly wasteful. Why are we not doing it? Well, because there's stranded costs. And what you can see here is that we have created a whole lot of stuff that has a very good technical lifetime, and it actually creates a financial barrier to getting out of this technology. And coal power is huge, is cheap, and sits there, and it's not easily done away with. But what I want to highlight here is again my ICEs, the internal combustion engines for passenger vehicles, because they have the largest techno-institutional effects, creating a lot of jobs and making lifestyles possible, where people live like 40 kilometers away from their job, and happily do so. And in the morning, they get into their SUV and drive. Yeah? So what's the problem about these energy transition? It's called institutional lock-in, technological lock-in, and behavioral lock-in. And that's a fantastic paper by Karen Seto, done in the annual review of environmental resources. This is, just check that out. And remember what I said at the beginning, we're now, for the first time ever, trying to take out something from the energy mix. Never attempted before. So, what does that mean? Okay, from her long list of things, 1, technological and infrastructural lock-in comes because we have long lead times, large investments, sunken costs, and long-lived effects. Institutions lock in because they are designed to stabilize. You're at a university which is designed to last. You don't want this to change, but then if you want an institution to change quickly, you get a problem. And you can also have lock-in through social structure, and it can be very difficult to interrupt habits. And this is why a lot of what is talked about when we talk about energy transition actually is eating diet candy. Which, of course, is not making Garfield any slimmer. But he thinks so. So is there hope? Into the 1950s, most goods that were transported on water over long distances were transported in bags and stuff. A major cost, and this meant that 60 to 75% of the cost of a ship transport was portside costs. And up comes Malcolm McLean, and he designs the ocean freight container. One of the most important inventions of all times, says Malcolm McLean. And that actually combines with something completely unrelated, and that is the ship diesel engine, which can be scaled up to enormous amounts of energy. And that means you have a steep rise in global seaborne trade, and that again means hope. Energy transitions to sustainability are significant change in socio-technical systems involving multiple actors, long-term processes, goal-oriented, but agreement on goal does not imply agreement on path. They entail conflicts, struggle, and incumbent actors with vested interests. They are non-linear, uncertain, and open-ended. And what the heck does that have to do with the shipping container and the diesel engine? Well, this is an emergent phenomenon, something you could not predict from either the shipping container or the diesel engine, and that might actually make, if we have more emergent phenomena, which nobody can predict, you could also make a few of these steps easier than anticipated. Thank you.
So thank you, Verena, for this very extremely interesting lecture. So we have time for a couple of questions. Yes, one there. And then we'll go there.
Thank you, Louise. I'm an ecologist. I really worry about what comes in the last, let's say, 10, 15 years, where we see a tremendous increase of wood being used, forests being cut down to produce electricity, which of course we all know that the production of carbon by burning wood is incredible, and we don't have that time. So what do you think of that period? I mean, especially in England, but in the Netherlands, and it's industrialized, shipfuls of tons of forests from Canada, from America, from the Baltic, from Europe. It's really a stupid idea, with the idea that if we plant forests and sustainably use them, then that's okay. So that's such a wrong thing to think. So what, I didn't see that in your figures, but it is a enormous trajectory that's ongoing. So what's your opinion about that?
Yeah. Thank you very much. I mean, of course, when you have like 30 minutes, you can't put everything in. But what I would say is the following. I think what has changed in the past 5 years or so is that the question, do we want to use places like the Amazon forest as a carbon sink? Or do you want to use them for forest products? Has actually gained political traction. And carbon sink policies, because we need to achieve net zero, right? When net zero came up in the IPCC, it became clear that you could put wetlands or mature forests, but not managed plantations, but real woodland forests into the equation. And if we can make it happen that this becomes financially interesting for the countries in which these carbon sinks are situated, we might be on a better trajectory than without that. But I agree, deforestation is a huge and not much recognized problem. Thank you.
We have time for a very last quick question and answer.
Hi, thank you very much for that. It was a brilliant talk. I'm a clinical neurophysiologist by trade, so I'm not really connected to this at all. But what was really striking, and it kept coming back in my mind, especially that picture about Garfield as well, where do you know of anyone who has done a comparison of sort of human metabolism over aging, and does that sort of equate to some of the things that you show over historically as the human species has evolved? Because energy consumption is one of the key things that a human body does, and it changes over time, and the body composition changes, the metabolism changes. It seems like there might be some lessons to be learned in the sort of aging process and society aging and energy consumption.
Yeah, thank you very much. The people at the Stockholm Resilience Center a few years ago did a very nice paper on their planetary boundaries of the food system. And what I remember is that from 1960s to like the 2000s, the amount of undernourished people had decreased, whereas the amount of obese people had increased. Now, those are both killers. But what the global food system had not achieved was to do away with malnutrition. And I'm fighting against thinking of food just in kilojoules. You have to think about food content. And what it also had not achieved, interestingly, is security of that food supply. So it not be poisoned, it not be tainted with fungi or something like that. So I think we still have a lot of work to do on the food system, but I think that given the demographic transition, caloric requirement will decline a little bit. There won't be much change on the global scale.
Thanks a lot, Verena, once again. I know there are other questions from the audience, but we really need to move on.
I'm here for the day.
Yes, exactly. So we continue talking about energy, as a matter of fact, and we are now going to listen to possible new forms of energies which may provide a supply for the next decades or, who knows, maybe centuries. So our next speaker is Professor Ambrogio Fasoli. Professor Fasoli is the project manager of Eurofusion, which is the European Consortium for Fusion Energy. Had these studies in Milan, moved to Lausanne, from there to UK, then he became professor to MIT in the US, and then back to Lausanne, where he's now director of the Plasma Center. So please, Ambrogio, the floor is yours.
Thank you very much. It's a great honor to be speaking in front of the Academia and to become part of it. It's also a fantastic opportunity to speak after those two incredible talks that we just heard, because they frame our work to some extent scientifically, and at the same time, the very last talk frames it in a sense of motivation. I hope I will give you an optimistic vision for what we can do in the future. And I also, as the chair said at the beginning, bring you down to earth compared to the first talk. But I'm not going to come on my own down to earth. I'm going to come with a star in my hand, just like Prometheus here, which we can see with your telescope in New York City. I hope also not to have the same bad end that Prometheus had with this idea of bringing down the fire of the gods to earth. So this is a very modest statement, but I think it's something that we need to really work on all together. This is not working. Okay. Just a word of introduction to the very concept. Many of you know this, but I'd just like to remind you why we can actually gain energy by moving along the axis of all the possible atomic numbers for the elements, looking at the nucleus. You can gain energy in two ways. You can gain energy by splitting very large nuclei that are already ready to be split because they are unstable, like uranium, for example. You can split them with a little kick given by the neutron, and then if you split them, you go down from the right to the left in this curve, which tells you how much mass, that is how much energy you have per component of the nucleus. In other words, we become more stable, and you become more and more stable going right to left. If you go to the center, you get to the most stable nucleus, which is iron. Trouble is that when you do that, you of course create other nuclei that are still quite big, and also still a bit unstable, so they are radioactive. You don't know what to do with them, and they emit neutrons without the little kicks that can further break other nuclei. So you can also, in principle, lose control of the neutrons. So that's nuclear fission. Now we can do the other way around, exactly the opposite, and still go down in the curve. So we have to go left to right. And in fact, you see the curve is not symmetric. So if you go left to right, from the very small nuclei to the slightly less light, you gain even more energy because you go down steeper. And that's nuclear fusion, the opposite of fission. Why do you gain energy? It's another way of speaking of relativity. You gain energy because the end products, if you add them up, have lost a little bit of weight. They have a little bit less mass, and that mass defect has to be multiplied by a huge number, which is the speed of light squared, and that is energy. So you gain a lot of energy going down in that way, even more than you gain when you go down in the fission way. Now you have to put together two light nuclei. For example, hydrogen, super light, the lightest of all, or isotopes of hydrogen, which are a little bit less difficult to put together. Why is it actually difficult to put them together? It is difficult because the nuclei are charged positively, so they repel each other. And so you need a hell of a lot of energy to smash them together so that they come close enough so that the nuclear force can take over and give rise to the nuclear reactions. And when you speak of energy for smashing, disordered energy, you speak of high temperature. And high temperature means not tens of degrees, not hundreds of degrees, means millions of degrees, hundreds of millions of degrees. We need 100 million degrees for those reactions to happen in a good number. What kind of matter can you have at 100 million degrees? Well, not the matter that we know of normally. We cannot have the solid state because it melts. You cannot have the liquid state because it evaporates. You cannot even have the vapor or gas state because it will be completely dissociated. All the atoms, all the molecules are dissociated. You only have a soup of particles, positive the nuclei and negative the electrons, that are going around in all directions, very disordered. This soup of particles is called a plasma. And I'm very happy to hear that you're one of the few astrophysicists who actually uses the term plasma because that's what it is. And I'm very grateful for that. Now it sounds very exotic on Earth because we're not made of plasma. We don't want to be ionized. We don't want to have atoms or molecules that are split. But most of the universe we know of, and I think it's about 5% of the universe that we know of, the rest we don't have an idea what it is, dark matter, dark energy. But most of the universe that we know of is made of plasma. So actually it's exotic on Earth, but it's what surrounds us. And we have understood that this way of putting the particles together, very light nuclei, and form slightly less light nuclei, for example, helium, is exactly the way the universe is powered. It's how the stars work, how the sun, our own star, works. We understood that about 110 years ago, I believe, not that long ago. And since the time we understood that, we tried to think that maybe we can do it on Earth. Now, the stars, we have seen fantastic images of how big they are, how many we have. The stars have an easy job because they have a lot of time, first of all. The nuclear fusion reactions that happen in the core of the sun generate energy. That's how we get solar energy, of course. But it takes hundreds of thousands of years for that energy to get even to the surface of the sun. We don't have that time, so we need to be much more efficient. Neither do we have the mass of the stars that holds together this soup, this plasma that wants to go everywhere because it's full of gradients, it's full of instability, it's full of turbulence. So we need to be much smarter than the sun itself. And smarter means that you have to have a specific reaction which is much more easy to obtain. So high, to speak in physics terms, it has higher cross-section. And that is the deuterium-tritium reaction, which is made by the two isotopes of hydrogen, one with one neutron, one with two. And that is the easiest of all. So some of our colleagues in private companies and so on, they say, well, we do other reactions because they have other advantages. Well, let's start with the easiest of all, because that's difficult enough. We need about 100 million degrees to make that happen. Where's the fuel from? The fuel is very easy in principle, at least, because deuterium, there's plenty of it. and that's around the oceans and in the water and so on. One molecule out of about 7,000 in the ocean water is made of deuterium instead of hydrogen. So there's plenty of it. What about the other isotopes that we need? Tritium? Well, there's not much because it's short-lived, it's radioactive. But we can produce it in situ, and that's a great thing because the reaction produces a neutron, a lot of energy, and that neutron has two jobs. One is to give us energy to make electricity, and the second job is to make the fuel itself because it can react with lithium, which we can put around our little star and produce, again, tritium, which we inject back in. So tritium doesn't come from outside, neither goes outside. It's produced and used in situ. And the other byproduct of fusion, besides the neutron, is what? Is helium. That's a gas with which we inflate balloons for children. So it's really not a problem at all for the environment. In fact, it would be nice to produce a lot of it because it's a scarce resource. We don't produce that much. And that helium nucleus, alpha particle, is kept inside because it gives its energy back to the plasma. Now, this is a reaction that's extremely interesting because it produces a lot of energy, like all fusion reactions. And to give you a number, we have seen numbers in the previous great talk. When we burn fossil fuels, which we just heard we do for more than 80% of our needs around the world, we use fuels that have energy density, which is number of megajoule per kilograms of about 25, 30, or no, a few tens, let's say 30. When we do this reaction, we go from 30 to 350 millions. In fission would be about 80 millions. So this is much more than fission. So 30, 350 millions, which means that, let's say for a town of 1 million people, you need a big stadium full of coal for 1 year of energy, which means about 15,000 trains that carry coal there. For that same amount of people, 1 million, for the same amount of time, 1 year, you can put the fusion fuel that you need for that in a little trailer behind your bicycle. You don't even need a car for that because we're talking about 100 kilos. So that's a game changer. And the fuel that you need to get from the outside world is deuterium and lithium. They are in the seawater, both, and at the moment lithium is mostly mined. It's well distributed. You don't need the Marines Corps to go and get it. Much, much better distributed than the fossil fuel. That's another big advantage. Of course, we don't burn anything. We don't produce CO2. We are not subject to intermittency because we can turn it on and off when we need. So this is a base load electricity supply. Neither, in the approach that I will discuss, are we related to weapons proliferation, which is another issue. And we don't produce long-lived radioactive wastes. So the potential of fusion is gigantic. So it is difficult because 150 million degrees, not so difficult, not so easy to achieve. But also, you need to achieve that temperature, and you need to achieve that temperature for enough of this plasma. You need this critical mass for energy to come out more than you put in. And you have to hold that plasma there and its own energy for long enough for it to give us energy back in a positive sense. So enough density, enough what we call confinement time, so enough time to hold it together at enough temperature. So as I say, the stars have an easy job. They have the mass, and gravitationally they hold it together. Okay. Another easy thing they have is that nobody outside, they don't have a bottle that contains them. We do have to have a bottle on Earth, right? And that bottle is difficult. I'll tell you about it. A second possibility is to make a mini implosion or mini explosion. In other words, a little pill, like the pupil of our eye, that you have to compress super high, so you have a huge density, and in that way, you don't need a huge time to hold it together because there's enough density. And that's a so-called inertial fusion approach, which is interesting, which provides results, scientific results for a reactor, for powering our towns. For me, it's a bit even more difficult than the other approach that I'll tell you about. But it's of course interesting for some people, not for me, because it simulates thermonuclear explosions. And that's also one of the reasons we don't pursue that so much in Europe at all. We pursued the magnetic confinement because this plasma is based on charged particles. And charged particles are subject to electromagnetic forces, and therefore they can be trapped in a cage that's made of magnetic fields. In that case, we can have a long time for the energy to be confined, and so we can afford having a good plasma producing energy with relatively small density, 100 times less dense than the air we breathe. So very little plasma in there. And because the energy density is so gigantic, very little plasma in there can give a lot of power. And it's not for decades, it's actually for the rest of history of humankind, most likely, because we're talking about hundreds of thousands of years, even millions of years of fuel. Now, as I said, it's not easy to make this plasma stay where we want it to stay. So this cage made of magnetic fields has to be pretty clever. I won't go into any details. There are two ways of making. One is to make it helical. In fact, in both cases, you need to make it helical, but you can make it helical because you drive a current itself in the plasma. And that's a concept that was invented in Russia in the late 50s, I believe, called the tokamak. So far, by far, the best concept for holding the plasma together. Or you can make it helical because you make your own coils helical, which has some advantage because you don't rely on the current in the plasma, but it's also complicated to build. And so far, the performance is not that of the tokamak yet. But these are the two approaches that I think are the most promising. And why is, in terms of basic physics, is a very challenging system, like the ones that we have seen in astrophysics, but to some extent even more. It's a very intrinsically nonlinear system because the plasma particles are sources of electromagnetic fields and at the same time are victims of electromagnetic fields, just like the plasma in the universe, of course. And so all the things are self-consistently coupled. We need to deal with scales that go from very, very small length and very short times to very large length and very large times because the single particles move over very, very short time scales and over small orbits, but you need to confine them in a cathedral-like object. And so you have to cover many scales, which means it's very difficult to simulate with a computer, and even nowadays. The other thing, you have to have a geometry that is an engineering detected geometry, so you cannot just have a linear, nice plasma like you would like to simulate in a computer. You need to make an object that produces energy and can even sell energy eventually. And so it's intrinsically complex. The plasma is a complex system. It's a self-organized system which develops turbulence of all kinds, with flows of all kinds, some of them favorable to us because some of them are those flows like the ones you have at the entrance of a supermarket. You know, you have a big flow to isolate the inside to the outside so that the heating is saved a little bit. Those flows actually set up in a plasma naturally, like they set up also on Jupiter. In our tokamaks, they set up, and we need to understand how and why. And so we need to simulate and reproduce those situations in which they do set up, because if we have a curtain, like at the supermarket entrance, which isolates the plasma very well, it means we can confine it for long, and the energy can be confined for long. That's great. That's what we want. And we are now understanding how to do it. We are now using those self-organized elements and flows to our advantage. But we also have a multi-physics and multidisciplinary system to deal with. Not only do we have to observe it like you do in astrophysics, but we have to make it and control it, because that's our object that will produce electricity and money for those that will invest in a power plant, not me. The core of the plasma is completely ionized, so it's like an object that has no atomic species. But then you go to the edge, and we do have an edge as opposed to a star that doesn't have a wall. We have a wall that surrounds the plasma, and then there is transition between the hottest place of the universe, or one of the hottest places in the universe, to a very cold spot, because we need superconducting coils to make the magnetic field, so almost zero, absolute zero. And that transition is difficult to deal with because you have gradients, you have, you know, in physics, thermodynamic potentials and driving instabilities. We have, in general, systems that are not at thermodynamic equilibrium, so not so easy to predict and to control, but we're making huge progress. And all of those blocks that I have mentioned are understood to most extent, to a large extent, but they have to be put together. Integration is a key element, because this machine is something that has to work. It's not something you can observe once every 6 months. It has to work 24 hours a day, 27 days a week, 365 days a year, and for decades, because the investment is large. You need that to work. And this is a simulation with actual orbits of the particles inside the tokamak, so they are very well behaved. They are there, and they work. But this, in fact, is our own tokamak in Lausanne, where we confine the plasma. We heat it about 25 times a day to temperatures that are much higher than the core of the sun. And we control it there in real time, sometimes even using artificial intelligence algorithm to keep it where we want. And then all of the blocks, the core, the edge, the injection of particles that heat it, the extraction of particles, they have to work at the same time. And that's not trivial in physics, and also it's not trivial in technology, because it's a system of systems. And so you may say, okay, but this is far away in the future, it's very difficult, almost impossible, it's a dream. It's happening. It's happening at the very moment. This is an example of a plasma. It's not spectacular to you, maybe, but it's spectacular to us. Why? Because this is the plasma that has produced the most energy in the world, in the history of humankind, on Earth at least. We produced, by the common experiment in England, common European experiment, 69 megajoule of energy using 0.2 milligrams of DT of fuel. If you had used fossil fuels, which we don't want to use, of course, you would have needed kilos. 0.2 milligrams versus kilos. This has happened. So this curve is saying that we can do it. And we've done it with the proper material around the world. We've done it following the predictions of the numerical simulations, which in some areas of science is not a nice thing to just confirm the predictions. But in our area of science, it is, because we want to control it and make it work. That's not the last step. There are a couple of steps. One is to show that we can get, of course, more energy out that we put in. And that's going to be demonstrated by ITER, which is a world experiment. It's an international treaty with 7 partners, a major one being Europe. It's actually in Europe, it's in the south of France. This is the image of ITER. You can hardly see the person there because the volume of the plasma of the star is about 1,000 cubic meters. So it's like a villa. And this is the first time that we will demonstrate that we can do it, because we get 10 times more power out than we inject. ITER is actually being completed now. It's being assembled in a very difficult project. I would say it's the most ambitious project we ever made in the history of mankind, at least for peaceful purposes. And the way it was set up, it was to avoid colonization. I really liked your graph there. I will use it if you don't mind. Because the way it was set up is that ITER parties bring component in kind, and don't just give the money to a group of people, enclosed in Los Alamos in the desert or something. But they bring component in. That means that all of the parties develop their own know-how to build their own fusion reactor in the future. Nobody will colonize anybody for fusion in the future. Now, it's not the most efficient way to do it, so we have some delays, but it's happening. So we have a few years delays. It's being put together, and it will demonstrate that we can get energy out. But we need to demonstrate that we can do it, in a commercial way, so that we can actually produce energy at a cost that's compatible with the market. Otherwise nobody will actually buy. And this is what we call in Europe the demo project, for demonstration. We need to demonstrate the performance, the integration, and availability of all the key technologies, so that we can commercialize fusion power using our own fuel producing cycle, and producing to demonstrate that we can do it hundreds of megawatt electric, which is a power plant that powers a small town or something for a few hours at any given time for the pulse, but many, many pulses. This is already being designed by us in Europe. Us meaning the European consortium that I have the honor of leading, which is called Eurofusion. It's 29 countries, so larger than the European Union. Couple of hundred institutions and 1,000 students and about 5,000 staff. So we work all together, no barriers, no secrets, because there's no any weapon-related interest here. You can notice there's Ukraine there as well. We work in ITER with Russia and China and so on. We know what needs to be solved as the final gaps that we have on the way. We know what they are, so we have to demonstrate that we can solve them. One is to actually demonstrate that this tritium can can be recovered in an efficient way and be injected. So the reaction is very easy to write on the board. It's a bit more difficult to actually do it in those conditions. We need the materials that can withstand those heat fluxes, gigantic heat fluxes. We need to control the plasma, how it's extracted when it's useless, because it has given its energy, but we need to avoid all the instabilities that are beautiful in the stars and all the elements in the universe, but in our little star, they had to be avoided, because if they eject particles and energy to the walls are not going to be happy. We need to make sure that the safety and waste are what we believe they are, much, much better than fission, and we need to make all of that compatible with remote maintenance, because everything has to be robotically controlled, robotically operated. So we need to strengthen R&D where we need to find the gaps. We need to also increase our efforts in simulations of plasma engineering, and the digitalization that happens in the rest of the world is now being absorbed by us. As I said before, we have demonstrated actually ourselves in Lausanne that you can control this little star by an artificial intelligence approach, because a star is very difficult to be controlled because it has a lot of instabilities of different kinds. And so you can teach your system over many, many occurrences of those instabilities how to actually prevent them from being, either from happening or from being damaging to you. We have to reduce the licensing difficulties, because we have to consider we are nuclear, but not as nuclear as fission plants, so we need to make those procedures much more agile, so bureaucracy is not making it easy for us. And we, in Europe, have a very big advantage. We can collaborate at the same time with US and China, and both parts are interesting. In US, because there's a very, very large private effort, not so much public, but private. In China, because there's a very strong public and private effort together. And in Europe, we have, I think, the largest and most comprehensive fusion program. We can actually take advantage of both sides. But we take advantage of both sides by also not understanding what ITER has been doing and why it's been developed the way it was, parallelizing activities by taking some risk, which we haven't done so far in the past enough, but knowing the urgency of things, we have to take some risks. We cannot just avoid risk, otherwise we will have fusion in 200 years, and we need fusion as soon as possible, as we just heard. And the last point is that we need to do it, we academic, we in a research institution or in university, we need to do it hand in hand with the private industry, because now it's becoming a commercial development. We cannot build a demo reactor, we cannot build a commercial power plant, we have to do it with industry. But we cannot, on the other hand, say everything is understood, go and build it, like others are saying. That's also a big mistake, because that's never going to happen. We also need to look at what the reactor will look like, but also I'd like to finish with this fact that we need all hands on deck. We need all competencies. We need to put together plasma physics for the core of the star with engineering of all different kinds, and we need facilities for that, and that's what we have in Europe and with our collaborators, to go to ITER to demonstrate the feasibility of science and technology for fusion on Earth, and to demonstrate the commercial feasibility. Thank you very much for your attention.
Thanks a lot for this, I would say, promising and hoping talk that we have heard. And I particularly liked your reference to open activities, open science that you are developing around that. I really think science can only be open. And that's especially true when we are talking about something which is going to define the progress of the humankind. And we want that progress to be shared by all, not just by some fortunate countries, or even worse, by some control groups. So that was particularly nice for me to hear. And I think we can take a few minutes out of the coffee break for questions. Yes, Éva? And then here.
Yeah, we heard in the previous talk that we have to have the nitrogen fertilizers by the Haber-Bosch procedure, which requires a lot of fossil fuels. What is the reality to change this one and using this new energy source, for example, for producing nitrogen fertilizers?
Well, the way nuclear fusion works is simply to produce heat, which then can be transformed into electricity, and plenty of it. And so then you can do what you want in the way the other plants operate. But of course, it doesn't produce waste, doesn't produce CO2. It's not subject to intermittency, so there's a huge advantages there. But basically, it's a source of electricity.
Yeah, but you have also the heat, and this is what you need.
You have what?
What you need, this is the heat. But I don't know how it can be transferred for this procedure. But anyway, so there is some hope that one way it can be changed from the fossil fuels to this.
I think on the long term, I have no doubt the fusion will be part of the portfolio, together with renewables. My personal opinion is that the transition, which everybody talks about, everybody says fusion will be late. Everything is late for the transition. But my hope is that there will be a contribution from nuclear, from maybe other source, more conventional nuclear for the next couple of decades, and then fusion will come in strong, and that will really revolutionize the base load electricity supply. So I give it a couple of decades.
So here, yep.
Now, in recent years, I've been talking to some people who've been actually even starting startups which use different approaches, lasers and other things. They're getting some funding. There's a little bit of a discussion about it. What's your view on it? And also happening in Europe, I see.
Absolutely. The startups around the world have raised more than 8 billion euros or dollars, which is a very good indication of the interest there is in fusion. Some startups and some of these entities which can no longer call startups have very interesting approaches. Some violate the fundamental laws of physics, like second law of thermodynamics, and I'm a bit less interested in those. But those that do not violate physics, they are pushing for some different approaches. The real serious ones, they're not pushing for that different approaches. And the recent developments, I've been at the G7 meeting a couple of weeks ago, and then the ITER meeting, is to work together. They bring fresh views in terms of processes and in terms of maybe taking more risks, but the physics is the same eventually, and the engineering issues are the same. And the engineering issue that some of the startups have forgotten so far, and now are realizing, is integration. ITER is made of 10 million components. They have to work together with a reliability of 99.9999999%, because then otherwise you exponentiate, the unavailability. So they are realizing this. We have to work together. Those that are serious are also open, like we are. Those that are not serious are also closed, and I don't want to have anything to do with those. But the real serious ones, they are open and they bring ideas. We can have higher magnetic fields. This is, for example, a very interesting startup of MIT called Commonwealth Fusion Systems, which is the largest of all. They are going to higher magnetic fields, but with the same concept of tokamak, with the very same problems to solve together, and we are collaborating, yeah. So the idea is to work hand in hand with those, not to be in competition.
We have a last question there? Yeah, that will be the last.
Thank you very much. That's really fantastic talk. To me, it just came across as the reaction itself is quite unstable, and there were points where you were saying, oh, we have to contain it, the conditions are not right. So in your view, what is the biggest risk related to this kind of energy production?
The biggest risk is to not make enough money, and that for me is not a very interesting, a very severe risk, if you like. Because if we lose control, well, a machine will not create any safety issue to people. If we lose control, it will shut down for a little while, and then the investor will say, damn, that day we haven't made money. But we cannot exponentiate the heat. The Fukushima kind of accident is intrinsically impossible in fusion. It's also intrinsically impossible to generate weapons-related material. And even those two things on their own, they're very important. If we have a Boeing 747 coming on our tokamak, okay, it would be bad, but for everybody. But we don't even need to evacuate the populations around, because there's so little fuel, such a small amount of fuel at any given time inside, that there is no problem. Why is there such a little amount of fuel? Because the fuel energy density is so gigantic that we need at any given time grams. So it's nothing. So basically, inside the tokamak, one of the most difficult things to do is to make vacuum. Because it has to be incredibly good vacuum. So it's really small amounts.
Well,
so in terms of safety, in terms of proliferation, I have no issues. I mean, the issue is that it is difficult and expensive to invest at the beginning. But those are issues that I think humankind will surmount.
That's all very comforting to hear. And once again,
thank you very much.
So with this, we conclude the first morning session. I think we have had a very exciting series of extremely relevant lectures by top qualified people that we heard from, and that was, well, wonderful. The program will continue here in this room at 11:30, and now please enjoy the coffee break.
For me, it's a pleasure to introduce next lecture that will be, for the first time, a lecture on arts and science. So, many times people in science, we think that we try to understand the world and that science is the only approach for it. But today we are going to listen how people in arts also try to understand. People in arts also do research. People in arts also try to use creativity to make things work and to understand how things work. So there are many things that we should learn. Maybe the first one is that the part of emotion that sometimes we do not take enough into account to handle our way of doing things. And today we have a person that is going to talk to us on arts and science, that is Mónica Bello. Mónica is Spanish originally. She has been art. She's a little bit of everything, artist, but mainly curator. And for many years, she has been appointed as director of a big center that is called Arts at CERN. So she works in Geneva at the CERN premises. Last year, they inaugurated a new center for arts at CERN, and this is the work of Mónica that is no doubt the headlines of arts and science. Thank you very much for being here, Mónica.
Hello. It's a real honor to be here. And I thank Jama and the team and the organizers, the president of the conference, and to host me, because it's quite a challenge to be here, but in a very positive way. Expressing what I've been doing for the last almost 10 years at CERN in the laboratory, European Laboratory for Particle Physics in Geneva, which has taken me, almost 10 years. And I'm an art historian, I'm a curator, but today I think I'm much more articulated in particle physics, which is very strange for an art historian, believe me. So when I listen to you before your talks, I find myself understanding and thinking, well, plasma is a familiar concept for me. It has been, and you know, and I listen to my colleagues and think of accelerator plasma, and I take artists to talk with them about this. Cosmology is easy. You can imagine the universe as an object, but still, for an art historian like me or the artist that we support, thinking of the challenges in cosmology today and the experimentation and the everything you need to do to make things work is really complex, but very, very exciting. So this is what we do at CERN and what we've been doing since 2012. So today I'm going to give you a bit of context of this moment in art and humanities in which we are, which is a thrilling moment of questioning and queries regarding knowledge and our place in this universe that we are trying to describe. And also what is happening in this other side, which is never the other side of culture, because I think science is an integral part of culture. And culture is calling out, is reaching out to scientists, researchers, and laboratories to integrate this view. And over the past, let's say 3 decades, but I know it's much more than that. But just to confine this in the last 30 years, the intersection of science and art has been notorious, and it has become increasingly prominent in everything we do in culture. If you go to a museum, an institution, an event of any kind where audiences of, broad audiences, professional people, experts of any kind, you hear nature being described with the language of science. And not only through the language, but also the 21st century visual culture is populated by these images that you often use or think of or create in your laboratories. And leading cultural institutions are really trying to, catch up with science and understand what is happening. Even something really interesting took place 3-4 years ago when the MoMA, the Museum of Modern Art in New York, bought from Peter Gallison and the event Telescope Horizon the image of the black hole. So this is now part of the collection of the MoMA, which is, you see, is a grain in a big scenario, and that is really telling us science goes so fast, and we are still here waiting to understand what nature, life, the body, the universe, everything is about. So the place where I work, let's see. Let's see if, okay, here. I think, yeah. You need to change the screen. Is the place where I work, CERN, has been going on for the last 70 years. So at this time, this image, I love digging in the archive of the laboratory and finding images of this kind, because today these lands where crops are being were grown, and this place is now a highly technological and scientific environment where we work. And CERN has, this year is the 70th anniversary of CERN, and from an aerial view, we already guessed the accelerators being built in the 60s and 70s, and later in the 2000s, we move into much more open laboratory with cultural engagement, but from a visitor point of view. So the visitors are today invited to come to CERN and to know about particle physics and what scientists do. But it was not until recently when the Science Gateway, the CERN Science Gateway, or Portal de la Science, I prefer it in French, was open last year in October 2023, that CERN gave this, move into this quantum leap and open a cultural, scientific, and technological center for visitors to know more and to engage with science. And in one of the tunnels here, we even have an art exhibition in which every 3 years we support artists to create new works but only after conversations and spending time in the laboratory. Conversations mostly with theoretical physicists, but also heavily influenced the artists and the artworks by the experimentation and the challenges of technology. When you think of something that has to become an object, something that can be manipulated and can be tangible and can help us to imagine. And this is what is happening today, but it took many years to get here. I'm going to tell you how we did it. So CERN has been for many years an iconic place, but you might remember when the Large Hadron Collider was announced, this big accelerator, the coldest place on Earth, the hottest place on Earth, experiment underground that was going to create micro black holes, etc., and all the conspiracies around it. You might remember this moment in which society said, hey, what's happening? And even later, which was even more spectacular, when the Higgs boson was discovered thanks to the data gathered by this experiment and other, this is the CMS and the ATLAS experiment, together managed to reach this data where the Higgs boson was appearing. There was this blip, and suddenly it was there, and the Large Hadron Collider was created to reach this point. So around that time, our Director General was Rolf Hoyer, and some of you might know Rolf. And Rolf was really interested, and is still now, in opening the society, in saying, hey, this is what we do. It's never too complex to explain. It's possible. We can access to complex ideas, but there might be challenges, but we can make subatomic scale closer to our heart and think about it like something that belongs to us. And as part of this thinking, and well, Rolf Hoyer is much more articulated and charismatic than me when he explains this. As part of his thinking was to create an arts program, because it was not out of the blue. We already had many artists knocking in the laboratory's door saying, hey, what are you doing? I want to know, I want to be part of this, I want to, go around, take pictures, ask people, invent these possible stories, narratives, but also intervene in the laboratories. So Rolf really believed in the power of humanities, culture, and art in connection with science. And there was something very pragmatic about it. Art conveys the complex reality of science in a much more accessible way. It's not going to be clear, it's not going to be didactic, but it's going to be much more expressive. And it's going to provide hints in a very diverse, with a huge variety of perspectives, but it's going to provoke and inspire others to think about science. So since then, since 2011, 2012, when the artists started to come to CERN as part of a large cultural policy of the laboratory, we set up some tools, a methodology, to do this in a articulated manner. So not just little things, but something that was producing experiences out of a cultural framework. And our core activities today still are artistic residencies. And during these artistic residencies, which are fully funded, the artist is paid and is not a visitor. He has the very similar status as the staff. So it's a user, it's a project, it comes as a project for a project. During this time, the artists are supported to go and understand what the experiments, the computing, the IT, the data people, the detector developers, the accelerator physicists, cosmologists, theory, any of the research groups are doing to pursue a better understanding of the universe. And we do that by creating expertise as well. So I'm a clear example of this. I'm an art historian, I'm a curator, but for many years I've worked in science. Before going to CERN, I was very involved in life sciences. So I was really interested in this part of culture. And when I applied for the job, a new door opened for me. And this is the experience we give to this artist. So for the since 2012, we've been doing this. And what is really interesting is that every experience of the art at CERN is different. But there is a sedimentation. There is a cumulative process in which art has become more, expert on particle physics, which, as you know, is not the easiest science to describe or to talk about. I mean, you don't go for dinner and talk about neutrons or, or the beams in the Large Hadron Collider. So in this image that you see here, we have Daniel Figueroa, a cosmologist who was at CERN at the moment and now is in the Universidad de Valencia in Spain, with a couple, semiconductor, they call like this by chance, by coincidence, and they were in residency with us in 2017. When they were with us, it was really interesting, and I always relate to their expertise and the way they act and create an accumulative knowledge for them later to produce new artworks. So I'm going to show you one of the works that we produce by them. It's called The View from Nowhere. I'm going to just play 4 minutes. The View from Nowhere is around 20 minutes long. It's, in 2017, they began to film in the Large Magnet Facility, mostly, where they test magnets and they ensemble the magnets at CERN. And while they were doing this, they created, or they did interviews with theoretical physicists to understand how they developed their work, in which way, and what was the core, the key aspects of it. And what you will see is the image, the visual culture of CERN, the Large Magnet Facility, and the activity that is taking place there, while you listen to 2 people talking about their work. So just, I think it's a good way to introduce you to something tangible that happens during the time at the laboratory, and I will just leave it there. The View from Nowhere.
There is a human viewpoint, because we are a few billion individuals sitting on some rock, going around some nondescript star in a nondescript galaxy. You know, every once in a while you think, holy fuck, you know, there's 10 to the 11 stars in our galaxy and presumably even more planets, and there's 10 to the 11 galaxies. So, you know, what else is happening out there that we can't yet see? There certainly is a particularity to the way we do our science, which is enforced by the resources that we have available, how much sunlight falls on the Earth and how big the Earth is.
Oof. Well, I mean, it's daydreaming with a lot of mathematics. It's like the process of creation. I mean, you try to create something new. You do some doodling, you play here, you play there, you do a little like computation here, a little computation there, listen to talks, read papers. I mean, it's like artists get inspiration. It's hard to tell where it comes from. You have to think in a creative way, but with rigor at some point. You have to have some logical rigor. Sometimes you only have, for example, the satisfaction of solving a riddle. So that's when, for example, string theory and some of these other theories, all of a sudden you got more or less the right answer, or an answer that looks right. And that's very intriguing. There, of course, these are things which are conceptual developments and conceptual breakthroughs. And you hope that these conceptual breakthroughs eventually will lead to something that could be tested in nature. The first thing that you do is try to get a mathematical model in your head, something you can work with. I don't need to do it in paper. So you can think in this kind of a mixture between what you experience and this very abstract mathematical world. It's the place where I can pose the questions. I don't think in terms of words. So these are non-verbal images or non-visual images. So you look, for example, at quantum mechanics, say. You can look at experiments, you can get some pictures, but most of the pictures and the metaphors are wrong or are misleading. That's where the mathematics comes very, very handy. So then I already have in my mind a collection of formulas for general relativity. So you have to, rewire your brain a little bit.
Science doesn't change reality. What I happen to think is a particularly powerful and effective way of interpreting reality, so that you can actually do something with whatever understanding you have. What we're trying to do is to assemble all the constraints coming from all sorts of different experiments within a specific theoretical framework.
In this film, artists decided to play the role of ethnographers, and this is why the movie is called The View from Nowhere. It has been in different exhibitions worldwide, since then, and we are very proud of having this artwork as the first art commission. Since then, we've been producing every year from 1 to 3 artworks out of the residencies, because this sedimentation that I was mentioning before produce this sort of experiences that give fruit to many intriguing approaches. And this is just one of them. So here you probably recognize your work and the work of many colleagues in laboratories anywhere in the world. But there are other artists that take a much more speculative approach, or an approach that is not so tangible on the idea of making science. So this is an approach that, interestingly enough, we saw in 1972 when the artist James Lee Byers came to CERN. Well, I didn't see it, I was not there yet. But for us, we mark James Lee Byers as the first artist in residency. And I think it's a really interesting case, and we had to go through the archives of CERN to find out what happened there. So James Lee Byers came in a way that we cannot understand yet, because he probably knew a scientist who said, yes, come to spend time with us. And he came in 1972 and 1973 for several weeks. But in the second year, I found some records in a website in the archive of Berkeley, where a friend recorded conversations with James Lee Byers in which the artist said that he spent most of the time with John Bell. John Bell was at the time developing his, looking for the challenge to describe the Bell's theorem, which he formulated in 1964. And at the time he was at CERN, and he was working to understand the experimental results. And it was already a really interesting and vibrant moment in which there was this, departure from theory into experimentation in quantum physics. Even I thought of the coincidence of James Lee Byers being there, because in 1972, John Clauser performed the first experimental test of Bell's theorem, leading to the first observation of quantum entanglement. And Bell himself concluded that these experiments said, open quote, now appears that non-locality is deeply rooted in quantum mechanics itself and will persist in any finalization. John Bell was engaged in these deliberations while James Lee Byers, an artist who was dealing with the intangible and the performatic aspects of art, was spending time there. And James Lee Byers says that he never understood, like scientists like John Bell invite him to his lab when he was, using these golden shoes, Panama hat, and always wearing white. So he is the only one until today, the only artist that was shown and was featured in the front page of the Sun Courier, which is very funny, because even this didn't happen after. The 70s were a crazy, wild moment, definitely. But in the little photo caption, they said, this summer we had a really interesting visitor, James Lee Byers. So I leave it here because I think it's a really interesting connection of John Bell and James Lee Byers and the moment in which physics was dramatically changing. And so our program is very much about bringing artists and scientists together. The dialogue, the conversations, and the trust that something is going to happen after that is the essential and goal for us, the main goal. So assessing knowledge, which is from a different discipline, like particle physics, being part of the laboratory environment and the community, and having the possibility to look at things from a different lens, from the artistic lens in this case, is an extraordinary thing that we can do today. In this picture, we have Armin Linke with Giuseppe and Maria Fidecaro, who sadly passed, both of them, this year. But Maria and Giuseppe were very charismatic, very important figures in some community. They spent their whole life in the laboratory. And Maria Fidecaro helped Armin Linke to understand how physics was performed when there was no accelerators. And Armin Linke, at the time, he is a photographer and an artist, was preparing an exhibition for the MAST in Bologna and the Centre Pompidou in Paris called Image Capital. And he was very interested in understanding nuclear emulsion experiments. Maria Fidecaro started her career in the Institute of Physics in Rome in 1947. And she went in the cable car to the Monte Cervino to place devices to connect, to detect cosmic rays at an altitude of 3,500 meters. So this allowed them to study the nuclear force. So out of these conversations, Armin Linke and Maria Fidecaro and Giuseppe as well, Armin understood how important the image creation, the image production was to connect with invisible forces in our universe. And these are two images that were brought to the Centre Pompidou last year. Armin has a theory influenced by the work of Peter Gallison, a philosopher and a historian of science from Harvard, and Bruno Latour in Paris, where experimental physics is part of a material culture in which experiments, people, artifacts, theories, and all the knowledge is a composition, is coordinated together to create what he calls trading zones. And we support him to develop this exhibition. I think I'm not controlling my time, so I need to wrap up here. But perhaps just to say something else. What is interesting is that, and what I'm being observing, is that science has this very important role in our culture today. We all know this. But as in the previous presentations, I heard our colleagues saying that it's very important to work together. We are in an important moment, and we have different paths to take in many different areas of human realm. And so art and science together bring not personal expressions, emotions. Art is not anymore about that. It's about understanding the commitment and the compromises that we are taking towards knowledge, our planet, other species. And I think art is very urgent that artists, philosophers, writers, filmmakers are welcome in laboratories to be with us, to create meaning and to have significant conversations that lead to a much more open and democratic society. And I'll leave it here, and I have several slides left, but for next time. Thank you very much.
Thank you. Thank you very much, Monica. So we go on with the next talk.
Okay.
Eva.
Thank you very much. I am Éva Kondorosi, Chair of Life Sciences, and this is my honor and great pleasure to introduce you the next speaker, Professor Emmanuelle Charpentier, who is Nobel laureate. She received the Nobel Prize in 2020 together with Jennifer Doudna for decoding the CRISPR-Cas9 genome editing technology. She received many very prestigious, numerous scientific prizes before the Nobel Prize and after the Nobel Prize. And I must tell that she's also a new member of Academia Europaea. She belongs to the biochemistry and molecular biology section. Emmanuelle received her education in France at the University of Pierre and Marie Curie and also at the Pasteur Institute. She had also some visiting fellowships at different places in Europe as well as in the US. Currently, she is the founding, managing and scientific director of the Max Planck Institute for Science of Pathogens and honorary professor at the Humboldt University. Even in Germany, she had many additional positions, and she is also honorary professor at the Humboldt University. She was a head at the Max Planck Institute and also at the Helmholtz Center. Yesterday, at the Life Science event, Francis Morica gave an excellent presentation on the evolution of the CRISP system and the decoding of the function, how the CRISP-Cas9 system works, really revolutionized the life sciences. Not only the medical field, but also the agricultural field. So today, Emmanuelle will talk about the CRISPR-Cas9 system, microbiology as a motor for innovation in medicine and agriculture. So please come and join in welcoming Emmanuelle on the stage.
Thank you very much for the very kind introduction. It's a great pleasure for me to be here today with you. It's also a great honor to join the list of prestigious members of the Academia Europaea. So I'm very happy, and I would like to thank those members who nominated me. So again, thank you very much. For those who have had the privilege to listen to the talk of Francis Morica yesterday, he may have explained you that CRISPR, for those who wonder what it means a clustered regulatory interspaced palindromic repeats, which doesn't tell you much. Now, maybe at the beginning, people would have said, oh, CRISPR, you know, whom do we have to blame for CRISPR? So it's Francis Morica. But ultimately, I think everyone loves the name CRISPR. You know, it's like so crispy, so some have difficulties to pronounce it. But I guess it's a very nice name because it's a little bit special, and so people at the end of the day, you know, remember it. So thank you, Francis, for the name. So I will focus my talk more on how we came to this. How we came in my group to work on CRISPR. And also how we developed our research into I would like to thank the people who contributed to the work. It's always important, specifically because you see a name, Krzysztof Szelinski, and you see Christophe written in a Polish manner. It's because Christophe has been really one of the key students for the development of the project, and Krzysztof Szelinski is actually Polish. And he was my student when I was based in Vienna, and when I was based in Umeå, he was still doing his experiments at the University of Vienna in Austria. He's still in Vienna, now he has moved on to industry. And there is also Elica Delcheva, so she was also a key player, a master student coming from Bulgaria. Other names, Umiusi. And another name, Martin Jinek, in the lab of Jennifer Dardna, coming from Czech Republic. And he has been also a key player in the story. So it has involved young scientists from Eastern Europe. And I like to mention this because without the young scientists, obviously we would not be here today. I mean, at some point we were a young scientist doing our experiments ourselves. But I would not be, here today if it was not that I had to also rely on young scientists, also young scientists who will trust me, because at some point no one, was believing maybe what I wanted to do with CRISPR, because it was a new field with regard to really looking at the mechanisms at the molecular level back in the mid-2000s, so about 15 years ago. And more. There is also a German team that has been involved in the collaboration. So this is a group of Jörg Vogel for Cynthia Sharma. So there was a collaboration with a group in Germany and a group in the US. And also later on, actually, we had a collaboration with bioinformaticians in Bethesda in the US. And for sure, some institutions have been also supporting my research over the years. The work started at the University of Vienna, the Max F. Perez laboratories. And then I moved to Umeå University to join a new initiative, the Laboratory for Molecular Infection Medicine Sweden, MIMS, that was part of the European Molecular Biology Laboratory at EMBL, or let's say an outstation. And then now I'm in Germany, and for sure a lot of funding agencies having been evolved to fund the work. Having said this, we all rely on funding agencies and taxpayer money. It's always important to mention it. We all struggle to get fundings, and we, not me any longer being at Max Planck, this is a privilege, but we all hope that, the public funding agencies will continue to fund research for the next generation of scientists who really need the funding, but we have for sure a responsibility with regard to using also public money, that is at the end of the day taxpayer money. So I think we most likely have a responsibility also towards simplifying certain systems in academia, to not spend unnecessary funding for wrong purposes, but use the funding really for the sake of good science. Yeah, this is my next slide. So this is about the CRISPR-Cas9 technology. I also look at my watch to make sure that I'm keeping the time. So the CRISPR-Cas9 technology, it's also called the gene scissors. And here you see the scissors represented, and here the scissors are actually an enzyme that is a protein with enzymatic property that has the capability to cleave the DNA in a precise manner, therefore reproduced on this image as scissors. And the technology is, in a way, those scissors that will be programmed to be able to recognize a certain sequence on the DNA and to be able to cleave it. And this programmation works with a molecule of RNA that is in nature, two RNA of molecules forming a duplex, so CRISPR RNA and tracer RNA. And this RNA of molecule works in a way as a GPS system, allowing the enzyme to recognize exactly where to go and to do the work. So this is very simplified the way I say it, but upon cleaving of the DNA, what will happen is that then specifically in cells of higher organisms, then machinery that are repair machineries will be triggered to take into account this cleavage of the DNA, and depending on how the tool is designed, the repair machineries will enter into play to lead ultimately to a modification of the DNA. And the DNA can be then modified in multiple ways. One can introduce a piece of DNA or a new gene at a certain site on the genome, on the DNA. One can delete a piece of DNA or a gene from the genome. One can mutate at the DNA at a specific location. One can correct a mutation. So in a way, one can do a lot of what we call bricolage on the DNA, a lot of gene editing and engineering in a precise manner. So it's a little bit more complex than what I said. You have also some rules defining how to use a tool. But in a nutshell, it has revolutionized life sciences because it really offered, compared to all the tools that were existing prior to CRISPR-Cas9, a simplicity of use, a versatility, and an efficiency, which allowed actually the technology, indeed, to be used very fast by the scientific community. So after we published the second article in Science in 2012 with the group of Jennifer Doudna in the US, a large number of scientists really literally jumped on the technology. They could foresee really a great advantage of the technology, hoping it will work. And in a very short time, which is very short in biology because one needs to do the experiments, write the article, submit the article that has to be reviewed and then published. But from June 2012, when we offered, when we explained what would be the guidelines to use the technology, to January 2013, February, already a lot of scientists could show that the technology was working in human cells, was working in organoids. The research on organoids, it's very important for clinical research and development to develop new cures for diseases. And that the technology will be also very useful to genetics in model organisms such as mice, flies, fishes, which are really model organisms that are used in the lab, also yeast, to understand the mechanisms of life in higher organisms and plants. So this was very exciting. And since actually 2013, since we have seen the publications of a number of articles showing the power of the technology has really evolved tremendously in multiple versions. Also combining the CRISPR technologies with other genetic technologies that were known prior to CRISPR, and also new tricks that were produced that were developed since the past 12 years. And it is really amazing how we see the technology developing always more and more, and the number of articles published weekly with regard to new aspects of the development of the technologies and new applications of the technology. So it has really revolutionized the field of life sciences. There are a large number of applications, and I will come to the fundamental research after I explain a few aspects of the applications. So, yes. So, CRISPR-Cas has been very useful over the past 12 years to really understand better the mechanisms of life. As a matter of fact, CRISPR would not have been as important in terms of implication if it had not come at the right time. There is a reason why the CRISPR-Cas mechanism was discovered rather late, in the sense that a lot of genetic tools originate from mechanisms, understanding mechanisms in microbes. And this relates to research that was done in the 60s, 70s, 80s, where actually one could have predicted that CRISPR, which is originally a defense system in bacteria, would have been discovered at the time, but there are reasons why it was not discovered at the time. But ultimately, it would have been discovered at this time. It would not have had, I believe, the implication it has had, because it needed also the development of other technologies. So the life science field has tremendously evolved over the past 20 years. It became a lot technological. I mean, I'm always careful when I'm excited about technologies, because I always try to explain to the young generation that the technologies come from basic science, and the most important is basic science. That's why I always come back to how we came to this technology. But having said this, the scientists can now, specifically the scientists in biology, can really answer questions which were not possible to answer 20, 30 years ago, thanks to all the technologies that have been developing. And so a lab now looks totally differently than a lab 30 years ago. Yet, and this is what the scientists do in my lab, we still do very conventional experiments with conventional methods, protocols, technologies, because when you go very deeply in the basic science, trying to understand very deeply at the molecular level the mechanisms of life, you also always come back to do the old good way of science, which is also critical to maintain, and also with this expertise critical to maintain. Having said this, I take the opportunity to say that as a microbiologist and bacteriologist, I'm very sad, because I see a generation of bacteriologists, microbiologists retiring and even not being with us any longer. And with it, really a field of expertise disappearing. And because also life sciences and our world of publications in life sciences, which one could criticize heavily, tend to always go for, fashionable, research, leaves behind research such as microbiology. We saw it also with SARS-CoV-2, and where we were wondering who are the virologists, where are they? And maybe the virologists tend to publish in low impact factor journals like the bacteriologists, so they are not supported enough, yet their science is so critical, so valuable, even more valuable in nowadays when we know that infectious diseases will be the, even more and more problematic in the future. And that it's very important to really support a variety of research, and microbiology and also fundamental biology using really, the good old way of doing experiments. The reason why I say this as well is because CRISPR, it's maybe for those who attended the talk of Moreka yesterday, could acknowledge to which extent CRISPR is really about evolution. But that's the point. When you have a very powerful gene editing technology, you can then, and this is what CRISPR did, you have a technology that allows to really understand the functions of genes in multiple organisms. So it comes from evolution, and it provides the technologies that allows to understand better the evolution of the world by being able to work and do genetics in cells and organisms where prior to CRISPR it was difficult to really do the genetics in those cells and organisms. And that this is by understanding the variety of our world and also creating an expertise of biologists who increase their expertise in the different, in the variety of our world, that we can also, I believe, be more ready to cope with the challenges in the future that are always sometimes coming from directions we did not always anticipated. And that's why I think it's important that the world of life sciences as well recognizes the importance of really evaluating the global expertise and not to focus only on fashionable projects for the young generation, a lot of young scientists are hyper excited about microbiology as a matter of fact. So the technology has been very powerful to boost really the understanding of functions of genes and understanding the mechanisms of life. According to other types of technologies, as I said, that have developed along the way, that the ability to really sequence deeply the genomes very fast. We know now that we can even have our own genome sequenced and read extremely fast. All the imaging of cells and organisms and all the technologies around microscopy, electron microscopy, have also benefited the field of CRISPR. Also, all the technologies that are delivery technologies. So when you have a genetic tool, you need to introduce it into the cell, and you have different ways to introduce the tool into the cell, and you have a lot of efforts that have been done into the delivery technologies, and so on and so forth. So a lot of robotics as well, allowing the technology to have been developed extremely fast also with regard to research and development that are done partly in the academic field, in industries, in biotechs, also in clinical labs, trying to understand better the mechanisms of diseases. So CRISPR allows to also genetically reproduce in the lab models of diseases that are more relevant to the clinical setting and that are important to understand the mechanisms of diseases, and also have the right models that allow to test new drugs in development. You have all the aspect of screenings for new genes, new targets for therapeutics. So you have a lot of aspects in research and development that are benefiting a lot of the CRISPR-Cas technology. In medicine, in addition to profit from the indirect use of CRISPR-Cas to find new targets, to develop better models, and so on and so forth, and understand better the mechanisms of diseases, you have also the direct application of CRISPR-Cas as a gene editing tool combined with cell therapy, allowing to really cure diseases, specifically genetic diseases, and this has been shown and the technology has been approved a year ago for the treatment of sickle cell disease, beta thalassemia, that are blood genetic disorders. Actually, one specific cure that can treat two diseases that this cure has been developed, by the way, by one biotech company that I have co-founded back in 2013, CRISPR Therapeutics, which later on joined forces with Vertex Pharmaceuticals to really bring this treatment on the market. So here again, it's the involvement, a lot of involvement of researchers in biotech companies, interactions with pharmaceutical industries, with clinicians, with also researchers in the academic field, to really come very fast to a treatment that really saves lives, because those diseases are very painful, and they have also a reduction in the lifespan, and also require in general a treatment that where the patient has to spend maybe up to a third of his time at the hospital, going through monthly transfusions that are very painful. And here it's a one-time treatment whereby the cells of the patient are modified to be cured and to be reimplanted back into the patient. And the first clinical trials that were taking place in 2018, so 6 years ago, showed that the patients can live a normal life. So, and it's quite predominant genetic disorders, beta thalassemia and sickle cell disease. So these are examples of how the technology can be used to treat diseases. It's also used in the context of cancer immunotherapy, whereby certain types of cancer can be cured by genetically manipulating the T cell of a patient to recognize the sick cancer cells and kill them. So in the field of cancer immunotherapy, there is a need of editing the cells. So there is a need of a genetic tool. There were other tools that were used prior to CRISPR-Cas, but CRISPR is also very much used. There is also the very exciting applications of trying to develop the technology for really, here what I explained, it's ex vivo more cell therapy, in the sense that it's really the cells of a patient that are modified and reinfused back into the patient. And for sure the challenges that are to develop the technology for a more in vivo approach, whereby the technology has then to be extremely precise if the technology is introduced directly into the patient, and with for sure all the development around the delivery and a precise delivery, and also safe delivery, and that is in current development to have certain applications in this direction. And in the field of agriculture, this is another example. The technology is very useful in the sense that it allows to produce plant crops in a precise and safe way, maybe different from what the technologies were used prior to CRISPR to engineer so-called genetically modified organisms or plants or GMOs. Here the technology relies on the modification of the genomes without introducing a foreign marker or a foreign piece of DNA. So one can do clean genetics and very precise. One can reproduce a mutation that maybe would occur in nature. So it's less about the technology than the plant that we want to produce, knowing that now we have a safe technology that allows us to produce genetically modified plant crops. So it's more, the reasoning is a bit different. The technology is safe, and it's more about what we want to produce that is maybe, the ethical, let's say, the regulations. It's more about, the nature of the plant to be produced. So, for sure, you have CRISPR engineered plants which have been commercialized. In Europe, it's a debate. In 2018, the European Court of Justice decided that CRISPR-modified plant will undergo the same regulations than genetically modified plants, which for sure did not sadden a lot the scientific community, which was not happy with this statement. And there was a revision that was supposed to take place. And actually it was expected that this year there will be a change, but obviously it has been postponed as far as I'm concerned. But there is really the wish of the scientific community, but also the developers, and also for the sake of economy, that there is an understanding that it's not about not having regulations, but it's about having regulations adapted to this new technology and give the chance also to the European market to be in the, to have a place in the commercial development of CRISPR engineered plants, and not leave it to other countries like the US or countries in Asia. So very fast, just that you leave with, I have until 20, so I have 13 minutes, just that you leave with an understanding, because I think it's an important technology, and independent of CRISPR, we hope as microbiologists that the research on bacteria and viruses will lead to even more genetic technologies in the future. So maybe there will be some other technologies that will be greater than CRISPR, or that will make CRISPR greater. But with regard to the where in the history where this technology can be placed. So the world of fundamental genetics started in the 19th century with Darwin on the origin of species. For sure, these are just selected milestones. Gregor Mendel on the laws of inheritance. Then the DNA was isolated in 1871. 1944, it was shown that the DNA was a carrier of genetic information, actually in a bacterium called Streptococcus pneumoniae. 1953, the double helix of DNA, the structure of the double helix of DNA was determined, and the genetic code was deciphered in 1966. So it's quite, some years in between the important milestones. Now you have extremely important milestones in the field of life sciences, maybe happening every week. In the 70s, end 60s, beginning 70s, this was really the start of doing a lot of research in the field of bacteriology and virology that led to the identification of a large number of proteins, enzymes, with properties that could be used for recombinant DNA technology. So the possibility, and that led to the possibility of cloning the DNA, of sequencing the DNA, of amplifying the DNA, and also on doing genetics, so really transforming, recombining the DNA. So the gene targeting, so precise gene targeting, came in the 90s, and with specifically some enzymes originating from higher organisms that one could understand could be used in gene targeting, and also some systems existing in bacteria that would allow to be used to knock out genes in mice. But there are two families of nucleases that were of interest, zinc finger nucleases and talon nucleases, that were actually artificial nucleases that were engineered based on known properties of existing nucleases. And they were engineered to do exactly what CRISPR-Cas is doing, so to be able to modify the DNA very precisely, except that for this technology, the programmability of the technology, so knowing exactly where to cleave, this programmability was contained into the nuclease itself. So one had always to engineer a new nuclease for a new type of modification. And this was cumbersome and not always working maybe as versatilely as CRISPR. And so that's why when CRISPR came in 2012, this was actually 10, 15 years, and actually quite a few years after Talon, but maybe 10, 15, 20 years after zinc finger. And so the scientific community was not all using these zinc finger talon nucleases. They were starting to use these nucleases, but when CRISPR came, a number of people switched to CRISPR, even though those technologies, talon and zinc finger, can still be useful. And coming back to the CRISPR very briefly, for us it started, for me in my lab, in my interest to work on a pathogen that is called Streptococcus pyogenes, also group A Streptococcus, so it's a human pathogen that can cause a wide range of diseases in humans. A lot of us had pharyngitis caused by group A Streptococcus. Here you see the bacteria colored in red for the purpose of the picture, invading epithelial cells, lung epithelial cells that are colored in green. And in my lab, we have always been interested, since I started my lab in 2002 on this pathogen, in understanding different mechanisms that allow to, focusing on the regulation of gene expression, understanding mechanisms that allow the bacteria to cause diseases in humans, to adapt to the human environment, to survive in the human environment and cause diseases. And so we focused on different types of molecular mechanisms, and specifically small RNA molecules. So RNA, you may have come across of the RNA vaccine, right, for SARS-CoV-2. So RNA is in, in the textbook, but now the textbooks have evolved to include the regulatory RNA. But the first understanding of RNA molecules was about messenger RNA being the transition between the DNA and the protein. So the DNA is transcribed into a messenger RNA translated into proteins. And for the translational of proteins, you have two other types of RNAs that are coming into play, the ribosomal RNA and the transfer RNAs. In the 80s, actually, and thanks to research done in bacteria, and trying to understand how small DNA molecules called plasmids replicates, there was this notion of RNA molecules that can have regulatory functions and interfere with the messenger RNA or the proteins to change the expression of the DNA. So a lot of research has been done on these so-called regulatory RNAs that have different names, whether one works on prokaryotes, so bacteria and viruses, or archaea, and eukaryotic organisms, so more higher organisms. But when we started to work on regulatory RNAs, there was certainly a link that was not done, and that was the possible link between an RNA molecule and the DNA. And this is what really CRISPR brought. So for us, at the beginning of 2000s, we were interested in understanding regulatory RNAs in the bacterium, so we used bioinformatic tools to try to find putative small RNAs, and we came across a number of small RNAs which we could show were well expressed in the cells. This is what you can see on the right. And we were focused on the tracer RNA because it was produced in 3 species and well expressed, and we figured out that this molecule was actually expressed from a piece of DNA that was shown to be located next to a gene that was annotated already at the time in 2006-2007 as a CRISPR-associated protein. And this is how we came to the CRISPR system. And so the CRISPR system, it's a system that allows bacteria to defend themselves against invading mobile genetic elements. So, for example, Streptococcus pyogenes can be infected by external mobile genetic elements such as viruses. So the viruses will infect the bacterium, will inject its own DNA into the bacterial cell, and you have different mechanisms of replication occurring, and the virus is produced inside the bacterial cell and can either escape to kill the cells, or depending on the viruses, can also inject its own DNA, integrate its own DNA into the DNA of the bacterium, and then bring some interesting genes that are important for the bacterium to cause severe diseases. CRISPR-Cas is one of the defense systems existing in bacteria. Bacteria, like us, we have different defense systems. Bacteria as well, viruses as well, by the way. And CRISPR-Cas is an adaptive immune system. It requires first recognition of the virus to establish a certain machinery in place to then be able to recognize the virus upon a second infection. So there is first an adaptation phase, and then a second phase whereby the bacterium can kill the virus. So I'm not going to enter into the mechanisms, but just to tell you that for us, we started focusing really on this so-called tracer RNA molecule, this RNA molecule, which we found was located next to a series of genes encoding the CRISPR systems. You have a large history of CRISPR, and I'm sure that you heard this yesterday. A lot of biologists have been involved. What was interesting in this field is that they were really pioneers of the field, including Morica, so really coming to the understanding of the identification of what is CRISPR, what role it can have into the bacterial cell, to then, after bringing other types of biologists, also phage biologists, RNA biologists, structural biologists, who focus then more on the molecular mechanism. And for us, we had the chance to work on Streptococcus pyogenes. That was harboring a specific system. CRISPR-Cas has evolved into multiple systems in bacteria and archaea that work in a way along the same lines, but using really different mechanisms. And each mechanism is a potential for also a new technology, or has allowed to learn a lot about the evolution of this system and learn a lot about proteins interacting with RNA and DNA. But in a nutshell, we had to use a very precise genetics. I've been always a bacterial geneticist, and I've always been a bit obsessed in developing genetic tools. I also worked in mice, and I knew that this was needed for the field of mice, but at the time we had also developed a very precise genetic tool, not based on CRISPR, but to allow us to do precise genetics. And then we included the biochemistry to really go very deeply into the mechanism and go to the hypothesis step by step that in this specific system there is an enzyme called Cas9 that can be guided by a duplex of RNA molecules to recognize the viral DNA and cleave the viral DNA. What happens when you cleave the viral DNA into once the virus has infected the bacteria is that the bacterial cells don't have a very strong repair machinery, and when the viral DNA is cleaved, the viral DNA cannot replicate, the viral particles cannot be reproduced, and this is a dead end for the virus. That's why it's a defense system against virus. And it was to exploiting this mechanism and to say, okay, maybe we can actually program this tool to recognize any sequence of DNA of interest, and this is CRISPR technology. But it has been really using, you know, really, how do you say, precise genetics and biochemistry, quite conventional, and going really step by step, methodologically, with lots of hypotheses, and this technology, which I said, the power of it. What was interesting is that, for me at least, what helped me a lot is that it was originating from having worked on different projects, and I was always reproached in my life to maybe, early life of as a scientist, to maybe do too many things, but at the end of the day, I could anticipate and I could figure out what could be the potential of the technology, what was in need, and also how to approach, because I could actually go back as well to a thematic that was a thematic that I had started when I was a PhD student, that I could not continue because no one was interested in it. But when we came to CRISPR, I used funds that was not to study CRISPR, but that was to study RNA molecules in general, but I use this funding to study CRISPR. Like a lot of early biologists working on CRISPR, we were often using funding that was not specifically to be studying CRISPR, because people would have said it's not fashionable enough, or it's not interesting enough to really do the research. Here is just a representation of how also the CRISPR-Cas9 system has evolved. It's present in more than 400 bacterial species, and it's also largely diverse. So the protein Cas9, for example, has only 1% amino acid identity comparing with other Cas9 proteins, yet it has the same function. The RNAs of the system and the protein of the systems have co-evolved. So they have different sequences, but they have co-evolved. So it's a large co-evolution. And this is by actually understanding the diversity of the CRISPR-Cas9 system and the way it had evolved, that it allowed us to pick on what was conserved, right? And again, my colleagues have I've gone on with studying more CRISPR-Cas systems that have been developed and that have been identified along the way. And again, a large field of researchers. So I was just lucky enough to come at the right time, at the right place, to pick up on the knowledge of other colleagues, specifically for the Cas9 system. My colleagues Sylvain Moineau, Philippe Horvath, and Rodolphe Barangu, and to have the chance to come from another angle and actually a little bit alone in the labs with my students, not knowing the scientists of the CRISPR field, we could decipher this mechanism that led to this very powerful technology. So I thank you for your attention.
this wonderful talk. Maybe one question if somebody has an urgent question. Yes, direct.
To somehow combine the two lectures together, we heard that science inspires artists. Are you finding some inspiration from art in your discoveries?
So I've always been interested in art, right? Having said this, I also did, I studied classical piano and ballet dance. So at least I can say that, you know, when you're a scientist, it's what I tell the young generation, right? It's a lot of repetitive work, which one finds being even an artist. I mean, I guess a painter will always paint every day the same thing. I mean, if you look at how painters paint, they paint, you know, they have this period where they paint the same painting over and over to come to the really the best one of the reproduction of the one single painting. But it's a lot of repetitive works. I mean, in ballet dance, it's always, you know, piano, it's the same. It's a lot of methodology, actually. It's a lot of focus, it's hard work. And it's a lot of also, I think it's the correlation with artists, curiosity, thinking out of the box, creativity. So for me, art has been important because it always allowed me to escape in a way. And I believe that, I mean, it's not, I guess you all know this, that our brain works a little bit, you know, in the background when also we do something else that can be having a walk, letting our mind go without a specific goal, or, you know, how do you say, admiring, you know, buildings or other piece of art, surely. So for me, it has been very important, yeah, and I correlate a lot being a scientist with being an artist. For me, it's, if one wants to be really the real scientist, it's very close from being an artist. This is something also for the young generation, we all have the same trouble to explain them that it's not a job from, you know, 9 to 3, 4 or 5. And it's not about working like crazy, but it's about, you know, creativity, ideas will come at odd times. So, you know, they can also come at, start 11 a.m. their day and leave later. But it's something that we see and that is very, very worrying, I find, you know. That it's like you cannot work from this time. I mean, think that you're going to have your best mind at a regular time, right? So,
I would like to ask something. Don't go away. So, as a plant scientist, I can tell you that we are using your technology every day. And we would not be able to do science without this one. And even last year, we made really a campaign somehow to push this regulation that this should go through. And we had very much hope that this will go through. But then the results were not so positive. So what do you think? What can we do that this should be really accepted? Europe will be so much behind other countries if we cannot do it. So
yes, I mean, what I heard, that was the explanation why actually this year a decision was not made, as actually everyone was expecting that it would be made in around spring. It's because obviously the group of people at the top of, you know, the decisions, let's say, are originating from countries which may not, you know, be so open to, you know, gene technologies, let's put it that way. And it's often what happens, I guess we all know this, right, in a lot of decisions that are taken also at the European level when it involves also politics, is that we all have to cope with also who is leading, you know, the case and having to maybe not be so lucky. I mean, I hope that Europe is going to wake up. I mean, you know, it's a bit dramatic, to be honest. It also goes along the same, you know, wondering that us scientists we have with regard to science and innovation in Europe, when one sees what will happen, I mean, what is happening in the US clearly, I mean, in the, like, for example, CRISPR Therapeutics, the company that I co-founded, unfortunately is based in Boston. This was the only place the investors would agree to have, you know, to give the funding, is to have the place in Boston, right? Why? Because you have the right ecosystem, the right manpower, the right culture, mindset, which we still do not have in Europe. And you know, everything is going very fast, and we are still, you know, lagging behind. If I refer to a report which I did not read, but that was recently written by Mario Draghi, about the fact that there is really a need to really, do something very fast to really make sure that innovations are, you know, a priority for Europe, because we have the manpower, we have highly educated scientists. I mean, we are maybe, I don't know, maybe we have scientists that are better educated than in the US, if I refer to my colleagues. And I think in Asia and China now they really set up wonderful universities, and now they can, you know, how do you say, provide a very good education. But that our young people don't have the mindset of, you know, innovation, because we have not been able to put the right system in place. And the more we wait, and the more Europe puts some, you know, barriers with regard to also regulations and bureaucracy, which is not always, you know, helping us to go ahead. And we have, unfortunately, I mean, we have the minds. We have really the minds. We have the ideas, you know.
Thank you. I will give now the floor.
Is it working? Yes. Dear members of Academia Europaea, dear fellows of the Young Academy of Europe, dear audience, I'm Katalin, the outgoing chair of the Young Academy of Europe, and I really feel honored to speak after Emmanuelle Charpentier and this fantastic lecture, and also after Monica Bello, and just outside of the next point where I'm going to talk about, I would like to highlight that along with the Academia Europaea and also the Academia Juvenum of the Wroclaw University of Science and Technology, we have organized an exhibition of arts and science, which you can watch by the entrance. And we made also a short video of microscopic and artistic images of our fellows that I will put to play maybe during the lunch break. So I'm greatly honored to present today the laudation for the 8th awardee of the André Mischke Young Academy of Europe Prize for Science and Policy, Dr. Jacek Kolanowski. Jacek is a habilitated assistant professor at the Institute of Bioorganic Chemistry of the Polish Academy of Sciences in Poznan, Poland, and the head of the Research Facilities and Innovation Center, Victor Chang Cardiac Research Institute in Sydney, Australia. I am really delighted to present this prize, introduced in 2017 by the Young Academy of Europe and renamed in 2019 to honor our founding chair, the late André Mischke. André, along with other founding members of our bottom-up initiative, made a huge contribution to science policy by building this transnational and interdisciplinary network and community, and by providing a voice for early to mid-career researchers at the European level. As a founding member and previous co-chair of the Hungarian Young Academy, I have personal experience about how tiresome and difficult it is to realize such a vision and to build such a structure from zero. In this respect, I would like to outline that one of the most significant contributions of today's awardee, Jacek Kolanowski, towards science policy at the European level is probably his role in setting up, among other stakeholders, the Young Academy's Science Advice Structure, abbreviated as YASAS, and in getting it officially involved in SAPEL with the help and support of many Academia Europaea and Young Academia of Europe members present here today. Jacek was also involved in the Polish Young Academy and served that community as vice chair and chair altogether for 4 years. He also launched the Young Science Beyond Borders conference, which provided a platform for young researchers from low and middle income countries and scientists at risk to network and access science in the EU. Great enthusiasm and engagement are required to start and run such initiatives, while in several countries, especially in EU 13 countries, such contributions are still not really recognized. In this respect, the Young Academy of Europe's initiative is unique to recognize and reward with this prize early to mid-career researchers who, in addition to having outstanding achievements in science, have also significantly contributed to policy making, science communication, and science for policy, both at the national and European levels. I probably first met Jacek online on one of the annual meetings of the European Network of Young Academies, and then on several other meetings, for example, those of YASAS, which he presided, and on which and webinars we were discussing also how European Young Academies could help Ukrainian researchers after the Russian invasion. So on these meetings, he was a deeply devoted, dedicated, and well-informed, knowledgeable speaker and leader who presented YASAS and the Polish Young Academy also at the meeting of the Visegrad Academies of Sciences. Jacek was involved in the foundation of the Center for Chemical Biology in the Polish Academy of Sciences in Poznan, and is also a great example for the promotion of translational research and for fostering diverse and flexible academic industry collaborations and facilitating research translation. His interdisciplinary research in the field of biological chemistry is focused on the design, synthesis, validation, and use of low molecular weight chemical compounds to visualize and control biochemical parameters in biological models, both for basic and applied research, including precision medicine. Jacek conducted his research in Poland, France, and Australia. He's recently mostly based in Australia, so we are glad that he could join us today in Wroclaw, Poland. And interestingly, he's the second Polish awardee of this prize, with Janusz Buinicki having been awarded in 2019. And he is also the second EU 13 awardee after Gergely Toldi from Hungary, who left Europe to pursue a career in Australia and New Zealand, respectively. It is good to see that Jacek kept his links with his home country and the institution, and I can only express my hope that one day the global brain circulation will bring back both him and Gergely to Europe. Indisputably, Jacek's outstanding scientific and science policy achievements provide an inspiration to young and established scholars alike and make him the ideal recipient for this award. Please join me in welcoming Dr. Jacek Kolanowski in receiving the 2024 André Mischke Young Academy of Europe Prize for Science and Policy. Jacek.
Thank you so much, Katalin, for this very extensive and very humbling introduction. I generally really like speaking, and I'm actually usually monopolizing discussions everywhere, but I have to say, in this setting, I feel very humbled and almost speechless. It's quite uncomfortable to be in front of such a esteemed audience and receive the prize here, but also very rewarding. So I want to thank Katalin, but also all the people who, and systems and institutions which make it possible for me to engage in those activities. And I think without those, you know, none of this would be possible. So I think if you put someone else in my position, they'll probably do the same or better. But if the institutions and the people around me weren't there, then none of this would happen. So thank you to all of you. I would have to speak here for a very long time to thank to everyone who really have a significant contribution to this. So I just want to make it general, and thank you again very much for it. And this award apparently comes with this great opportunity to also talk to you about something. So I wanted to use that time to, especially in the context of what we've heard today also, to talk to you about my passion for methodology and something, and repetition, and something which people don't find extremely exciting usually. But I did, and I still am. And how this one took me to meanders of the research ecosystem, if we can call it that way, through the lab, but also to other places. And especially through the lens of the very subjective lens, I want to underline, of the early and mid-career researchers. So the EMCR here stands for early and mid-career researchers. And we in our network of young academies, we kind of use that abbreviation over and over again, but I just wanted to make sure that we are all aware of what it is. And I don't consider myself early anymore. I think I'm mid somewhere up there or further down, but yeah, but I've been early, and so I will maybe take a few minutes of your time today to go through that, through the subjective story of the whole process. So as I said, I'm really kind of, and always have been quite excited about the tools and the power of tools and methods. But I think we've heard today also from Professor Charpentier, but also others, that, you know, this always goes in conjunction with the understanding of mechanism and the basic research. And they usually fuel each other, right? So you have an understanding, you can design the tool that then allows you to ask questions and respond to the new questions, and so on. Right? And being a chemist by training and synthetic chemist by training, we've been always told by our lecturers, maybe because of, you know, certain discomfort and maybe lack of confidence, that chemistry is the central science, you know. But I actually also want to say that I think it is, in the sense that it actually makes it now possible to answer ask and answer new questions in the wide variety of fields. And with that in mind, you know, we have, and of course I could choose many different, I can see it here, but not here. We could choose many different examples of, to try to demonstrate and say that tools and methods, chemistry tools and methods is really important. But, you know, the one which is very relevant today also because of the Professor Charpentier talk, but also kind of speaking to the minds of people and the general audience, is, you know, Nobel Prizes. And if you look at the Nobel Prizes in chemistry, we can argue about this, if I should put it in one column or another, some of those. But I made a subjective decision there, and I think that majority of the recent Nobel Prizes, but also earlier ones, are actually about the methods, technologies, tools. And I think this really shows you what has a great potential, a great impact, and how important that type of work is. And so, but you know, this approach, methodical approach, and making tools and sticking to the processes and developing processes, have also informed my kind of engagement in other areas, especially in the area of building research infrastructures, but also policy and advisory. And I've just been, that was not my idea, the picture here in the corner, but I've been invited with some of my colleagues to actually contribute to this manuscript that we've just put together, which we call the retrosynthesis mindset, which I think is just an example of showing how putting words to something that we kind of feel and use and understand in the real world, in the sense that there is methodologies, there are processes in science and discovery of tools that we can actually adapt to all of these different areas of work. And if we do that, we can be usually very efficient and often quite effective. And we sometimes don't even think about it consciously, but we still do that. And the retrosynthetic approach for the chemists in the room, you know what that is. So building from the top to bottom, trying to get to the bottom of the building blocks and then put it back together. That's something that I realized after being asked by my friends to contribute to that paper, that actually it is something that's driven what I've been doing quite a lot in these other fields as well. So that's kind of like just a summary broadly of kind of my journey on my trip through the different meanders of research ecosystem. And it all kind of like, of course, is based and started and is continuing in research. But there's also a work in the research infrastructures that is around translation, and then the work on trying to turn that into an impact as well on a broader scale. And so, but this all, again, is underpinned by the approach to methodology, to processes, and by this approach of tool development and application. So I just want to start quickly from this, the academic research part. And you've heard, Katalin has already said you a little bit about my journey, but I started in Poznan and Polish by birth. But I just went through different countries throughout my adventure with science. And you can see here, apart maybe from the first work, which was synthesis and synthesis and synthesis, the rest was all about kind of tools. So developing a small molecule tools, MRI contrast agents mainly, or sensors in a way. We can argue with some of you here whether we should call small molecules as sensors, probes, or other terms, but things that allow you to measure things, to detect things. And so I worked on them during my PhD and also during my postdoc, where I also work on fluorescent probes. And then moving to Poland, I started my research group where we work on fluorescent bioluminescent tools, but also covalent probes and prodrugs. So this is the area which I will maybe tell you a little bit more later on. And I just moved in January to Sydney, where I actually work in the Innovation Center there and the Cardiac Research Institute. But what we do there is actually project agnostic. So we try to facilitate work in a variety of different disciplines through the infrastructure we're building and using there. So when it comes to the work that underpins, or the topic that underpins my work up to date, is really in development of these tools, which I've been repeating myself, telling you about. But it is the two types of tools that I usually talk about also to students is the tools that we use to see things, to visualize things, to measure things, and the tools that we can use to manipulate, control, modify, right? And they actually have often, they can stem from the same mechanisms, but they have to have a very different property, because the ones that are to visualize, they have to be benign to the system we observe, and the ones that we want to control, they can still respond to the same stimuli, but they need to be very effective and usually specific in changing things. So the mechanism that leads to the design of the tools, to understanding how we need to design the tools, is the same, but the design in itself has to be different. And so we really focus on trying to look into something which is really reliable and which allows us to see and modify multiple things at the same time. So these are kind of like the differentiators that we've been building. And to make it, to capture relationships, but also to be more effective and maybe safer in terms of their drug development. So when it comes to the probes for the multiparametric, the probes that we were trying to develop is the probes or systems that allow us to see multiple things at the same time. And of course, you all are more than aware, the biological systems are so complex. For us chemists, they are very complex, and often difficult to control all the changes and parameters there, because it is not only the multitude of compounds or elements of the biological systems, but it's also the fact that we have to take into consideration where those different elements come together. So time, but also space, right? So we can have, it's not enough to just detect that something is appearing. We have to know in which molecular context is it appearing, when, and in which place, right? So this really makes it extremely difficult if you think it from the pure kind of design, kind of in vitro perspective. But a step towards that is kind of to try to use multiple or tools that allow us to see more than one thing at a time. And of course, you can do it with the many single probes or single things that then we can see multiple things at the same time, or we can develop a single molecule that allows you to see multiple things. And so this is a work that we've been trying to develop. So these, we call them the dual analyte probes, so dual analyte sensors. And the advantage there is that they actually allow you to detect slightly better an interaction because they have a two different molecules can have a different locations at the given time, but the one molecule will always be in the same location. So that makes it slightly more reliable. The interpretation of the data is made more reliable with it. So I've been working before during my postdoc, and we've developed a lot of probes for very elusive analytes in the biology, fluorescent probes, but also MRI contrast agents. And in my work in the independent group, we also worked on the variety of tools, fluorescent bioluminescent, but also protein labeling tools. And I'm not gonna, I could and would love to talk to you on the corridor about some of those things for much longer, but I just wanted to give you a flavor in general of what we've been doing. So designing the dual analyte probes, for example, for hypoxic state that is more reliable than detecting only single parameter. Like usually people either look into the low pH as a biomarker of hypoxia, or a strongly reducing power of the environment as the hypoxia, which is correlated with a lot of diseases. But putting this together makes sure that we actually detect hypoxia specifically from a different other conditions that sometimes have only low pH or only reducing power. And in the collaboration, so that's again something that we haven't been working on, but we've been asked for by the virologist during the COVID pandemic to try and come up with the idea how we could actually measure effectively effects of the small molecules of drugs on the entry of the virus into the cells. And of course, there's a lot of different ways, but one thing that we've done, we've developed this dual analyte probe for the two proteases on the surface of the human cells that are involved in the entry of the retroviruses inside the cells. And so we've then also worked a little bit by repetition to turn it into a robust service. So robust protocol, robust service that we've been now commercializing through the research infrastructure. And so far with the revenue of 200,000 euros, it's not a huge thing, but it just shows you how you can get to that process by repetition. And of course, we have not been funded to repeat things. We've been funded to always find something new and something up. But I think this is very important that if we take time in repetition, this is what Professor Charpentier also said, then we can be awarded, but it's a risk that not often it's easy to take and to make a decision when we do it. So we've also developed bioluminescent tools for multiple targets, and this is just the two enzymes that are important in the cancer development, and also in labeling, of proteins, covalently labeling of proteins with a without needing for genetic modification of the proteins. And in the lab, when you are a scientist and you develop something, and you always also want it to be impactful, but as I said before, it is not straightforward, I think, with the current systems to take something that we publish or it's publishable and to move that to that impact level. And I think, the example of that in my field is also the amount of tools and fluorescent probes people publish. So there are thousands of them published in the years. And a few years ago, my collaborator has counted, in the Web of Science, how many of those tools have been actually used again. And it's less than 3% of the tools that are published once are ever used again. And the reasons, of course, are multitude. One of them, it is quality. And quality meaning something which is robust. But of course, if you are not incentivized and funded for repetition and robustness, then it is difficult to make something robust and to use the resources there, hoping that it will pay off later on. The resources is another thing, so funding. And other one is also making it visible for others to use and useful for use. And of course, there are different methods and ways of success stories that were able to get to the impact and try to target those problems. And of course, CRISPR is one of the amazing success stories of having a technology that then, from the research publication, was taken up by the community and spread it around. But I would like to ask you a lot of questions. We didn't have the time today. You know, what do you think are the key elements of this publication that made it, for example, this successful, right? There is probably it can be probably a robustness of the protocols, but also other things that you needed to put in there, because we have so many of them published. And you said yourself, there's so many techniques that could be used for that purpose, but there are some that become used and some that don't. So that's, I think, a very interesting thing. But, you know, there's a lot of other problems in resourcing and in this rewarding the repetition and reproducibility. And I just wanted here to give you a few completely unrelated topics for you, or like examples where people try to do this, for you to maybe check out or to think about it and to provoke discussions maybe later on. So I think today, Professor Falcke, I was asking questions, and he said maybe what we should do in publishing is to actually publish always a paper with the people who developed it and people who checked it. And I actually, it was quite interesting to hear that, because I was looking for that for a long time in organic chemistry, and there's one actually journal that I found that is very low impact factor, and very little people publish there. But what they say needs to be done there is you always have two groups. You have a group who optimized it, who developed the synthesis, and the group who checked if it works. And they always publish together. And I think there is a huge space for us in this community to also think about, why is this model not more common, and should we, for the sake of what science should be, the repetition, the robustness, shouldn't we advocate for this broadly? Many of us are already at the sitting boards of the journals and other places, and this is something to think about, whether it shouldn't that be a usual step that we do. Another thing is this, I was working in Sydney 10 years ago, and next to me someone was involved in this open source malaria initiative, where they actually publish real time all their notes online to the group of people who are registered in the consortium. So it's like, the PhD student just writes it up there, and then they correct it, and everything is tracked, everyone can communicate at the same time, change things. And that's another interesting way of trying to get this reproducibility, robustness, and review in a slightly different way that we did today. There is also another initiative that have been close to my heart. So I haven't been involved in that initiative, but this is something I'm using a lot, which is a cell painting technique. So that the technique, basically what it does is just staining cells with multiple colors, and then using changes in the pattern of staining caused by stimulation by drugs or other things to see what mechanism of action those drugs induce. And really there is no novelty in terms of the fluorophores, there is no novelty in the concept and so on, but it's about reproducibility, making something robust. And this was possible because big institutions came together and made a consortium and could invest time and money to optimize that. And this has been very successful and brought other people in. And the small thing that we've been trying to do now, which also allows us to do this repetition, is the grant of Horizon Europe, and this is in the neuro-nanotoxicity. So something I've never worked in terms of the nanomaterials, but we try to transplant different methods for toxicity evaluation from small molecules into nanomaterials. And some of those grants actually fund the consortia for optimizing, not for developing new things, for taking the existing one and repeating and finding out which ones are good ones and reliable, and developing standards or standard drafts or proposals. So there is more and more happening in that area. And so another kind of step, so this translation, we can think how to do this translation. And for me also, the chance for making that translation of what I do in research was also work in the research infrastructures. And so this is, some of you familiar with translational research know about this technology readiness levels. So this is the idea that technologies go through certain levels, and they to start from the basic research all the way to the application in clinics. And this one is particularly for the drug development, but it actually is quite transferable to the different products and models. And actually, there is something that people have defined in this work as a valley of death. Valley of death is a place where a lot of projects get, there is a huge attrition of projects, so projects get dropped. And they are getting dropped in these levels where we start to validate them and reproduce. And the reasons behind this is funding. So academic grants fund earlier stage. Industries are interested in something validated. There's not much space, more and more now in Europe, but not much space funding this middle ground. But it's also making connections between different sectors that allows you to make that step across, but also the quality of the product and service that you develop, and in the terms of making something, again, robust, right? And if you have a choice as a researcher, especially a young researcher who has a limited amount of resources, am I going to spend all of these resources of sending my samples to multiple people and repeating the same process over and over again and getting a paper very low published because it's nothing new, it's a repeating of an existing thing, or doing an incremental change, but it's novel and I can sell it as a novel thing, then, you know, decisions are hard to make, those decisions. And I think this should also make us think about how we can create a system where we're not wasting the novelty, but reproducing those things is actually incentivized as well. And I think research infrastructures are the place where you can do it, because you don't have a pressure there for publishing, like in the groups, but you have experts and usually publicly funded infrastructure, which is state-of-the-art, usually better than any private infrastructure available. And you can do this type of work in those places. So one of this research infrastructures that I've been working on together with the group is the Center for Chemical Biology at my institute in Poland, in Poznań. And we've created the first in Poland screening platform, but also brought one of only few in the world MinFlux microscopes. You can see it here, which allows you, it's an optical microscope, which allows you actually to visualize things with the precision of single nanometer. So that's another order of magnitude more or less than the super resolution microscopy that you all heard about, probably. And so in there, we really kind of worked in a proactive manner, and we went out to the researchers, helped them select technologies for their work, not waiting for them to come to us. Go out there. We really managed to increase the success rate on funding acquisition. We ran a lot of projects in the recent years, which brought actually revenue and sustainability for the research infrastructure there, but also increased the quality of the research projects that are running in our institute, but also now in other places in Poland. And now I'm doing work to take it further in Sydney, where I actually run this innovation center. Sorry, I almost hit you with the laser. I'm so sorry. So I'm running this innovation center with multiple facilities in there that allows us to cover a huge kind of like the pipeline of preclinical work from the beginning till the really kind of like a end of preclinical studies. And we focus there, we add to what we've done in Poland, this interaction with investors and clients to co-design what they would like to see in the product, and then take on ourselves this optimization process to move the product from what people publish to the level that investors are interested in investing in. So, so I wanted to just show you here, there's a lot of text here, but I want to kind of put this out there that I think the right managing of the public money that we invest in the research infrastructures require us to rethink how we use those infrastructures. And I think because there is a huge potential and they are often underused, because our approach usually is a more reactive. So we wait for people to come over to research infrastructure and tell the people in the research infrastructure what to do. And we often focus only on academic support, despite the fact that we have usually competitive equipment that is much better than the commercial contract research organizations or other places like this. So in our new kind of catalyst-like model of the research infrastructure, we advocate for going out there and taking it into our own hands, talking to researchers, talking to industries, and designing projects for them using our technology. I think this has been extremely effective in my experience, and this also is nothing, it allows people to bet if you have a new technology, it's very difficult to think about how you put that in your own research. But if someone who is an expert in that can help you out with this, that can be very beneficial. But it's also about thinking strategically and thinking about how we can make our operations sustainable. And one of the things there is also to invest in internal R&D in money that is not doing new things, but repeating things published and finding out which ones are robust and which ones can be turned into something useful. But it also requires investments in business development activities. So in going out there and promoting this sort of services that we try to commercialize to external users. And from these services, what we can often derive is the product. So if you have an assay or protocol that you optimize and you offer as a service to collaborators or people, and you do it enough times, you can turn that into a product like a kit or the reagent that you can start selling. So this is actually a step that we're often missing in the commercialization process from the research academic work. And so this really allows us to be more impactful, more sustainable, and in terms of financial sustainability, and really allows us to do it more efficiently. And so the last thing that I wanted to talk about is some of the activities that allowed me to also be here today, I think, which are the activities in the voluntary activities in the community of the young early and mid-career researchers, and especially in the National Academy, where we worked a lot on outreach or on training, but also on trying to get involved in policy and advice. Young Academy Science Advice Structure that Katalin has mentioned, which I can see people from SAPIA here and Sam today, that allowed and made it possible for us to be a part, for the early and mid-career researchers to be a part of the process, but a formal part of the process, giving us a real vote, a real voice in that space. And I think, you know, there's still a lot of debates, and I've heard from Rudy today as well that there are some things that we've been bringing up. They are still sometimes contentious to talk about and to put forward. But I think importantly, it gives a chance to voice them. And I think this is really critical, and we really appreciate that opportunity. And finally, I really wanted to underline the importance of the Coalition on Advancing Research Assessment that I haven't been involved much in, but I think its role is really critical. So what I want to kind of now wrap it up with is this thing that I call the EMCR paradox. So I think nowadays, I think that the role of the scientist and how we perceive what scientists or researchers should do has been changing from different reasons. And on top of the usual things like publications, we add to that expectations of, you know, impact, engagement, contributions to policy, outreach, you know, all of those. But at the same time, we evaluate early and mid-career researchers, but also others, based on the publication metrics and traditional outputs that actually are quite narrow and don't capture this diversity of expectation. And so I think this diversity of research activities that we are asked to do and we want to engage in is also cannot be captured by something which we've developed or has been developed in the community 50 years ago. So we need that change there. And to build these better systems, we need to embrace the diversity of careers and the fact that people want to do different things around science can only benefit and does benefit institutions, and it should be rewarded as a research activity in a way as well. Also, to do that, I think we really need to think about the role of the research infrastructures and the mobility between academia and other sectors that we all talk about and we say it's great, but we don't really often truly reward and promote that sort of activities. And also to recognize that excellence is something beyond fitting into traditional model of doing research. Excellence can be, and even scientific excellence or research excellence can be actually manifested in a very different ways nowadays, that we should think, we often see it, but we don't have metrics and systems to recognize it. So with that slide, I just wanted to kind of call on action to try and think about that on the institutional level, on the individual's level, to try and build careers in a way that we do things that we are good at, that enjoy, but also that maybe build support systems around our peers to allow us to make it effective, and also to policy and decision makers to reform that system and to support this diversity of careers and recognize that this is really important. This is how the research is done nowadays. And this is what we expect, so why shouldn't we actually reward and acknowledge it as well? So that's the end of my talk. Thank you so much for your attention. There's a lot of people, institutions that I wanted to thank, and I could spend another half an hour just talking about them. But thank you so much, and thank you for the opportunity again, and yeah, have a good day.
Thank you and congratulations again. I'm not sure if there are any very quick questions. We might go, yes, Siet has one. Maybe I will give you the mic.
Yeah, just a very, very short comment because the lunch is waiting for us. To overcome this valley of death you mentioned, we have introduced in the recent past in the European Research Council, but also in the European Association for Cooperation in Science and Technology, COST, the proof of concept grant scheme and the innovator grant to basically explore innovation potential of findings of frontier research and networking already financed by these organizations, and both are very successful and of course could be further expanded, but we know that indeed, as you pointed out, this first step is often the hurdle, but it is being addressed, and I think you made a plea to go beyond that. But again, Europe is on the move in these things.
I agree, and I think this is great. And of course, when I was saying funding in general, I also mentioned that this is happening in some places, and I think that's a great example. One thing that I noticed with these most of these programs is when we talk about the translation and commercialization, we think about the product. The reasons behind commercializing product is, of course, that the return of interest can be very high on the product. But there is a much lower hanging fruit there that we undervalue and we don't take advantage of, in my opinion, which is service commercialization. So commercialization methods, protocols, through providing services like the contract research organizations, but not competing with contract research organizations, but doing that on the things that are more high-end. When they trickle down to contract research, then they become mundane. But we can pick up as through the academia, things that are early on, the CRISPR methodology, and then offer this before a product as a service to do things for people. And I think this one is highly underfunded in generally in all of those programs. But I think it's a first step to going to the product commercialization. And we have all the prerequisites here in the public funded systems to do that more.
Maria also would like to have...
Yes, very shortly. Thank you very much. Further to what Siet said about the ERC efforts, proof of concept, and further to what you just said, there is, of course, a dedicated source of funds in the framework program for exactly this phase of repetition, of business development, of commercialization of innovations, etc. And this is the European Innovation Council. And I mean, under this framework program, the funds are really substantial, 10 billion euros. So this has been addressed, but then again, the problem is that the application pressure is huge. This is, of course, the case for the ERC as well, and only a fraction of great applications can be funded, though the budget is big. And now we have heard, well, let's see about Horizon 10, but we have heard signals already that this part in the next framework program should be better funded, but we will see what happens. Thank you very much.
My name is Maria Makarov, and I'm president of Academia Europaea. So, welcome to the intellectual powerhouse of Europe, and this is the community of Academia Europaea. You all have undergone a very, very strict evaluation process. As you know, the first criterion is excellence, scholarly and/or scientific excellence. But Academia Europaea has signed the QUARA principles. You may know QUARA stands for Coalition for Renewal of Research Assessment. and more than 800 universities, research organizations, academies, funding agencies in Europe have signed the QUARA principles. And the essence of the QUARA principles is that whether assessing now researchers, scientists, scholars, or their projects, the focus should be on qualitative indicators. The focus should be on the quality of the essence, of the substance of what they are doing, what they want to do, and what they have achieved. And quantitative indicators, such as impact factors, attracted funding euros, etc., they should be used only when necessary to support the findings of the qualitative assessment. Now, we signed this agreement, Academia Europaea, we signed it, and now for the first time in this round, these principles were taken into consideration. And the point is, for us, that taking these QUARA principles into consideration, also unconventional researcher pathways could be recognized in the assessment of the nominations. And also, perhaps then, it would be easier for the younger generation of scientists, of researchers, of scholars to become members of our academy. Now, a few words about numbers. Over the 3 past years, we have had more than 1,000 new members, and in this round, I believe the number of new members is 317, at least it is over 300. And this brings us to a total number of members of 5,600. And then you do remember that Academia Europaea, the word Europaea means Europe, whole of Europe. It's not the European Union, it is 44 countries. So this gives diversity. But we do have a challenge in the nominations, which is that we need more diversity in the membership still. And we need the share of women, scholars and scientists to be increased. We need more members from the widening countries. And it is not a goal per se, but the goal is to increase collective intelligence that diversity brings with it. And believe it or not, but when Academia Europaea was founded 35 years ago, the share of women founders, women members, was 18%, and today it's 18.3%. The share of widening country scholars and scientists is less than 11%. So you are eligible to nominate new members, and the rules and regulations are on the website how to do this. And I just, invite you to keep in mind the diversity factor when you nominate peers. And I really invite you to make nominations. This will increase your own sort of sub-community amongst the members of Academia Europaea. So now I give the floor to our Vice President, Professor Donald Dingwell. So please, Don, continue.
Thank you very much, Maria. So just briefly to say one last time how we're going to physically do this. Your name is going to be called. We'll wait for you to get to the stairs. You'll come up the stairs on my right, and then you'll migrate across the stage in a series of steps. I will shake your hand. You will move to the president. She will shake your hand, give you a gift of the Academy, and then the 3 of us will have one photo taken that you will receive later, and then you leave the stage on my left, okay? There will be certain people whose names are called who are not here, no problem. I'll wait a certain amount of time to see movement, like a good hunter. If I don't see anything, I will move to the next name, but if for any reason I miss you, don't see you, just shout. I will freeze like an animal, and we'll make sure that you can get up here on the stage, okay? So we're in this together. We both want the same thing. So let's begin. I have a series of slides which describes in a series of bullet points the specialties of each of the members, which we will project now. They're by section, they're not by alphabetical order globally, so you're going to have to pay attention to what's there and what I say. You won't simply be able to calculate when you're going to come to the stage. So the first new member that I'd like to invite to the stage, if he is present, is Haskell Greenfield from the University of Manitoba. Is he in the room? Apparently not, but again, if I make a mistake there, simply say so loudly. The next is Slobodan Markovic from the University of Belgrade in Serbia. Luisa Migliorati from the Sapienza in Rome. It occurs to me that we can use the central stairs for everything, so let's do that, okay? I grew up in the woods. Okay. Felicitas Schmieder from the Fernuniversität in Hagen. Is she? She's Fern, okay. Darius Stola from the Polish Academy of Sciences in Warsaw. The list that I'm reading to you is the list of registered participants for the meeting. Arlene Holmes Henderson from Durham University in the UK. Gabor Kosha from the Eötvös Loránd University of Budapest. Here he comes. I can point out to all of you, you will receive a nice certificate in due course, but we will send them to you following this ceremony. Enrico Morano from Turin in Italy. Niels Arne Pedersen from Aarhus University in Denmark. Sofia Xenofontes from Aristotle University of Thessaloniki. Bas Arts from the University College London in the UK. Anna Carlier from the Sorbonne in Paris. Livio Gaeta, University of Turin in Italy. Aylin Küntay from Koç University in Istanbul. Janet Pierre Humbert from or Pierre Humbert, depending on which country you were born in, from the University of Oxford. Is she here? No, okay. Malka Rappaport-Hovat from the Hebrew University of Jerusalem. Michael Schulte from the University of Agder in Kristiansand, Norway. Helena Duffy from the University of Wroclaw in Poland. Thank goodness she's here. Tatjana Jukic from the University of Zagreb in Croatia. Markus Messling, Universität des Saarlandes, Saarbrücken. Martin Prohachka, Charles University, Prague, Czech Republic. Wojciech Balusz, Jagiellonian University in Krakow. I pronounced it German, I'm sorry. Poland. Massimo Leoni, Università di Torino, Turin, Italy. Gabriele Balbi, Università della Svizzera, Lugano. Susanne Kinnebrock, Augsburg, Universität Augsburg, Germany. Margret Lünenburg, Freie Universität Berlin. Anna Kaun, Södertörn, University, Stockholm. Ramon Salaveria, University of Navarra, Pamplona in Spain. Oh, I've done something wrong. Technical assistance, please. Yeah. This guy is going to be famous. I hit the wrong technical for some reason. Okay, Monica Tadiken, Pamplona, Spain. From Braunschweig, there's a technical issue, apparently. From Braunschweig, ladies and gentlemen. Oui. Apologies. So I hope I didn't cause that. Barbie Selizer from University of Pennsylvania, Philadelphia. Hui Wang from Tsinghua. We'll invite you to say the same thing at the end, and then you come up, okay? At the end, we'll make a general call for anybody who is in the category of new member and has not been called. So, Philip, no problem. You'll be up here in a minute. Hui Wang from Tsinghua University in Beijing. Daniele Caramani from the University of Zurich. Maurizio Ferreira from the University of Milan. Harriet Buckley from Durham University of the UK. Inaki Alday Sanz from Tulane University, Barcelona. Randall Lesaffer from KU Leuven, Belgium. Antonello Miranda from the University of Palermo. Gregor Stuban from the University of Ljubljana, Slovenia. From the University of Palermo. That was Antonello Miranda. Kenneth Hugdahl, I hope I pronounced it roughly correctly, University of Bergen. Andrew Kresch, University of Zurich. Barbara Hammer, University of Bielefeld in Germany. Mira Mazzini, Technische Universität Darmstadt. Herzlich willkommen. Stephanie Rindele-Maar, Technische Universität München. Andreas Zeller, CISPA Helmholtz Institute for Information Security in Saarbrücken. Tiziana Di Matteo, King's College, London. Ambrogio Fasoli, who spoke to us earlier today from Swiss Federal Institute in Lausanne, EPFL. Despo Fatakasinos, University of Cyprus. I think I realize why our photographer is so fit. He's doing a lot of running right now. Martin Ostoya Starzewski, University of Illinois at Urbana-Champaign. Tanti Kim Nguyen, University College London. Cecilia Ceccarelli, Grenoble. Yes, La Louis, EPFL, Lausanne. There must be a big meeting in Lausanne right now. Steve Moges from the Hungarian Academy of Sciences in Budapest. Xiaoxiang Xu from the Technical University of Munich. Was here yesterday, okay. Luis Blanco from the CSIC in Madrid. Emmanuelle Charpentier, we know she was here, but I've been told she may have been called away for public relations and other things. So we congratulate her once again, of course. Jun Biao Dai, Chinese Academy of Agricultural Sciences in Shenzhen in China. Jyrki Heino, University of Turku in Finland. Leontios Kostrikis from the University of Cyprus. Francisco Martinez Mojica from the University of Alicante in Spain. Andres Metspalu from Tartu in Estonia. Michaela Müller-Tutwin, Institut Pasteur in Paris. And Natalia Prevaskaya from the University of Lille. Holger Puchta from the Karlsruhe Institute for Technology, KIT, in Germany. Li-Chin Zhang from the East China University of Science and Technology in Shanghai. Thomas Brunner, die Universität Konstanz. Pirjo Helariutta from the University of Helsinki, Madam President. Anna-Katharina Simon from the Max Delbrück Center in Berlin. Sharon A. Toos from the Francis Crick Institute in London. Claudia Bagni from the University of Lausanne. Susanne Helyes from the University of Pécs in Hungary. Peter Holzer from the Medical University of Graz in Austria. Gemma Modinos from King's College London. Hello, Gemma. Hu Dongqi from the Beijing Tiantan Hospital in China. Pavel Cvičák from the University of Oxford. Alessandro Chiarucci from the Alma Mater University of Bologna. Richard Primak from Boston University. Carlo Rodinini from the Sapienza University of Rome. Louise Vet from the Netherlands Institute of Ecology in Wageningen. Ji Chong Chow, University of Oklahoma, Norman, Oklahoma. Boris Buklacic, University of Zagreb, School of Medicine, Croatia. Xiaoyuan Chen from the National University of Singapore. Martin Fromm from the Friedrich-Alexander-Universität in Erlangen, Nürnberg. Martin Kolzenburg from University College London. Rainer Schulz, Justus-Liebig-Universität Gießen. Michelle Wenzing, Heidelberg Universität. Mone Saidi, Icahn School of Medicine at Mount Sinai in New York. With that, I will come to the end of my list of established names, and I will ask any of you who have been made members and have not yet had the honor of coming to the stage to come now. And if I know your name, I will say it. If I don't, you will tell me. So this is Philipp Stockhammer from my own university in Munich, the LMU.
You don't know my name, right? Katalin Zheng.
Katalin Zheng.
Yes.
Tongji University.
Shanghai. Thank you.
Thank you. You've been called. Janet Pierre-Humbert. So I look into the room for further unannounced regular members, and I don't see any, but we have one very special thing left to do here, which is to acknowledge that we have a new member called a patron member, which is the Hungarian Research Network, HUNREN. And we have a special certificate prepared for this, and I would ask our representative of the HUNREN to join us now on the stage. Madam President. As you see, the patron member received a certificate right away. So if you're wondering why, or if you'd like to investigate becoming a patron member, please put yourself in contact with us. But we have a very special relationship with the Hungarian Research Network to the mutual benefit of both of us. So we are through this year's ceremony. I'd just like to say one or two words, and then perhaps, Madam President, you have one or two more words to say? You will decide, okay. I just want to say, you're new members. You know, there's this great German expression, which I forget all the time, but it basically means there's some magic in every beginning. This is your beginning in the Academia Europaea, and there, I hope, is a little bit of magic in it for you. And there's also great value in the newness of you to us, which is you can tell us what you think of how we work, and you can tell us what you think we should stop doing or do better. And the best time to do it is now, in the next 3 months, before you become jaded like the rest of us and just run the show. So I'll be acting president from the 1st of January, and I will be particularly happy to hear from any of you. I'm very easy to find. I'm the only dingwell on the continent of Europe, I think. And if you would contact me and give me any advice or any messages or any suggestions, I promise you I'll respond to you personally. So thank you very much for that, and I'll hand over for a few last words to our president.
Now you are members of Academia Europaea, MAE, and this is what would be the English word for this title, an honorary title. And so you should put that into your CV, because this, of course, is an indication that you belong to the sort of elite of researchers and scholars of entire Europe. And you, of course, are welcome to put it under your signature in your emails, like many, many, many of our members do. So once more, congratulations to all of you.
Yes, the request has come in that you all now come to the stage together, and we'll have a class photo. So please come on up. It will only take a minute. Just use whatever stairs are close. So.
I think that saying came from the musical Pippin.
The music?
Musical, Broadway musical Pippin.
I've read it somewhere else, but you may be right.
I think they have a saying just like that.
I was filling out a crossword puzzle, and that was what the answer was.
We may be using the stairs.
Try to see the camera.
I think this is going to work. I don't think that this small in front.
There's the photograph. Ah, there. He's up there. Officially.
Okay.
Colleagues, ladies and gentlemen, I think we are at the time, 6:30 or 4:30, so we have to start with the life science session. Actually, in the previous years, we tried to have a common topic, but this year, based on Varietas Delectat, we use different topics, but there is also some link between them. So we are going to hear a talk which is on evolution of human population, migration, infectious diseases, but this is also connected to climate change, biodiversity, and many problems in this respect. The third talk will be a completely different one, restoring vision. But this is, I think, a topic which will be also interesting for you and for many, many people, because this is one of the unresolved problems. So the first talk will be given by a Balzan Prize winner from 2020. I have to tell that the Balzan Prize is really a very prestigious scientific prize. Maybe not everybody knows this very well. This is given every year on all scientific disciplines, but always on a different topics. So last year in the life sciences, it was on ancient DNA. And the winner of the Balzan Prize was Eske Willerslev. And he got this prize for his studies on human DNA with an evolutionary perspective focusing on population mobility and migration, and thus to a large extent contributing to transform our understanding of human history. For leading the way in using ancient DNA from teeth to identify human pathogens, and for retrieving DNA directly from environmental samples, opening a new scientific fields. Really, I think before him and his studies, environmental DNA was not really used widely in the scientific population. So I am particularly happy to have these Balzan Prize lectures, because they are really at top level of scientific quality, and also the Balzan Foundation is very generous to support the speakers of the Balzan Prize winners. So I am very happy that from the Balzan Foundation, Susanne Werder is among us, and he came to be present during these Balzan Prize lectures. So the first speak will be given by Eske, but he's going to speak about the genomic history of Western Eurasia. So Eske, please come. I forgot to tell you that you are director of this center and professor of the University of Copenhagen and University of Cambridge. But
it's okay. Don't worry. Thank you so much for the invitation to come here. So, yeah, as was just said, my talk will be mainly about the genomic history of Western Eurasia, and I hope there will be two take-home messages, two main take-home messages. One is that you can say we genetically, in Europe and also in large parts of Asia, genetically were formed very recently due to processes that happened very recent in our history. And secondly, if you understand this population history, if you want the history of how humans were formed in different parts of the world, it allows you to go and try to understand what is the underlying reason for differences in disease risk among different human populations, okay? So let's get to it. In terms of, we know from archaeology, obviously, that humans have been present in modern humans, anatomically modern human. Our species has been present in Europe for at least about 50,000 years. But who were these modern humans related to? We knew very little about until we could do genomics. And here we have Kostyenki 14. We did the genome. I think it's the first ancient human genome done from one of these very early Stone Age peoples in Europe. He's between 36 and 38,000 years old. And what we could see is that, Kostyenki 14, who's found just outside Moscow, he's not, you can say, we don't know any descendants of this individual today, but what we can see is he's closer related to present-day peoples in Europe and West Asia than to any other contemporary peoples around the world. So it suggests that there is at least some degree of continuity, not very much, but some degree going from these very early Stone Age peoples all the way up to today. We can also say from genetics something about the behavior of some of these very early Stone Age peoples. Here we have Sungir, which is contemporary with Kushtinki, also found close to Moscow. But here we have multiple individuals that died around the same time and were buried around the same time, okay? And what we can see from genomics is, well, they came from very small effective population sizes. That's not a surprise, very small groups of peoples. But what might be more surprising is they are not inbred at all. So that tells us that even these early Stone Age peoples had a deliberate strategy, behavioral strategy to avoid inbreeding, to find mates, even though they were far away, in order to avoid inbreeding. And I think it's in contrast to at least what we can see from the Neanderthal genomes that has been published today, another human species that was almost contemporary with these guys here, right? That they are heavily inbred. So there is a behavioral difference between the two. Moving on, sorry, oops, I jumped one slide here. So, well, we continue in Europe and also in Asia for that matter to live as hunter-gatherers until, you can say, around 10,000 years ago, right? So our diet consists of meat, fish, berries, roots, and you know, we continue living in small hunter-gatherer groups. What is kind of surprising is that among even the hunter-gatherers, in these late hunter-gatherers in Europe, before we become farmers, we can see there's a very deep genetic divide between the east and the west of Europe. So from around the Baltic states down to the Black Sea. So for some reason, people doesn't mate with each other very much on one side of the border and the other side of the border. And it's not a physical border. It's not a physical barrier. So it must be some kind of cultural barrier. We don't know exactly why, but we can see it genetically. So it goes, you can say, it is already existing among the late hunter-gatherers. What then happens around 10,000, 11,000 years ago is, well, humans down in the Middle East and Near East start domesticating animals and plants, right? They become farmers. And we can see genetically that they're moving up through Europe, right? Bringing farming with them. But they're kind of, you can say, they are moving up through on the west side of this divide, not on the east side, right? So it's really the west hunter-gatherers on the west side that are getting experience with meeting all these farmers coming up, while on the east side they continue as being hunter-gatherers for way longer. And that, and in southern Europe, we see a lot of mixture between, you can say, these last hunter-gatherers in Europe and the new arrivals, the farmers from the Middle and Near East, which further deepen, if you want, the genetic divide between the West and the East. That divide doesn't exist here today, so don't worry about it. If you worry about Putin or something saying, well, it's exactly what we always said. It will be resolved. It will be dissolved in a moment. But anyway, so you can say you have this transition, and this transition is considered among the greatest changes in lifestyle that we know in human history, right? We're going from meat, fish, berries, roots, what you would call a paleo diet today. There's even people believing that's healthy for you to eat that today, into basically eating something similar to muesli day out and day in, right? And you are going from being mobile, living in very small societies, to be more stationary in larger societies. And it actually has pronounced impact on our genetics. I mean, one of the things we can see is that something called the FATS region in the genome, which is involved in making short-chain fatty acids into long-chain fatty acids. You need that for your brain and nervous system. Well, that's under massive selection. So it's really, that changes in Europeans. I mean, the genetics changes in Europeans, and it's because you're getting long-chain fatty acids directly from fish and meat. But when you are eating muesli or grains, you are getting it as short-chain fatty acids, and the body itself needs to change it into long-chain fatty acids. and that's the fats region that are involved in that. When these farmers move north, you can say it doesn't look like, at least everywhere, that it's just, you can say, admixture and people basically getting kids with each other. So when we get into places like Denmark, which has an incredible skeleton material covering this transition, it's one of the richest, you can say, numbers of skeletons in this transition from hunter-gathering to farming. What we can see is that there's hunter-gatherers living in Denmark, but then there's coming mixed individuals from the south. I mean, hunter-gatherers mixed with these farmers, and within a few generations, the hunter-gatherers are gone in Denmark. We don't know exactly what happens to them, but I would say, in my view, but this is my personal view, I think it looks like genocide. I mean, it's very hard to see it differently. I mean, there's some of my colleagues, they believe they paddled to Norway, but I don't think they've tried to take the ferry from Denmark to Norway. It's, even in a ferry, it's actually a very unpleasant experience. But so you can say the dynamics of the meeting between these peoples is probably not just one thing, right? It varies across the landscape, whether it's, you can say, peace and love, or whether it's replacement and war. Then when we get to the Bronze Age, of course, archaeologically, we also knew that something was happening, right? People were using new metals, they were burying the dead in new ways. The nuclear family becomes the most important entity. But many believed, before genetic studies, many believed that it was due to the same peoples just learning to do something new, just as they believed that when farming was introduced into Europe. But again, it's shown to be wrong genetically. It's actually due to yet another migration, this time from the Pontic steppe around 5,000 years ago, which is the area around Ukraine, Belarus, parts of Russia. And these peoples, well, we call them Yamnaya, and they were a herding people. They had herding animals, and they were pastoralists. What was quite amazing when we saw these genetic results, both done by our group, but also by the group of Reich, was you saw this movement around 5,000 years ago, northwest into Europe and eastwards as well. And this movement fits beautifully, you can say, with a linguistic theory about the early spread of the Indo-European languages. So the Indo-European languages is English, German, Danish, whatever, French, the most widely spoken language family in the world, right? And of course, linguists has been interested in understanding when does it originate, how does it spread, and there's been all kinds of theories about this, both in terms of the timing and from where it comes. But one of the linguistic theories, some call it the steppe hypothesis, predicted exactly that pattern, right? That at 5,000 years ago there's a northwestern and eastern spread from the Pontic steppe. And of course, from genetics, you can't say what people were speaking. I mean, that's impossible, right? But you can, of course, look at the pattern and compare it to patterns obtained, for example, from linguistics and say, well, it actually looks like there is some degree of consistency here. And what is kind of interesting, now this is a quite old paper, but it's still the same point. When you look at the genetic diversity in Europe, I mean, the gray dots here are present-day genetic diversity in Europe, where you see, you know, the differentiation between Southern Europeans, Eastern Europeans, Northern Europeans, etc. And what you can see is that the hunter-gatherers in Europe, even the late ones, are kind of falling outside that genetic diversity. And even with the farmers, you are not really getting into that present-day diversity. It's really first with the Bronze Age that you can say what we would call modern Europe, from a genetic standpoint, is formed, right? So that's 5,000 years ago. It's very recent, right, in our history. Well, we also know Yamnaya went eastwards, right? We know they were going eastwards. And we know we find them there. So they went there. There's no doubt about it. But they do never seem to have the same genetic success in Western Asia and in Southern Asia, Central Asia, as they have in Europe. You remember that in the eastern part, it's still mainly hunter-gatherers, right? Who were these peoples that the Yamnaya meet on the eastern side of the divide 5,000 years ago? People actually didn't know who they were. I mean, who are they related to? Who are they? And what is pretty interesting and very surprising for us, it turns out that these peoples are remnants of a very ancient group of peoples that actually don't really exist today in its, if you want, in its pure genetic form. It's related to a skeleton we found and sequenced, or we sequenced, that is from Lake Baikal in Siberia, dated 24,000 years old. And this is a child skeleton. And back then when we uncovered, you can say, the genetic makeup of this skeleton, it was a big surprise because this is an area, of course, Lake Baikal, between Mongolia and Siberia, where East Asian peoples are living today. I mean, that's the indigenous population, right? And this skeleton is most closely related to Native Americans and secondly to Northern Europeans, okay? And not really very closely related to Asians. But the remnants, we thought these guys died out, you know, in the early Stone Age. But in fact, they survive in Western and Central Asia. And those are the people that the Yamnaya are meeting, okay? And these peoples, why are they not successful? Well, this is speculation from my point of view. I have to be honest with you here. But what we do know is we have the oldest evidence of the domestication of the horse in this area. This is Kazakhstan, around 6,000 years ago. You find horses with marks of bristles and milk residues in the pots. They domesticated the horses. Some archaeologists believe it was the sophisticated Yamnaya that taught them how to domesticate the horse. But in fact, we don't find any evidence of admixture between these peoples and Yamnaya. What it looks like is that it's really a local phenomena. They are hunting the horse, and at some point they are managing domesticating. What is kind of the tragic irony in all this is that this event, which is one of the biggest cultural achievements in human history, they're not spreading the knowledge. It might be that they can keep Yamnaya away or whatever, but it's not being widely spread. So the domestic horse that we all know of today, and which is all over the world, is actually a separate event, okay, that reaches Europe. And then you can say the descendants of Yamnaya from Europe, some people call them battle axe culture, others Syntasta, it's really the same thing. They invent the chariot, the two-wheeled wagon, war machine wagon, you know, from Ben-Hur and all that, right? And they are then going across from Europe into Asia, across the Ural Mountains. And after that, we don't see the remaining hunter-gatherers, these guys, you know, that also gave rise to Native Americans. They're gone, right? What happens to them, we don't know. I think they're killed, but I always say that, as you can hear, when we don't see people. But these guys, the Syntasta, have influence even all the way down into these with the two-wheel wagon, have influence both linguistically but also genetically, all the way down to South Asia, Northern India and Pakistan, okay? Well, then, as I said, we enter a time where this second event of the domestication of the horse has been spreading all over Eurasia, right? And of course, the horse domestication changes everything. How quickly you can go from A to B, how you do trade, how you do warfare. And an area that no one really were very interested in before the horse, namely the Eurasian steppe, becomes the most important area, if you can say, in that time period of the world, because the ones that control that controls the trade between Europe and Asia. We also know it as the Silk Route, right? And first, it's these, you can say, the remnants or the descendants, if you want, of Yamnaya, these Syntasta battle axe people that controls it. Well, then it's taken over by the Scythians, right? And who are the Scythians? Well, it's both male and females are mounted warriors, right? And when we genetically test them, it's very interesting. The Scythians is a multi-ethnic culture. So it's you can say culturally they're very similar across the Eurasian steppe. but genetically, you know, they are the remnants of the Santasta battle axe peoples and then Asian groups that are coming down from the Siberian forests. So you actually have a very similar culture, but quite distinct ethnic groups, which is pretty unusual. But even those guys can't control the steppe. Everybody wants it. The next major group coming in are the Huns, right? And who are the Huns? The Huns are coming out of China, and they don't have a very big genetic impact because they are living as like an upper class society. But linguistically, they have an enormous impact because they are Turkic-speaking people. And they are basically transforming this area from being Indo-Iranian, Indo-European speaking to becoming Turkish speaking. But it's still very dominated by people of European genetic descent at this point, right? But this is not the case today, right? It's not the case. Today, these areas are dominated by people of East Asian ancestry. So what is happening? Well, what happens is Genghis Khan and the Mongolian horde, right? That are basically coming in, and now we are up in the medieval times, right? We're up in medieval times, where they are basically spreading from Central Asia westwards all the way into Eastern Europe, right? And also eastwards, and are really, you can say, transforming genetically this area to becoming East Asian, and we see the world we know of today. So you can see the world we know of today is extremely recent, right? It's not deep. It's not a deep, deep history. It's really events that form both Europe and Asia, much more recent than I learned in school, where, for example, I learned Eske derived directly from the Stone Age man in Denmark. I mean, totally wrong, right? I derived from Yamnaya, if anything, right? Okay. Well, finally, just briefly, if you move up to younger periods, such as the Viking period, we all know about the Vikings, right? We have seen the series, the Vikings. Who are the Vikings? Well, big blonde men meeting from all parts of Scandinavia, going out raiding together across Europe, right? That's kind of the narrative. Where is it coming from? It's coming from the sagas, right? What are the sagas? That's written text that was done many years after the Viking period, right? And which has a very specific purpose. I mean, if you read them, you will see a Viking that dies always says something tremendously cool before they die, right? And then you ask yourself, well, was war that different back then than now, where we're just lying screaming, right? So there's a purpose of portraying them in a certain way. And we did a large study on the Vikings, and well, what can we see? We can see many things. First of all, there was fewer blonde Vikings than there's blonde Scandinavians today. Secondly, Vikings are not an ethnic phenomenon. It's a lifestyle. We find Vikings that are half Southern Europeans, half Scandinavians, half Sami, which are the people in the far north of Scandinavia, indigenous peoples, half European Scandinavians. We even find Vikings buried with swords and shields and everything in Scotland. They're not Scandinavian at all. So Viking is a lifestyle. It's not an ethnicity. Yes, it originates out of Scandinavia, but there's many other groups that are taking, you can say, this lifestyle into the way they're living. And when I said that, I got a death threat from Norway, of course. But yeah, but it's true. So you can see there's a lot of identity here, right? We can also, there's found one raiding party of Vikings. It's found in Estonia, right? And it's a group of Vikings coming in, getting killed, and then buried. So they're lying there, and you have kind of a snapshot of a Viking party, right? And in the films and the sagas, we hear about, you know, all the jarls meeting from different places in Scandinavia, going out raiding together. What do we see? Well, it's Uncle Bob and three brothers, you know. It's a small society in Sweden, right, that go out raiding together. So I'm not saying that it never happened like we see it in the Vikings, but there's just not evidence for it. Archaeological, we don't see that evidence, let me put it that way, genetically. We can also see where the different Viking groups were traveling to. You know, Danes are mainly going to England, Swedes to the Baltic, and the Norwegians are the ones that travel furthest, you know, to both Iceland Ireland, Iceland, and Greenland. And I would say the Viking period is really, you can say, characterized by there's being very little interaction within Scandinavia itself. We don't see a lot of interaction there. What we see is a lot of interaction outside Scandinavia, from Scandinavia, right? People are going out of Scandinavia to explore, you can say, what's out there. Okay, so you can say, roughly speaking, right, Europe was formed by 3 major migration events. It's the hunter-gatherers, right, that came in. It's the farmers that came from the Middle and Near East bringing agriculture. And it's the Bronze Age Yamnaya people from the Pontic Steppe. So all Europeans can be modeled as a mixture of these 3 events. So what makes Europeans different from each other, if you are Northern European, Southern European, Eastern European, Western European, is really how much of each of these 3 ancestries you have. Okay? So it's a relative, you can say, well, Danes have more Yamnaya than Eastern Europeans, for example, right? But, and Southern Europeans have more farmer, right? Eastern Europeans have mainly have more hunter-gatherer and so forth. But it's all relative. How much do you have of these 3 migration events? So therefore, you can then start saying, okay, we know this. We also know now the genetic makeup of each of these 3 migrations. We have a good idea of what was the diversity of a Yamnaya, the diversity of a hunter-gatherer, the diversity of a farmer. Let's take UK Biobank, right? What is UK Biobank? UK Biobank contains information about you can say, the genetic and phenotypic, if you want, relationships, right? The genetic behind certain phenotypes, blue eyes, brown eyes, light skin, but also various types of diseases, okay? So it says something about disease risk and the probability of having a certain phenotype, right? So, and it's important to say it's risk or probability. It's not like it's a given, right? But you can have a certain genetic profile that gives you an increased risk of something or increased probability of something. And then you can take these different ancestries and you can paint UK Biobank, right? And you can start asking the question and say, well, is the sum of these genetic mutation variants, as we call it, that we know are important for various phenotypic traits or diseases that are coming with one or the other of these migrations? And yes, that's the case, right? So for example, the ability to become very tall height, right? Genetically, the ability or the potential, if you want, it's a Yamnaya trait. And it actually makes sense, right? Because Northwestern Europeans that has a lot of Yamnaya, well, generally they're quite tall compared to other Europeans, right? If you look at things like diabetes type 2, well, it looks like this is a trait, genetic trait that are coming with the hunter-gatherers. And that also actually, to me at least, makes sense, right? Because if you're living as a hunter-gatherer, you will not get diabetes type 2, right? Because you're not exposed to what will give you a diabetes type 2. But if you start eating grains with that genetic profile, yes, then you actually have a chance, right, of getting there, right? And things like anxiety, where you're like very nervous, is a farmer trait, right? Genetic, you can say the genetic susceptibility to that is a farmer trait, right? So you can start trying to kind of say, okay, you know, where are these different traits coming from? Why do we have them? And if we go into more detail in one of them, that's what we did with something called multiple sclerosis, right? Multiple sclerosis is an autoimmune disease. And it's really the immune system attacking the body, okay? And it has a very high frequency in Northern Europe, right, including Denmark. And it's been a bit of a mystery why. How can it be that this autoimmune disease has this high frequency there? And if you track some of the genetic variants responsible for increased risk of multiple sclerosis, you can actually follow them and you can see, well, they're deriving from Yamnaya, from the Pontic Steppe. You can also see approximately when they originate, around 5,000 years ago. what was a bit surprising is what we can also see is, well, they are actually under positive selection, both on the Pontic steppe, but also after Yamnaya gets into Europe. Positive selection, what does that mean? It means that back in the day, they were beneficial for survival and reproduction. People with these variants had a higher, you can say, survived better and got children that survived better, right? Which is, of course, you wonder, how can that be, right? It's hard to see what's the benefit today, you know, getting multiple sclerosis, right? But that's what you can see. So you can really follow, and this is just one example, you could do this with many diseases where you can say, where you know something about the genetic of the disease risk. You can start tracking it back, right? And in principle, you should be able to do the same in Asia. But what it demands is that you have a database like the UK Biobank, right? Where you can really go in and say what is, you know, which is mainly based on GWAS data and stuff like that, right? But then you can actually do these things. So why, let's get back to why do we find positive selection for these traits that gives multiple sclerosis today? Well, to get to that, I need to go into very briefly here in the end, infectious diseases, right? So infectious diseases, we generally thought was something that really, you can say, epidemics was something we saw in medieval times, right? Because the general notion was, well, before that, we don't have enough people in the cities and enough exchange, so we can really get these things spreading. And it was a huge surprise for us when we discovered by that looking at teeth, the cementum of teeth, that you're not only getting the DNA of the humans from where the tooth came, you're also getting the DNA of the bacterial pathogens and DNA viruses that these people were carrying at the time of death. We haven't been able to get RNA out, but DNA viruses, right? And, well, we saw that, you know, in the Bronze Age, right, during the Yamnaya times, I think it was approximately 10% of the skeletons we looked at was infected by pestis, which gives plague, right? So thousands of years earlier than anybody thought, right? And when you then start screening all these skeletons for these diseases, of course you found out that, well, what we thought was very different, right, from reality. For example, if you take things like hepatitis B, which is a disease people even die from today, and massively numbers get infected, well, some people had suggested it had only been in Europe for 500 years, right? We find it almost 5,000 years back in time, right? And we see things like smallpox, right? That's actually the Vikings, the bloody Vikings, they spread that all over the place, right? When they were traveling. The oldest evidence of smallpox, which has been one of the most deadly infectious diseases in human history, right, was really spread by Vikings. And if you take some of all these strains from the past and put them into phylogenies of present-day diseases, it completely changes the mutation rates of these diseases, right? So before we only looked at strains, you know, covering the last maybe 50 years or something, and then people looked at mutation rates, right? But if you bring in those, it changes everything. And in reality, it tells us something about what we will expect in the future, because it tells us how were these viruses and bacteria, what mutations did they carry and were successful, right? So it's only a matter of time. If something has been successful in the past, most likely before it returns again. So it actually gives you an opportunity to understand, well, do our current vaccines cover what might happen in the future, for example, right? And you could even make experiments if you dared after the COVID epidemic. You could even make experiments where you actually put them in to revive them and stuff like that. But I don't want to go there at this time. But back to multiple sclerosis and that story, right? So if you take a lot of these skeletons and we screen them across time and space for these infectious diseases, what do we see? Well, we see, maybe not very surprisingly, that, well, infectious diseases has always existed as far back as our skeleton takes us, right? But what is quite interesting is that these infectious diseases that are jumping from animals to humans, and which are the ones we historically and also presently are very worried about. When do we see those? Well, we see the earliest evidence of these 6,500 years ago, which is very late, right? Because we have had domestic animals since 10,000, 11,000 years ago, right? And not only do we first see 6,500 years ago, we only see them kind of explode, become very common 5,000 years ago. 5,000 years ago, the modern day world of pathogens was formed, if you want. The ones we know from history books and all that. And where does it happen? It happens at the Pontic steppe, where we have Yamnaya, okay? So a logical interpretation of this with the variants that provides a higher risk for multiple sclerosis today is, well, what is it they're giving you? They're giving you a hyper-efficient immune system, right? That would allow you to survive a world of massive amounts of infectious diseases, right? And then you're, of course, carrying that, but when you are removing a lot of these infectious diseases, right? Well, of course, then you are sitting with a hyperimmune system that has nothing to attack, right? And starts to attack the body, right? So you can, by bringing some of all these types of evidence together, you can start trying to understand, you can say, the underlying reason for why there's these differences in disease risk. And I think, for me at least, a very important take-home message here is that, and this is what we see more and more, I think, from our data, is that things that we consider negative, right? It's like, oh, damn, you were born with this mutation that gives this increased risk of something. And you see, you kind of have a negative, it's like this, well, oh shit, right? But in reality, what it is an expression of is, well, it's not very good or it's bad for you in a certain environment. But in another environment, it's good, right? So instead of just saying, you know, well, we should all adapt to where we are, which I learned in school, you have to do what the teacher says, etc., right? You have to adapt to the conditions you are in, even though you hated it, right? Right? Instead, maybe what we should start thinking about is to say, well, to find the environment that suits you, right? That suits your genetic makeup rather than the other way around. So thank you very much for your attention.
Thanks a lot, Eske. I have a question with regard to the pathogens. As you know, that I'm also very interested in those. You focus on the steps and the enormous importance of the steps with these kind of human pathogen interaction. I was wondering if this is not also due to the fact that first, we have a lot of research done in this step, and there's a lot of very well genetic preservation. You know, us working a lot in the Eastern Mediterranean, where we have much larger communities at the time, but horrible DNA preservation. So with us trying to get pathogens from the dentine, it's almost zero chance. And when I look at these large urban centers that existed much earlier than 5,000 years ago in the let's say Eastern Mediterranean, Near East, I mean, these would be the perfect places of, let's say, humans getting in contact with diverse microbial communities, and also these close human-human interaction might have been crucial for spreading pathogens. And if you look in the early literature, it's all about medical recipes starting from the 4th millennium onwards. So I really ask myself if our focus on the relevance of the steps for this human pathogen interaction isn't something that is also due to the fact that we are missing relevant pathogenic data from the Near East.
Well, of course you can say, I will give you that missing data, I mean, we don't know, right? That's the short answer. If you don't have data, you don't know. And of course you can say, well, maybe that's the case. What I can say is we have a lot of samples covering also the time before the Yamnaya, right? Also in this paper. And there you don't see it, right? So yes, could there be a more complex scenario that we haven't uncovered, you know, where, let's say, they came from the south where we don't have enough samples and moved to the steppe? Maybe, right? It's hard to exclude if you don't have data, but I would say, based on the data at hand, I think it's the most, you can say, obvious explanation, based on the data in hand. Of course, it's how it is, right? If new data comes and it shows something else, you have to change your interpretation. But you would have to then have something coming from another place, getting into the step and somehow bypassing the other people living there, you can say, in the northern parts, right, before. And that's where I'm a little bit, I don't think that's, to me at least, a very obvious scenario, but who knows?
Thank you. I've got the microphone over here, so I'm going to go next. Harriet Buckley, Durham University. Hello, sorry, you didn't see my hand, but your colleague did. Yes, I'm Harriet Buckley at Durham University. Thanks for a really interesting talk. 2 questions, quite quick questions, possibly long answers. At the beginning of your talk, you said there's some kind of barrier between these 2 populations and we don't know what it is. Have you looked at what the ancient climate would have been like at that point and the river systems and so on? And in other aspects of your work, have you considered what the climatic conditions would be?
Yeah.
And the second question is much more modern day. In relationship to your thesis that you just elaborated at the end there around multiple sclerosis, which I found very fascinating, would you also then expect to see a coincidence of other autoimmune diseases, including long COVID, being concentrated in those populations?
Yeah.
Thank you.
Thank you. So for your first question, I mean, we are considering also climate to the degree it's possible. And I would say, well, for example, when we actually found this Bronze Age, you can say, plague epidemic kind of evidence, right? That was because we saw an enormous amount, in particular in Western Asia, of population replacements very fast after each other, right? And of course, the first thing we thought about was climate change, right? And you go in and look in the record and you don't see anything obvious, right? And then it was actually an archaeologist, Christian Christiansen, who said, well, couldn't it be infectious diseases, right? And all of us natural scientists said no, because that's way too early. But then we said, okay, let's look, right? Because we're not medical doctors, the only thing we had heard about was plague epidemics, right? We all heard about that. And then we looked for that, and it just came out, right? And of course, as soon as that happened, you were then screaming for the rest, right? But yes, so I don't think it's climate. I mean, I've talked with, of course, we've talked with our archaeological collaborators that believe at least that there is some kind of cultural differences. How well, you can say, how well supported that is, I don't know. But where they claim that, you know, there's evidence of warrior societies and stuff like that on the east side, which is not on the west, right? And maybe it is a bit of a mystery to me, right? Because normally what we see in general, I would say, is when people are living close to each other, they have sex one way or the other, right? That's basically what we see. So there is something weird about this divide. In terms of other autoimmune diseases, yes. And of course, we're looking into this, and that exactly seems to be the case. Exactly what you suggest, yeah.
There is a question by Don.
Yeah, the Vikings also made it to Newfoundland. And is that completely irrelevant? Is there anything from genetics left of that fact?
Of what?
1,000 years ago in Newfoundland.
Oh, of Vikings or?
Yeah.
Yeah, so, I mean, I think there's very little doubt that the Vikings, you can say, reached Newfoundland, right? So you have found you can say the dwellings, if you want, of them. The problem is that there hasn't been found any skeletons in America of Viking age, of Vikings. And I actually, as part of the Viking study, I contacted, you can say, the ones responsible for these houses in Newfoundland and asked whether I could go in and take dirt samples from the soil of the floor, because we can retrieve DNA directly from the sediments, right? It's a different talk. I didn't cover it here, but unfortunately at that time they at least said that it was kind of closed and we couldn't get access. But that's the only way I can see we can really, unless somebody at some point uncover a skeleton. What we can see, because there's been found skeletons, is in Greenland, of course, the Norse. And the Norse seems to be largely coming from Norway. I mean, it's from probably through Iceland, but it's Norwegian, you can say, in ancestry that are going there. And what is quite also surprising is that, of course, because the idea is that it's the Greenland Vikings that are reaching North America, right? Then we thought maybe we could also look, or maybe there would be traces of Native American or Inuit or Paleo-Inuit DNA in the Norse, in the Greenland Viking skeletons. After the meeting, we don't see anything. I mean, and which is kind of interesting because anywhere else they're going in Europe, they mix a lot with the local population, right? But when it comes to, you can say, these indigenous groups, we just don't find evidence of it.
There is one more question.
Hi, so my question is probably naive, how long is a piece of string type of question. How quickly does positive selection take? And I'll give you a specific example. People in Tibet,
yes,
who live at altitude, they have a strong advantage of having a mutation in a gene called EPAS. And people living in the Andes don't have that, but they've still been living there for a very long time. So how long does it take to acquire something which is unambiguously an advantage?
Yes. Well, how long it takes, of course, depends on, you can say, the selective pressure, right? How strong is the selective pressure? An example of a very fast selection that we have looked at was, and which was a surprise for us, was when we looked into these sea divers in Southeast Asia, right? The Bantu that are kind of living, you know, traditionally at least, on a boat or in the water, right? And they get seasick when they get into land. And this is a lifestyle that are believed to only have existed for 1,000 years. And if you go in, both look at their spleen size first, it's like 50% larger than the closest relative on land, right? And if you look at selection, positive selection, you see massive selection in the diver, anything to do with diving, right? I mean, spleen size, red blood cells, diving response, all these things. And of course, we were super surprised. I mean, I have to say, we were very surprised because we thought, well, it's way too little time. But then the elder Bantu basically, in the oral tradition, whether it's true or not, I don't know, but they said traditionally when a baby was born, they basically put a string around the legs, right, and the arms, and then they were taken underneath the boat and up. And if they survived, well, they survived. If they died, right? And of course, if that's the case, that's a massive selection pressure, right, on the population, right? So that potential, I don't know whether I could explain it, but it's very interesting relative to hypoxia, right? Because it's acute hypoxia. So it's different from this, what you are talking about, which is kind of, you can say, not acute hypoxia, it's also hypoxia, right? But and there's a lot of interest in this because of, for medical reasons, when you do surgery or whatever, right? If people have a high risk of going into hypoxia or not. But that's at least, that sometimes it can happen very, very fast under the right condition.
So, Eske, I think we have to move.
Yeah, sure. Thank you. Thank you.
This session will be Yvonne Buckley. She's from the Trinity College Dublin, and she is co-director of the Co-Center of Climate, Biodiversity and Water, and she is directing or involving 14 institutions from Ireland and Great Britain and Northern Ireland. So she is an ecologist, and she has really a voice in decision making, which is involving climate change and biodiversity and other processes which are required to understand how animal and human population or plant history is evolved, and she can give also the molecular basis for this one and can give some explanation. Sorry, I lost my voice, I cannot speak anymore. So Yvonne, if you can come and take over the floor.
Thank you very much. It's a great pleasure and privilege to be giving the talk here today after such a fascinating series of talks that I've seen. Does that work? Yay. Okay. Thank you. It is a great pleasure and privilege to be giving this talk here today after a fascinating series of talks this morning. And I'm going to talk to you about biodiversity in a warming world. So it's the intersection between biodiversity and climate. Okay, so as Éva was saying, I'm a co-director of this co-center for Climate plus Biodiversity and Water, where I'm lucky enough to work with nearly 100 different researchers across 14 different institutions on the islands of Ireland and Great Britain. And it's a new funding mechanism which has enabled us to come together. And I'd just like to acknowledge my co-director Mark Emerson at Queen's University Belfast and Professor Ed Hawkins at the University of Reading, as well as our Deputy Director Andrew Parnell. And just to give you an idea of the interdisciplinary nature of the co-centers, myself and Mark are ecologists, Ed is a climate scientist, and Andrew works in AI and meteorology, amongst other things. So we work with social scientists, ecologists, climate scientists, hydrologists, and a range of other different disciplines. And it also has this unique co-leadership model as well, which I really enjoy. So I just want to kind of position myself in what I do to give you an idea of where I'm coming from. I'm now, I guess, quite interdisciplinary, but I trained originally as an ecologist and a quantitative ecologist. And I've grown more and more fond of investigating the ecology of nature and people's interactions with nature. So my skill set's in fundamental ecology, but I've worked in agroecology, forests, freshwater, zoos, anthropology, human behavior, technology, ecosystem management, conservation, and restoration. And currently I have a strong interest in shaping policy in the areas of climate and biodiversity and water. Okay, so I'm going to talk today about using ecology to do two things. First of all, to understand the effects of global change through the lens of genetic diversity, using my favorite model species, demography, land use change, and climate. And then the second part of the talk is really about how we can develop effective solutions to the really huge challenges facing us in society, and what kinds of management options we have available to us, and how we engage with policymakers. And I'm using Ireland as a case study there. So just to start, I'm not here to convince anyone that climate change is real or that the biodiversity crisis is upon us. Both of these are very, very well documented through reports from the IPCC for climate and the IPBES, Biodiversity and Ecosystem Services part, for biodiversity. And I guess traditionally there's been a bit of a siloed development of these two fields, with climate scientists working over here and biodiversity scientists working over here, with a bit of crossover in between, but it hasn't been very systematic. Luckily, this IPBES crossover workshop report here did some really great work in highlighting the importance of considering both biodiversity and climate change together. And that came out a few years ago now, but the integration of biodiversity and climate in terms of the science that we do and the research that we do, as well as the policies that we make, is critically important for solving both. So there are shared drivers of both the climate and biodiversity crises. We have invasive species, direct exploitation and overharvesting, pollution, and land and sea use change really driving biodiversity change and biodiversity loss. And then we have pollution and land and sea use change both contributing to climate change. And then we also have interactions between, as the climate changes, it affects biodiversity, and also as biodiversity changes, because of feedbacks through the Earth system, it affects local climate and ultimately global climate as well. So we not only have shared drivers, we have shared solutions to both of these. We can think about restoration and nature-based solutions, so restoration of habitats and ecosystems, and nature-based solutions where I'm going to talk about them a bit more later, so I'll leave the definition for then, but it's things like planting planting trees and urban drainage systems and things like that. Afforestation, you might think, would be great for biodiversity and great for climate, but there's real problems with afforestation. This is putting forests where forests have traditionally never occurred. For example, in grasslands, in ancient grasslands, that can actually reduce biodiversity while contributing positively in terms of solutions to climate change. So there are some trade-offs that we need to be aware of. And then we have sustainable food systems, and we've already heard over the last couple of days about the importance of sustainable food systems for addressing climate change, but they're also incredibly important for addressing biodiversity change and loss. Things like pollution, land use change from unsustainable food systems are really the main drivers of biodiversity change and loss. So we can see, hopefully, you're convinced about why I'm interested in looking at both of these two things together. And now we move into a couple of kind of like case studies to show you what we're doing in this space. So I'm interested in understanding the effects of multiple aspects of global change. And I'm going to tell you a story about admixture and how climate shapes genetic diversity in a really interesting plant species. And then I'm going to talk more generally then at the macro global scale about how land use and climate compare as drivers of species distributions. Because you often get a narrative around climate change. Obviously, climate change is going to change biodiversity because plants will either not be adapted to new climate conditions and go extinct, for example, or they will adapt very slowly, or they may adapt, but it may not be fast enough to keep up with the pace of climate change. So climate change is predicted to have very significant effects on biodiversity. However, land use change is also a very significant driver of biodiversity change. So we were interested in evaluating the size of those effects. Okay, so this little guy down here is called Plantago lanceolata, and I guarantee that in pretty much any patch of grass that you can find outside your house or in a playing field or wherever, you will find this little guy, and probably in quite some numbers. It's probably one of the commonest species in the world, which is really exciting because it occurs all over the world, which means it can occur in a range of different climate conditions, from the subarctic all the way through to the subtropics. So it really lends itself, I think, to an understanding of how this little unassuming plant manages to cope with such a wide array of different climatic conditions. So about 10 years ago, together with some ecologist colleagues, we set up Plant PopNet, which was a team science project to look at the population dynamics of this plant across a range of different climates in a range of different contexts all over the world. So all these circles that you can see on this map here are our sampling sites, and then the blue purpley shadows are where the plant actually occurs. So you can see that we have sampling sites in Australia, New Zealand, throughout Europe, and North America. We're lacking, I think, some in North Africa. It'd be great to get them some there, and over here in the really eastern part of its range. But we're doing pretty well. We have it in its native range, which is Europe and Eurasia. So that's these pink dots here. And then we also have it where it's been transported by people relatively recently to North America, Australia, and New Zealand in its non-native range. And that will become important in a minute. Now, because it's a team science project, we're all doing this research in our backyards, which makes it a very sustainable research project. Nobody is flying anywhere to do this. And then we put all the data into one place, and we curate it at Trinity College. So all of these lovely people here and more collect the data for us every year, where they go back and census individual plants in the same plots every year. And we're now up to 7 sites with 9 years. That was a little while ago. I've actually got up to 10 years now in our data set for multiple sites. So it's the most spatially extensive and temporally long-lived plant demography data set in the world, which is super exciting if you are a numbers nerd like me. So what do we do with all these numbers? First of all, we can look at a global map of climate. So we have the mean annual precipitation here, and we have mean annual temperature here. And then in these kinds of, kind of greeny, gray, bluey areas are different kinds of ecosystems that occur throughout the world. And all of this smear of purple and pink points are where Plantago lanceolata, ribwort plantain, lives. So you can see that it covers a whole range of different climatic biomes, from boreal forest through to tropical seasonal savannas down here. So it really is a jack of all trades when it comes to climate. We can look at these plants in the field, the good old trusty quadrat approach. We can bring them into common garden experiments in the glasshouse to look at adaptation and phenotypic plasticity. And we can obviously extract genomic data as well and look at all kinds of interesting things about where they've come from and how they get moved around the world. Okay. So we call this a population macroecology approach. It's macro because we're taking a bird's eye view of the entirety of the species range across the world. And it's a population approach because we're looking at local site demographic data at this global scale. So scale is really, really important. And we are, I guess, leveraging the very, very fine-grained, detailed work that we do at the site level. We're leveraging that up to a global scale by including many, many of these sites all over the world. And that gives us new insights. So the first piece of work I'm going to talk about is by Annabel Smith, who's now an assistant professor at the University of Queensland. And we were interested here in genetic diversity, so genome-wide genetic diversity in this species. We came up with an a priori model for how genome-wide genetic diversity might come about. There are obviously environmental and ecological conditions that affect the demographic performance of a population, that affects effective population size, that affects diversity. And then there's also this human activity element. So humans move this plant around really commonly. And in fact, it has some links with the previous talk because Plantago lanceolata occurs wherever humans go. A congener, a closely related congener, is called white man's footsteps in North America because the Native Americans noticed that wherever white men went, this plant would pop up. It gets transported in animal feed. It gets transported on livestock. It sticks to their fur. And it gets transported anywhere where the early farmers went, which was very interesting. So this is what the genetic diversity... Oops. Oh, no. Okay. Don't know why that skipped so much. This is what the genetic diversity looks like. So here in Europe and Eurasia, where it is in its native range, you can see that every color here is a different kind of genotype. So we have these kind of North Atlantic blue genotypes. We have these continental Europe yellow genotypes. And as we move more south in Europe, we get more diverse genotypes down here, which are mixtures of blue and yellow and green. And over here in the east, we have this pink genotype. And it was very interesting, the previous talk talking about an east-west divide. Unfortunately, we don't have anything further east than here. So it would be really interesting to get some more easterly genotypes to see what's going on there. But you can see that when it gets moved to North America, to Australia, to New Zealand, it's this green and blue genotype primarily which gets moved. And even here down in South Africa, it's a greenish genotype. So even though lots of different people took this species to these different places, a certain combination of genotypes seems to have done very well when you move it away. So that was interesting. But there's also higher genetic diversity in these within a non-native population than there is within a native population. So here in Ireland, we only have one blue genotype. That's all we get. But over here in New Zealand and Australia, the blue genotype is combined with the green genotype and the yellow genotype and a bit of the pink one as well. So we knew we were going to get higher genetic diversity in the non-native range. We were really interested in figuring out whether there was any climatic signal to genetic diversity. So we looked at different measures of climate, like temperature, seasonality, and precipitation. I'm just showing you these two here. And this is neutral genetic diversity, and then this is adaptive genetic diversity. And what you'll notice from all these graphs is that the red line is always higher than the black line, and the red line is the non-native populations. So this pulling together of moving of lots of different kinds of Plantago from the native range into the non-native range has led to much higher genetic diversity. The other thing you might notice is that the black line goes up, it goes down, and the red line tends to have a much shallower slope than the black line. So the native populations seem to be much more strongly structured by the environment, by these climatic variables, than the non-native populations. So we have admixture in our non-native range. It increases population genetic diversity, but this same admixture weakens environmental structuring of adaptive diversity in particular. So we're seeing the breakdown of this climatic structuring of genetic diversity as the plant gets moved around and combined with other genotypes. Okay, so when we move species around, we create new genetic associations, and they're exposed to new selection pressures. So that's very interesting because we have this, we have two intersecting elements of global change. We have the movement of plants and animals around all over the world, and then we have climate change happening on top of that. And what we're actually seeing in Plantago is that you have a higher genetic diversity, particularly in those adaptive loci, which may actually enable the non-native populations to adapt faster to climate change. However, this admixture during the introduction process can weaken genetic diversity climate associations. So it'll be very interesting to, I think, do climate change experiments on these different genotypes in the lab and see how they see what happens. Okay. So moving on, I'm going to now take you away from the just one species approach, so we can learn a lot by looking at model species, and now just kind of zoom out to, now we're talking about lots and lots of different plant species, and we're talking about them occurring all over the world in different kinds of land uses. And this is a very classical macroecological approach. We use the PREDICTS database, which has been put together by a large collaboration team led by Tim Newbold in the UK, which looks at plant occurrences in different land uses. And this is the part where we were interested in comparing the effects of climate to the effects of land use change as drivers of plant occurrences and abundance across life forms. And we were interested in which one was bigger, basically climate or land use, as a driver of plant occurrences. These are the global biomes shown here. That's how climate is distributed from a plant's eye view. Those are areas of the same color, have got similar plant climates. And this work is done by Dr. Caroline McKeon in my lab. Okay, so in order to look at this question, we used a neat trick or a neat feature of plants. Plants occur in lots of different life forms, from trees all the way through to aquatic plants, and they have different sizes and different longevities. But importantly, their growing tips are in different places. And a Danish botanist back at the end of the 19th century, Roncaer, classified plants into lots of different groups depending on where their growing tips were and according to what kinds of climates they could survive in. So we knew that this classification system for plants relied really heavily on climatic associations. So we thought this would be quite a strong test to see whether land use would have a similar effect to climate when we know climate is structuring where these different plant life forms can live. So we took Roncaer's life forms, we looked at all the species in the PREDICTS database, and there's thousands of species in there. We looked at species occurrence and species abundance according to what life form that species was, what the climatic variables were, and what the land use was. And importantly, we looked at the interaction between life form and climate, and the interaction between life form and land use. So we were interested in how land use affects different kinds of life form occurrences. So here, if we just concentrate on one land use, this is primary forest. And I'm absolutely delighted to tell you that trees occur much more commonly in forest than little tiny annual herbs. So as an ecologist, it's great to get a positive result like that confirms your view of the world. Here in urban areas, we see the little weeds, the little short-lived small weeds here doing very well in urban areas. But our trees also do reasonably well in urban areas, or surprisingly well in urban areas, because we plant them there, we put them there. So we can look at how different life forms are distributed within a land use, and then we can look at how the life form is distributed across different land uses. So if we follow our trees here, you can see that they occur in primary forest in secondary, in mature secondary forest, in intermediate secondary forest, and then they start to go down as you get into these more intensive land uses like pasture and cropland, and then they come up a little bit again in the urban areas. So we can look within and across land uses about how these plant species are distributed. And then we can look again at how our life forms, the trees and the herbs and the things in between, are distributed according to precipitation and according to temperature and temperature variation. And we can quantify the distance from the average of what we'd expect for these different life forms, and we can quantify those and compare them. So in orange here, we have bars representing the effect size of land use, and in purple, the effect size of temperature. Now the temperature effect, land use is categorical, temperature is continuous, so the temperature or precipitation effect is the effect of 1 standard deviation change in temperature or precipitation or variability in those things. And a 1 standard deviation change in mean temperature is around about the same as moving from one biome to another, of moving from boreal forest to a grassland steppe type environment. So those are very large climatic differences. And what we see is that the effect sizes of land use, differences in land use, is about equivalent to, these are the effect sizes here on the x-axis, is about equivalent to the effect sizes that we see of a biome to biome difference in climate. So land use change is having a massive effect on what kinds of plants can occur where, and it's equivalent to moving from, forest to grassland. So, in terms of climate. So this led us to conclude that human land use is comparable to climate as a driver of life form occurrence. This is something I think that as an ecologist we kind of knew, but nobody had ever quantified it before, and it's a really useful measure of how profoundly we are changing ecosystems. And human activity itself is a biogeographic force. So this is where plants would occur without humans, these biomes, and as humans come in and change the land use, it's overlaying that with an equally effective effective is a bit of a positive word, but yeah, it's overlaying that with a land use filter on top of that. So land use is very, very important. We know it's a driver of species loss and change. Climate action, however, is critical for reducing the impacts of climate change on biodiversity, which we know are going to be profound. Some species will do well, and some species won't, and we'll lose a lot. However, the effects of land use change due to climate action may be more significant for biodiversity than the effects of climate change, at least in the short term. So the kinds of things we're doing in terms of the energy transition, solar and wind, offshore as well as on land, can have quite important changes in land use associated with it, which we know will change what kinds of plants can occur in those places. So land use change for climate action can be positive for biodiversity, or it can be negative for biodiversity. And climate action that degrades biodiversity is just not a sustainable option, particularly over the scales of the transition that we're going to have to put in place. So I'm not using biodiversity here to say we can't do climate action. What I'm saying is that we have to do we have to do climate action, taking biodiversity into account, and there will be hard choices to be made along the way. So these shared drivers and feedbacks mean that both need to be tackled together. And this is where the developing effective solutions part of my talk comes in. And this is where engagement with policymakers and providing the evidence to be on the table when policy is being made becomes so important. So this is just a little vignette. This is an image from COVID times when I was giving evidence to an Oireachtas committee. So this is a government committee which was developing our climate bill and coming up with our national climate objective. And I was asked to give evidence on the role of biodiversity in the climate bill. And this was really my first experience of giving policy advice at this level. So when the climate action, and I gave verbal and written evidence and defended myself against, defended my position against questions from the committee members. And then when the Climate Action and Low Carbon Development Amendment Act, the snappily titled 2021 legislation, which guides climate action in Ireland, came out, it was really great to see that biodiversity is actually embedded in the national climate objectives. So this is to pursue and achieve no later than 2050 the transition to a climate resilient, biodiversity rich, environmentally sustainable and climate neutral economy. Yay. I would love to live in that place. Let's see if we achieve it. So that was great. And there was lots of mentions of nature-based solutions in the legislation as well. And just to say something about Ireland, it is a very flat kind of society. It's not very hierarchical. The reason why you can get things like this, changed in legislation is that you can actually ring, you can pick up the phone and ring a minister. You can talk to people. It's a small place, and that really facilitates well-informed policy making. So we were then working a lot in this space, and this is Courtney Gorman here, and we were commissioned to write a report by the Climate Change Advisory Council on how climate and biodiversity solutions might interact. So we came up with 6 recommendations for win-wins for climate and biodiversity action, which included restoring carbon-rich ecosystems, which in Ireland really means bogs, promoting agroforestry, natural capital accounting as an enabling activity, integrating solar into the built environment first. We need to stick it on rooftops first before we do utility-scale solar in the wider countryside. Increasing offshore wind capacity. We think that there is a way, there are ways of combining offshore wind with positive or at least not too negative effects for biodiversity. And then afforestation, but with native trees in particular, and focusing on a restoration type of approach. So that was an important piece of work that got us started on the road towards thinking about more climate and biodiversity focused activities. And more recently, we've been again commissioned by the Climate Change Advisory Council to formally assess biodiversity as part of our carbon budgets process. So in Ireland, climate action is guided by legislated carbon budgets, which set certain amounts of carbon that can be emitted over time in line with EU targets. So we prepared this paper to really investigate how the different activities that would give rise to compliance with our carbon budgets might affect biodiversity. And then finally, another report that was commissioned by the Climate Change Advisory Council was on nature-based solutions for climate action and ecosystem restoration, where nature-based solutions are actions to protect, sustainably manage and restore natural or modified ecosystems which address societal challenges, such as climate change, by providing, while simultaneously providing human well-being and biodiversity benefits. So a long-winded definition, which I will give you in short form in a minute, but we were able to identify examples of 81 different nature-based solutions all over the country, covering about 5% of the land area of the Republic of Ireland, that contributed to climate adaptation and mitigation activities. So there really are quite a significant, potentially quite a significant tool that we can use. So for example, we have adaptive nature-based solutions such as this drainage scheme here, which provides for a drainage pond beside a road, which prevents flooding or copes with the more intensive rainfall that we're going to get, that we are getting. Here we have a restoration of a woodland habitat to sequester carbon and protect biodiversity or restore biodiversity at the same time. And here we have a peatland restoration plan here, which is both adaptive and mitigative, because it can hold back floodwaters, the bogs can absorb these intense rainfall events much more easily when they're restored, and it also is good for biodiversity and good for keeping the carbon in the bogs. Just a few more examples here. These ones are particularly good for biodiversity, such as the Galway Bay native oyster restoration projects, so we could do restoration projects in the sea. This one is close to my heart because that's where I come from, looking at shrubs and diverse shrubs and hedges as buffers. And then we have the Burren Life. This is where I've done a lot of my fieldwork, the most biodiverse place in Ireland, which has been, I guess, post hoc labeled as a nature-based solution. And it's very interesting because it keeps farmers in this landscape. It is a farming farming or human-generated landscape, and it's the most biodiverse place in Ireland. So it just goes to show that conserving biodiversity does not mean not working with people. It doesn't mean locking it up. In a lot of cases, particularly in Ireland and many other very modified ecosystems, it involves working with people to manage those ecosystems. So we then provided a range of different recommendations to policymakers on these nature-based solutions, including, we need a simple, comprehensive, and shared definition for nature-based solutions that policymakers get, because they don't understand nature-based solutions, they don't get it. We need to build that evidence base for the function and benefits of nature-based solutions, particularly as we try to scale them up. All of those 81 different projects really were pilots. They haven't been scaled up. And that's what we need. We need to rapidly scale up the use of nature-based solutions. We need to integrate them into policy frameworks. And we need advisory programs for the application, the monitoring, and the evaluation of these nature-based solutions, in the same way that we provide advisory programs to farmers for how to manage their land to be more productive. And then through the Co-Centre for Climate plus Biodiversity and Water, we really are working at that level of building the evidence base for the function and benefits of nature-based solutions through all kinds of activities to do with restoration. And then to solve the definitional problem, or to make it more easier to understand, this little kind of triple helix or triple circle diagram here is one that we put together for this special feature in Journal of Ecology on the plant ecology of nature-based solutions. Basically, nature-based solutions are good for the climate, good for people, and good for biodiversity, and that's where they sit. And then there's other kinds of systems which are, good for just two of those. So if you can hit the good for the climate, good for people, and good for biodiversity, you've got a nature-based solution. Much simpler definition, easy to get. So hopefully that's shown you how we can move from very fundamental, seemingly, abstract, and why does she want to know about the genomics of this weird little plant that occurs everywhere? We can move from those kinds of very fundamental ecological concepts and ideas and data all the way through to policy making. And I think it's really important that everyone, no matter what your disciplinary background is, there's space for thinking about climate change, thinking about biodiversity, and helping to make the world that we are all going to be living in, hopefully, over the next 20, 30, 40 years. Because if we think about 2050, when we are supposed to be in a completely defossilized, climate neutral economy and society, it's only just around the corner. It's only 26 years away. So I'm excited to be able to contribute to that, but it's a huge challenge, and I think we need more people working on it. So thank you very much, and thank you also to my colleagues. Oh, sorry, can you just stick up that last slide? I had one more slide. Thank you. I just wanted to leave you with this nice image here of Trinity College Dublin lit up with the climate stripes, and Ed Hawkins, my collaborator in the Co-Centre, obviously generated the climate stripes images. This is Ireland, which shows you going from cooler temperatures all the way back here, and time runs this way, to our much warmer and hotter temperatures here that we're experiencing now, and which are only going to get hotter. We're going to get hotter and wetter and more variable. So thank you very much for your attention.
Some time for a few questions. Yeah, there is one question there. Please give the microphone.
Is that me? Yeah. Thank you so much for this very, very interesting talk. One thing I wanted to ask you about, and maybe I just misunderstood it, but the map that you showed of the diversity of the species that you followed, I will not try to pronounce it, but you mentioned that even from the Native American populations, that was a species that they called kind of like a marker of the white men being around. And when you look at the map, actually, the colors match very well the primary colonizers. So if you look into the America, you have mainly southwest West Europe, green color, as I noticed, and Australia is green, but also blue, which is the UK.
Yep.
Is that?
Yeah.
Yeah.
And actually, yeah, so I think you're right that some of those colors do reflect who moved it out of Europe. And it was the North Europeans going, and particularly the blue, which was the islands of Ireland and Great Britain. That element was much stronger in New Zealand than it was in Australia. And I think, you know, there's again, you can see that the footprints being reflected in the genetics. And in another species that I studied, looking at the population genetics of another invasive species or non-native species, we saw it even more clearly, where even down to the fact that the populations in Chile were quite different to the populations everywhere else. And it was only after talking to the people, my collaborators in Chile, that they said, oh yes, of course, because, you know, there was a lot of German immigrants that came into Chile, and we found this weird German genotype was only in Chile and nowhere else in the non-native range. So we really do see the footprints of human migration through plants.
So following that, do you think that this is a new tool for us to look into where people
I would love people to use plants to reflect, and I think Plantago lanceolata is a great example of how you could use that to look at the migration of people through Europe, maybe combining it with the human data would be super interesting.
Thank you.
Thank you.
Give them meanwhile, maybe I will ask you, what is the secret of this plant? So what is the secret of this robustness, that it can work and grow everywhere?
Yeah,
it would be interesting to know.
Oh, absolutely. And when we bring all these genotypes into a common environment, we bring them into like a common glasshouse environment, and we can do experiments with them. They are incredibly phenotypically plastic, which means you can, you know, they'll change their shape, they'll change the way that their life cycle operates in response to environmental conditions. So I think that the kind of the easy answer to your question is they're just masters of change, and they can, you know, they can alter what they do and how they do it. Now, what the genetic mechanisms for that are is really interesting, and that again would be something that I would love people to have a look into, because if we can, you know, engineer in the this fabulous ability that Plantago lanceolata has into other kinds of plant species, that would be something that might be quite attractive and useful. Yeah.
Thank you. I just follow in some way question by Jacek, and actually your remark about the plants and migration, I think the Professor Eske would answer that, of course, in the past you can trace the mobility. So migration is a subset of mobility, how people move through for example, bananas and others. So there is like kind of archaeology which look at that. But what I want to ask is whether in your project you look at the loss of biodiversity and the loss of cultural diversity, how they could be connected, because that's come to this question if there is through colonization, certain plants were spread, and that also connects to the loss of cultural diversity, which might be connected, and certainly yes, is with the loss or change of biodiversity. And they are now projects where the indigenous people basically restore the old seeds and so on. Anyway.
Yeah, no, fascinating. And I know that there's been studies of linguistic diversity and biodiversity together, and show that some of the same drivers of biodiversity are also drivers of linguistic diversity. The creation of, you know, barriers in the landscape that isolate human populations leads to linguistic diversity, for example, and those same barriers in the landscape, like high mountain ranges in New Guinea and things like that, can lead to the evolution of, you know, isolated populations of animals and plants that become their own species eventually. So there's definitely common drivers, I think, of linguistic diversity and probably cultural diversity, as well as biodiversity. And then by extension, you would expect, exactly as you're saying, that some of the drivers of that loss of cultural diversity may also be the same drivers that impact on the loss and change of biodiversity as well. And I can see that Eske has his hand up. So do you want to respond to the first part of the question? Oh, right, sorry. I thought it was in response to that one. Yeah.
I was just, I mean, it was very interesting, this about land use being, you can say, a major driver for human land use, right? For decline in biodiversity. And I assume, I don't know, but I assume this is mainly agriculture, right? And so what is it specifically about agriculture that reduces the diversity? I assume it's it's because of change in competition. But is it, I mean, between, you can say, crops and natural species, but is it pesticides who is the main driver? Is it fertilizer? Is it, you know, have people, is there kind of a common reason? Because that would be another way to go in and attack that issue, right? Or deal with it.
Yeah, I mean, fundamentally, the intensification of agriculture is about getting rid of diversity. It's about creating a system that can be easily managed and with very specific inputs. So it really is a system that's designed to be as least diverse as possible in order to reduce space-to-space variation and temporal variation in the productivity that you're achieving. So it's designed per se to get rid of your diversity. It didn't always have to be that way. It certainly wasn't that way in the past. And now we're seeing an ecological intensification of some farmed landscapes where we're putting the diversity back in order to get the kinds of benefits for pest control that we know that biodiversity brings by putting in flower strips and increasing our field margins and restoring hedgerows to bring, you know, the pollinators and the natural predators of pests back in. So as we, are developing problems with the inputs, the pesticides, there are problems associated with those which we are recognizing, and we're trying to engineer them back out of the system. We're trying to engineer fertilizer kind of out of the system because of the climate change effects, as well as the water, very important effects of fertilizer runoff on water. As we start to take those, dial back those intensified inputs, we need to dial up the ecological intensification in order to get the benefits of diversity back into those farming systems. So I know that in Ireland, the organic farming sector is the fastest growing farming sector at the moment. It doubled in the last 2 or 3 years. So, we really are trying to diversify the farming system as we dial back on those intensive inputs.
Thank you.
Yeah.
There is a question here.
Yes, thank you for your talk. I have one question. So it's so logical what you're explaining to us. So the question is how to bring it to the people who are responsible for changing the land use, so which are quite a lot. I mean, these are not only the farmers, but these are also people who are working in the local authorities, for example. How are you going to do this? Because I haven't seen that in your plan of measurements, this reach out to these people so that they have this knowledge.
Right, so I have a great example of that, and this shows you how small and connected Ireland is. So we have a general election on Friday, and the candidates are all coming around and knocking on doors. And my husband says I must be the only person in Ireland who gets excited when a candidate knocks at my door, because I run out there and I have my asks, straight in front of me. And I'm like, what are you doing about nature? What are you doing about climate change? Have you considered this? Have you considered that? So I was talking to one of the candidates, and I suggested, look, what we really need here is we need to move the National Parks and Wildlife Service, which is concerned with biodiversity, into the same department as water and forestry. And we need to have like this integrated system. And she was like, oh, that's really interesting. That's good. And I said, look, if you get anywhere close to government, that's what needs to happen. That would really be a game changer. She said, oh, great. Okay, excellent. I'll take that back. And she's standing for election. And then I was at a climate and biodiversity hustings organized by one of my colleagues in the co-center, where they brought representatives and leaders of all of the political parties who are willing to turn up, which is most of them, and asked them questions about climate and biodiversity. And the leader of the party for the candidate that I talked to at my door, when they were asked the question, what needs to change, she said, oh, we need to bring the National Parks and Wildlife Service into the same department as forestry and water. And I was like, yes, talk to people. So that's the solution. We need to talk to people, and we need to get people talking to their elected representatives about the things that matter to them. We consistently hear in Ireland that climate change matters to people, that biodiversity matters to people. But when they're on their doorstep talking to a politician, they talk about housing, they talk about health, they talk about their children's future in terms of housing and health. They don't talk about their children's future in terms of the world they're going to live in, and how they're going to survive and do well and thrive in that world if the climate is a disaster and if we've lost all of our natural ecosystems. So I think we need to get those messages onto the ground, get people talking to candidates about that. And part of the remit of the co-center is that we have a strong education, public engagement and policy element, and we actually have a policy response unit which is philanthropically funded, which will bring us more closely together with policymakers. So for example, we have a scheme at the moment where we are developing projects where PhD students will have internships in departments, in government departments with the public servants for 2 or 3 months during their PhD training. So that way we can embed the scientific knowledge into those departments, but we can also learn what the challenges are of the policymakers, and that will be brought back out again. So I think working with philanthropy, working with government, working with industry are all critically important for getting the message out there into as many sectors as we possibly can. Thank you.
So thank you very much for your talk. It was really wonderful, and we are running out of the time, but I think it was so exciting that we allowed more questions, but maybe our session will be a little bit longer. So the next speaker will be Professor Botond Roska. He is an MD who received a diploma at the University Semmelweis in Budapest. Then he got his PhD in California, Berkeley at the university in neurobiology, and then he studied genetics and virology at the Harvard University. He had a research group at the Friedrich Michel Institute in Basel, and now he is director of the Institute of Molecular and Clinical Ophthalmology. And his research now on how restoring vision is really an unsolved question, and he has really very promising way how to solve this problem. So Botond, come and tell us your research.
Thank you very much for the kind invitation. It's very nice to be here. A lot of different topics are here that normally I would not hear about. So what I like to talk about is the problem of blindness, and the last 25 years I've been working on it, and show you the first results in which, at least in few people who were completely blind, we were able to restore vision to some level, and we hope in the next year this will we will improve and show you the technologies and the understanding that led there. So vision is a process that starts with a video. This video enters your eyes. It's captured by the retina, and then here it goes to the center of the brain, arriving at the back of the visual primary visual cortex, and sort of radiates through your cortices. In around 50% of your cortex, we can measure visual activity. They're extremely highly visual animals. Now, the retina, which is in the eye, that's a part of vision, is a very tiny part of the entire visual system. Its importance lies in the fact that almost all diseases that cause the loss of vision are coming from the eye, and the one that we cannot solve are coming from the retina. So the retina, indeed, is a computer. It's a part of the brain that during development is sort of pushed forward. And what it does, it receives one video that enters your eye, and it creates around 20 movies to the brain. And these movies are simultaneously broadcasted to the brain via the optic nerve that connects the eye to the brain. As if you would have 20 cameras in your eye, each is computing a different feature, and your brain is real-time putting together. So you don't see my face. Your brain is watching, it's 20 videos of Baba in my face, a real-time guessing what is out there. Now, if we zoom into the eye, and this was done already many years ago by famous anatomist Ramon y Cajal, but you can see that unlike in a computer, when every computer element is the same, it's a transistor, what you see here is a lot of different shapes of neurons, at least 100 different shapes, we call them cell types. And each of them is a computer processor, and they are wired together to compute these 20 images. Everything starts with these photoreceptors. You have two types of photoreceptors, rods and cones. And everything ends with these cells called ganglion cells that form the optic nerve, their axons for the optic nerve, and in between there are like 100 computing elements. And the key element of all for understanding computation is this cell type concept. These are the Lego elements. But what we learned in the last 20 years, that these are also the key to understand disease of the retina, since almost all visual diseases are cell type specific. And today, almost all new therapies that we and others develop, especially gene therapies, are cell type specific. So this is really the language of medicine and science today. So what happens in blindness, which is caused by photoreceptor dysfunction, that although there is an image or there's a video that pours into your eye, there is no outcome. There's nothing goes toward the brain. That's the sort of the state of blindness. And what I like to talk about is two specific blinding diseases. One is a large family of diseases which are inherited retinal degeneration. These are genetic diseases. And the second one is age-related macular degeneration, which causes not entire blindness, but blindness at the very center of the retina, called the macula. And what I'm talking about is going at the state of blindness and try to recover vision once it's lost. And the story, what we have been working is really started in green algae, people studying green algae and how green algae can orient toward light. So they actually can see whatever we might see, and they go away from light towards light. And scientists found that these algae, they have one single protein that is needed for vision. And that is a light-gated channel that when you shine light, this opens and the current flows and the algae move. Now you need at least 20 genes to see, and the only difference between you seeing and algae seeing that you can adapt to different light levels. Here there's very little light. You would go out on the beach, there would be 1,000,000 times more photon, but you can see around because you have this very sophisticated process of adaptation. These algae, they don't, but as far as perceiving the light, they have the same ability. And the idea that came to me when I was a graduate student finishing at Berkeley, studying actually how the computer works, the retina computer works, is to take these genes from algae and put it back to blind human patients. And of course, at that time, for most people, that was a complete joke. I told these ideas, and they told me, okay, good luck. So they had no technology to put anything in your eye back. There was no real gene therapy. And the idea of using genes from a different organism than humans and putting back was really not yet perceived well. But nevertheless, I, at that time, laid down 4 different ways how these can be engineered into blind patients. And the only difference between these 4 different ways is where do we engineer in these light sensors from algae. The absolute best at that time was clear, is to put it back to the cells that lost their sensitivity, namely the photoreceptors, in this case cones. And the worst, but the absolute simplest, is to go to the last cell type in the retina, where you would lose all computation, but you would just get a light-sensitive layer. What I like to talk about is showing patients with this last approach, because this was the simplest. So this took us around 20 years to get there. And I'll show you how, meanwhile, spent 15 years of engineering the best approach, which will be in clinical trials in 2-3 years. But technology completely changed. Now we can really target 1 out of your 100 cell types in a living human with a gene therapy vector. And the technology we use is a gene therapy vector. These are called adeno-associated viral vectors. This is basically a protein ball. And this protein ball inside, there is a single-stranded DNA, which has 2 regions. One where the gene itself, what we put in, and this is the light sensor coming from algae. There are, of course, hundreds of those, and we have to select which is relevant. The other one is a postal address. We call them promoters. Basically, when the virus goes into the cell, it will just enter indiscriminately most of the cells. And this promoter tell it which out of the 100 it should express the proteins. And this is actually the hardest part to engineer something that in a human actually would work in the right cell type. And the way we find these promoters or these DNA regions, these actually synthetic, we create them, is first we developed a technology to make very large scale human retinas in a dish. This was first shown by a Japanese scientist, Yoshiki Sasai, but he was unable to build fully mature retinas. And a postdoc in my lab, Magdalena Renner, showed that a new procedure that she can build actually a 5-layered human retina called an organoid in a dish. And what's nice about them, we can make tens of thousands of them. So recently we did a screen with Novartis testing a drug screen on 20,000 human retinas. And these retinas indeed light sensitive, and the cells actually compute information. And they have many of these cell types you have seen before. And this is the key that we can put them into 96 well plates and test a very large number. Indeed, by now we tested around 3,000 different viral vectors in them. So we can reduce them down to, let's say, a few hundred. And then we use another technology then, is because the post-mortem human retina. This was developed mostly by Arnold Szabó in Budapest, the ability to keep alive after patients die. He can keep alive human retinas for around 20 weeks. And this is a really key technology today, because in the adult final tissue, what we want to do with the gene therapy, we can develop the gene therapy. So this can be cut to small pieces from organ donors, and we can test hundreds of viruses or gene therapy vectors we can test here. So what we, in the end, we get in the human retina some viral vectors that can very precisely can target specific cell types. Here some you see on this picture. So I'd like to, using these technologies, I like to now talk about patients and what would they see with the absolute simplest approach. Now, it's the simplest approach for patients, but time in medicine is going fast. So this is still from the idea of 2002, the first patients was 2019 that was injected. And we actually we kind of evaluated during COVID. And this was a collaboration with José Sahel as an ophthalmologist and several other people and a small company we started in Paris. So what it is a very simple injection. So what's complex is to create these viral vectors. What is very simple is the therapy, because simply you inject into the eye. This is a 10-minute procedure. This is called an intravitreal injection. And what we developed together with GenSight is a goggle. This is like this, except it's black here. This is a goggle. It's a video camera that's watching the world. And a projector in the back that is projecting something to the eye, at least one eye. We only inject one eye in this case. And a computer in between that we can mimic some of the retinal computations, because in this case, again, there's no retinal computation. It's the ganglion cells which receive the light. There are other reasons, I don't have time to go, but what it gives us an opportunity that when a patient is injected and there's no goggle, the patient has absolutely no vision. It's the same as there would be no injection. Maybe you put on the goggle, that you can test what can you see, as opposed to the no goggle condition, which is the blind and no blind condition. So I show you two patients. So far we had 10 patients, but these two is basically describing what they are capable of. And the very first test, they had the task of have the ability to perceive an object, to locate it, and then to touch it. And this particular patient became blind at 48 years. What I mean by blind in this case is that he was unable to see object, but he could tell the source of light. So in a dark room, like algae, when there was a light source, he could orient that way. And the reason we did it, we started with this one, with this patient, because we thought it's important to learn where is the projector the light is coming from. Later, it turned out to be not the case. But so what you see here is as the beginning, when there is no, we call natural monocular condition, which is no goggles. So this is the normal blind condition. And this patient had the task of finding this notebook. And you will see is that, so he's speaking French in the background, but the point is that he sees something coming from the table, but there's no perception of any objects on the table. And then we put on the goggles. You can see them on the patient, and now here you can see on this MacBook what the video camera is actually recording. So the patient is sort of scanning the table, and you can see at one point is that the object will be on here. The object is now in the view of the camera, and the patient then says, yes, there is an object. It says it's on the right, and watch the sort of the precision of the motor action. Now he has to find it and points to this object. So what we see, and this is very characteristic of this patient, is that it takes quite a while to find the object because it is a very, very small visual field. So the infection of the retina is very small. But once it's able to find it, the motor action is incredibly precise. So despite 10 years already lost vision, you revoke the motor action, and then it's incredibly precise. That means that the brain keeps it for a long time once you learn vision. An even more sort of extreme example I'll show you in the next video, which is a 70-year-old lady who has to count these pens. She had actually zero vision, so it was a complete lack of vision. We lost around 20 years before, and she's sort of going around and counting. But the point I like to make is at the very end, we ask her to put her fingers on one of the pens. And this is what you see. And this is the precision you can do. Is that, so again, it's telling us is that it takes time to find the objects, but the motor action is incredibly precise. Now, so what we found in these patients, around half of the patients we tested had actually visual recognition capabilities, is some patients has extremely good object recognition, but none of them have face recognition, nor the ability to read. And that is because what we transduced here is really the ganglion cells, and the retina has no computational ability here. So in order to get there, we turn to another technology, namely go for the best approach, which is to target those cells, the center of the eye, they call the foveal cone photoreceptors, that lost their ability to see, but in many cases the cell body is still there. This is an approach we actually published very early, but we relied at that time on mouse models, and it took a long, long time to develop it together with Bence George, head of translation at IOB, and we just started a small company, Basel, to bring it to patients. So the key point here is the ability to build a gene therapy vector that very precisely and exclusively targets out of the 100 cell types the central cone photoreceptors. And this is what we achieved. That is 4 years of optimization, is that the green signal here is the sensor, the red is the cone marker, it's a human retina, and it's basically one-to-one. Almost all the cones have the sensor, and almost all sensors are in the cones. Now, the key point before going to therapy is that how would we know that it works in humans? And this is a real ability to keep alive human retinas post-mortem, because that's where we can test. So the technology we developed is to take organ donors, and the very first day of organ donation, we can put the retina on a multi-electrode array, which can record from the human retina. This has 30,000 electrodes developed at ETH by Andreas Hirlemann. We put the retina on the day of donation, and we show light stimuli. So you can see 1,000 electrodes respond as we flicker the light. So this is normal, healthy human light responses that normally would go to the brain. In this case, the patient is dead, so we're recording in a dish. But these light responses, after one day, they go away. the retina, the photosensor would degenerate. So we can apply our therapy on these retinas post-mortem. Wait 5, so just to show you, in a healthy retina, you get different responses. I don't want to explain you how the retina works, just you see that each of these different colors show you different types of ganglion cells responding to the stimulus we show. It's just a flash of light. So what we can do now is apply the gene therapy after the normal light responses go away, wait 5 to 9 weeks post-mortem, and then go and test again, and then compare. And this is remarkable with the newest approach, so-called OVE approach, that essentially the responses we get in human retina is identical to the one that normally you would get. So this is the best approach we can ever be able to come up. And this is what we are now bringing to patients. But the key, of course, a key question that might occur to you, that are there patients with remaining cone photoreceptors, or they might die? So before going to therapy, we did a large international study. My institute conducted this study across 18 countries where we would look at blind patients with now using optical coherence tomography. This is a technology that we can image the retina in living humans. It takes around half a minute to get these scans, and found around 62% of the patients who go blind have remaining cones. That means we will not be able to target all these blind patients, but only, let's say, 2/3 of them to go for therapy. Now, this is a story I wanted to share with you, and sort of finish with 2 thoughts. One is that you might ask, is that why don't we work on technologies that stop the loss of vision as opposed to restore vision when it's lost? And the answer is very key. It's much harder to keep a vision than to restore it. This is very counterintuitive, but the reason for that, because in medicine, we can do things if it's safe. We cannot do, no one would go with a gene therapy to your eye if you still have somewhat vision. We would never do that. But when you go blind, it's like having cancer, that you know that the patients, if you don't do something, will die. In the case we know the patients, you cannot be more blind than blind. So we have a real opportunity in medicine to actually test gene therapies that we have no clue. At the end of the day, we cannot predict therapies. But this gives us an opportunity. This gives us an opportunity to really develop safe sensors. So what my institute is doing is now turning into a second phase of working on how can we prevent the loss of vision in other diseases, such as glaucoma, or indeed age-related macular degeneration or diabetic retinopathy. The second remark I like to say is that what I've talked about is how to go from a basic understanding of a part of the brain to therapy in really rational steps by developing technologies over 25 years. But at the end, somehow these developments also brings back a new basic science. So what we have now in the lab is a human retina post-mortem that is able to respond to light just as your retina responds in your eyes. That's what I showed you. So that gives a completely unique opportunity. We can study a part of the brain, the retina, in conditions that we could have never imagined. Now we have a brain part which is fully functional, and the first time we can study the human brain in ways that we could not imagine without developing this therapy before. And with this, I'd like to thank a lot of people in my lab, previous lab members, collaborators, especially José Sahel, whom I have been working for a long time on ganglion cell-based visual restoration, Benze George, with whom I'm working on this new cone-based visual restoration that hopefully gets the ability to restore the recognition of faces and to some level of reading. And thank you very much for your attention, and happy to answer questions.
Thank you so much. You really give the hope for the blind people. So, some questions?
There is one there.
This is really fascinating. It's out of my field, but I think I recall that some people who go blind and have their eyes removed lose the sense of circadian rhythm, whereas people who have preserved eyes still maintain it. So what happened to your patients in terms of their circadian rhythms when you have the probes expressed?
Does it work? No, yes, so it's only those patients lose circadian rhythm where the optic nerve is atrophied, so the end stage of glaucoma. All these patients have a normal circadian rhythm. And the reason for that, because there is an additional light sensor, it's a ganglion cell, which is called intrinsically photosolving ganglion cell. And until you have an optic nerve, even you completely lost form vision, you would have a normal circadian rhythm.
Thanks a lot for this presentation. Optogenetics has been always very fascinating to me, although I've never really had the chance to work with it. But I wanted to ask you also about this work that you've done with Novartis. You mentioned that you've developed the retinal organoids, you miniaturized them for screening.
Yeah.
And we all know that in screening an organoids, the biggest challenge is heterogeneity of the organoids.
Yeah.
And for screening, this is a killer, can be a killer, because we have an effect that we can't compare to anything. So I wondered, how do you quality control the homogeneity of your organoids for the screening?
Yes, we solved by, yes, so the way we solve it is very different than others. Our way going that we could develop a huge number of organoids. Indeed, I can create 1 million retinas in a dish very easily. And then selecting out from that using computer vision in AI. So we have a robot that goes there and selects out. So we didn't solve the problem of homogeneity, but we solved it by overproducing. It's the same as you do in industry, that you remove the good ones. Yeah.
I have several questions. So when you make this treatment and when you inject the retina, will it stay there, or this is just temporary?
Yeah, it's very good. It stays there actually forever, it looks. And the reason for that, because these dependovirus elements, they will go to the nucleus, will not integrate in the genome, but they circularize, and they stay there as far as we can see forever. At least in patients, it's reported, some other gene therapies, they report more than 10 years. So no one has seen a decrease. We have patients since 4 or 5 years now, and there is no decrease of.
And the main problem is that you lose the activity of the photoreceptors. Yeah, the other parts are okay. So what would happen if you use the mRNA technology and just bring in the photoreceptor?
Yeah, so Katalin Karikó, I remember, actually knew her before the pandemics, because we have common friends, and he wrote and asked me the same question. He said, Botond, you should bring in RNA. So we tried that. It cannot be done. There are 2 reasons for that. First, RNA will be there for 5 days and then degrades. Yeah. So this is very good for immune reaction. It's the opposite what we need. We need forever. And the second one is that there is no good technology right now to bring in RNA. We tried lipid nanoparticles. They are toxic and they don't come in. But the key problem is not how we bring in. That probably can be solved. The key problem is RNA is to get something for a few days.
I was thinking only that maybe if you want to make some screening, what would be the best if you are working on the retina? Then maybe it can give some first.
Yeah, so if you need for a few days something, the RNA is actually quite good. And we use RNA for single cell electroporation. That works very well, but not for medicine. Now, where RNA could be extremely useful is that we have other therapies. So we have a paper coming out next week in Nature Medicine with Bence George about a completely different therapy, which is base editing therapy using CRISPR plus a deaminase. And there you want the opposite. You want to edit the genome and get out. So for that, which is different from autogenetic therapy, this would be great, but we cannot yet bring in RNA, unfortunately, in the eye of patients with current technology.
then one more question. So what is the reason why the photoreceptor activity decreasing?
They have a subcellular component called outer segment. It's a very, very specialized, it's an antenna. This antenna goes out. And in these diseases, what usually start is that the rod photoreceptors, they have some mutations, it express genes are mutated, and they die. So rods are very easy to die. The cones, for them, is very hard to die, but they lose their outer segments for an unknown process. So that's where they go, the antenna is missing.
If not, then we are almost in time. So thank you very much, Botond, for this fascinating.